Okay, all the way back, all the way back, all the way back, all the way back, all the way back. Whoa, okay, the whole thing. And finished. Okay. So the Zero Knowledge Summit is an event that's presented by the Zero Knowledge podcast, of which I am the host, and I have some of my co-hosts here as well. Zero Knowledge podcast has been around for a little while, and I use this time often to kind of share a little bit about this community in general, the podcast, the summit, other things that we're doing. So this podcast, I don't know if maybe you don't know it, but it's been running weekly since 2018. It first started October 2017. And in January 2018, we said we're going to try to do this as a weekly show. At the time, I had my co-host Frederick. And then in March 2018, we launched the first ZK Summit. And I'm pretty sure this was the first Zero Knowledge focused event that happened, so that's kind of cool. And now we are at 9. In October 2021, we also kind of initiated the ZK Hack project, which is like a learning hub. I'll tell you a little bit about it. And now I'm very excited that here, this weekend, we did for the first time an IRL hackathon, ZK Hack Lisbon. So on the episodes front, on the podcast front, we're at 277 episodes and counting. There's lots of great content to explore if you want. Yeah. And I always use this to sort of highlight a few of the top episodes. So these are the most listened to. And we have 2 new additions this time around. We have new ZK use cases with Dan Bonnet. That was episode 256. It was a very good one. I recommend it. And we also have proofs, arguments, and zero knowledge proofs with Justin Thaler. So yeah, those 2 episodes kind of popped up. Information theory and blockchain with Sriram, I think, is currently the most popular of all. Yeah. So yeah, a little bit more about ZK Hack. As mentioned, it's a learning hub. So where the podcast is often just like, it's a lot of zero knowledge, but not only zero knowledge. We talk about a pretty broad set of topics. ZK Hack is very much for zero knowledge, like education, learning, building. And we have a Discord that's quite active, and we have the website zkhack.dev if you want to check out all the things we have going on. There you can find, we have ZK Mesh, which is our monthly newsletter. You have the ZK Whiteboard sessions, which are like really good onboarding if you're still kind of new to ZK, so do check it out. And yeah, I just want to again highlight ZK Hack Lisbon. I know we have a tweet going out, I think today on the ZK Hack Twitter, where we shared all the winners. I really recommend checking out what came out of this hackathon. We were very much impressed. I think it definitely went past our expectations. We kind of weren't sure if anyone could build really anything with some of the tooling, and they did, and they built really cool things. And I think that shows a very significant moment for this ecosystem, that we're really stepping into the moment where people can build applications more easily with a lot of this stuff. I think it's going to change and accelerate what we have. If you're curious where so the ZK Hack event is actually over on our YouTube channel, but also the videos from the stages and all of the talks today will be over on the Zero Knowledge Podcast YouTube channel. There's also a lot of other cool stuff there, like the study clubs. I do recommend checking it out if you want to find out just sort of more about all of the things that we're doing. And I also want to highlight the jobs board. So we have a ZK-focused jobs board. I think we've had this for 2 years now. And I just want to highlight this because a lot of the sponsors here today have jobs posted, and they're fresh jobs. So if you're looking for a new opportunity, check that out. You can find it if you go to the Zero Knowledge website. There's jobs board is one of the headings. And yeah, you can find us on Twitter, and we have a link tree with all of these links. Do check it out. So now let's talk a little bit about the event. Zero Knowledge Summit 9. Ooh, this is a little stuck. It's our 9th edition. I have to say this is quite wild. The first edition had, I think, 120 to 150 people, and it stayed at that level for many years. We then did 2 online during COVID, and then when we brought it back last year, we started to get around 350. Like, it had definitely changed size. But this time around, we had over 800 applicants, and we have now over 500 attendees, and it's surreal and amazing. So thank you all for being here. It's crazy. Yeah. I want to share a bit about what we have kind of set up for you. We have our main stage, which is here. We have a side stage, which I will say is like really large as well. It's kind of like two main stages. They're both very, very big. There's a breakout stage, which fits about 50, and there's a workshop room where you're going to have about 20 people. For the breakouts, in the afternoon, there's also going to be workshops hosted there. And I would say if you're planning on doing a workshop, go with the intention of really engaging. Bring your laptop, ask a lot of questions. It's meant to be very interactive. We also have a co-working area upstairs, and yeah, I think you'll be able to explore a little bit the space. I don't think I have a slide about the program. I want to make one quick correction, because I know somebody pointed this out. On the printouts, on your lanyards, and on our signs, we accidentally put, for our final talk, both like the one before and that one at 5. It's 5:30. It's just afterwards. So just, we saw it. Sorry about that. Yeah. Password, there's no password on this, and I believe you should be able to find this quite easily, so check out the Wi-Fi if you need it. I want to say, I don't know if the team is all here, but I want to say a massive thank you already to this team, and especially to Agnieszka. Is she here? Oh no, I think she's outside. This event, I mean, not only this event, but ZK Hack and this event was very much like Agnieszka's effort and energy. So she's not here, but I still want to give a big clap out. I want to just clap for Agnieszka. Thank you so much. Yeah. I'll tell her. Rachel was working with us this entire time on speaker management and attendee management, so thank you, Rachel. There's me doing a little bit. There's Henrik, who is, you might actually recognize his name. He's also the podcast editor. He used to do all the film work here. This time around, he was the kind of AV advisor to us, and he's going to be hosting the side stage with Alex Pruden. But yeah, Henrik is also the person who made the jingle for the show. So if you like that, that's his music. And I want to say a big thank you to Kobe, who helped on the backside with programming. So yeah. So let me thank our sponsors, our fantastic sponsors who really came together to put this on with us. Our platinum sponsors this time around, returning sponsors are Alio and Nanoma, and first-time platinum sponsors Jump Crypto. So thank you to these top sponsors for coming on board. Maybe we'll clap that. We can't do it without them. I think that needs to be, yeah. We have our gold sponsors, ZK Sync, Era, Lambda Class, and Risk Zero. And actually, all 6 of these teams have booths outside, so you can actually meet those folks. And they also, most of them have jobs on the jobs board. So yeah, I just want to highlight that. We have our silver sponsors, Scroll, Polychain, 1KX, Fenbushi Capital, and Lemniscape. I think I'm saying that right? Lemniscap? Sorry. And we have our community sponsors, Sysmo, Geometry, Aztec, Espresso Systems, Celestia, Snarkify, Panther, Sunscreen, Gnosis Chain, and Ironfish. So thank you to all of the sponsors for coming on board for ZK Summit 9. Yeah. Cool. So now it's fun. So I think you all noticed, so we do this application form every year. And it's kind of hard to do. Like, I know there's a lot of questions, but it's really useful what we learned from this. And we always ask kind of a question. And I have to say, ZK Summit 1, we had asked something like, what is zero knowledge? You know, because we didn't know it back then. But they've become progressively harder, more in the weeds. And so we asked this question on the forum, and I'm going to share with you a few of the answers that we got. So the question was, how would you explain the lookup argument to a friend? It's a mathematical proof that a thing is within a thing. Some relations are hard to express using low-degree polynomials, which is the typical language of ZK. To model these, we can simply list all tuples that satisfy the relation and add a constraint saying that a tuple is in the list. I think this is quite good. How would you explain the lookup argument to a friend? Look it up. And we got a lot of those. We got look up, don't look down, do look up. Anyway, a lot of these. It's like a note of things you need to quickly recall. Lookup arguments is a pre-written list of things that it can be. I think can't actually shouldn't be there, but it is the main character featured in the Jungle Book. Ah, no, that's Baloo. It's actually a material used to seal joints in pipes. Ah, no, that's caulk. Maybe it's just a protocol for proving that the elements in a committed vector form a subset of the elements in a preprocessed vector commitment. All right. How would you explain the lookup argument to a friend? Someone just posted the whiteboard session video with Mary Mahler's lookup arguments for performance optimization. I liked that. It's like giving the proof system permission to bring a one-page cheat sheet for the exam. And Nico, who helped me with this was his favorite answer. And then one answer was, I wouldn't because all of my friends know that already. Yes, I have a weird set of friends, and I think your friends may all be here. But yeah, thank you all for these great answers. It's always fun to see what you come up with here. I want to sort of mention one last thing. I don't know if you're aware of this, and maybe don't turn it on right here, but there's this project that Kobe created called zkpod.ai. It's a LLM. He fed it with all of the podcast transcripts. You can ask it a question like, what is a lookup argument? And then get my voice answering sometimes correctly. It's not perfect. It's something we're working on. But I kind of wanted to mention it here. If you hadn't seen it on Twitter, you might want to check it out. And I also want to mention it because this is sort of like a very experimental project that we're playing with. I mean, it's very much Kobe's, but it's my voice, so I'm sort of involved in it. But yeah, I think we are looking for people who might want to work with us on stuff like this. And actually, not only this, generally for the show, for the events, for the hackathon. If you're really looking to get involved, I'd love to kind of hear from you. If you're looking for a new opportunity, you can look on our jobs board, or you can actually get in touch with us if you want to work on any of these projects. So I would say find us on Twitter, ZeroKnowledge.fm, and then send maybe a note in DM, and then we'll kind of get you into a funnel there. But yeah, I wanted to do that. I usually, in the past, I haven't really felt the need to sort of put that call out, but things are growing really quickly right now. And yeah, I'm definitely looking for new people to join our team. So that brings me to the end of my intro. Welcome again to the Zero Knowledge Summit. I hope the day is amazing. I am very excited for the talks that we're going to see. Yeah, and I hope you're excited as well. Can you put the slides back on, please? Sir? Thank you. Okay, I now want to bring up our platinum sponsors to share a little bit about, kind of what got them interested in this event and what they're working on. So first, if Raul from Jump Crypto could come up. There you go.
Hey everybody, how's it going? Hopefully you're not as jet lagged as I am. But yeah, really excited to be here. I just wanted to share a couple of notes about what Jump Crypto is, what we do, and like why we're even interested in the space. So Jump Crypto started out, as kind of the crypto sort of arm of Jump Trading, which is a quantitative trading group. Does high HFT sort of trading stuff, trades like a bunch of different asset classes around the world. We're based in Chicago, Illinois. But we started in 2015, kind of core like bread and butter trading stuff. Over the past few years, we've really expanded into a bunch of different efforts, venture, building in the space, doing, contributing to a bunch of different open source projects. A few of them, I'll talk about them right now. So Wormhole is a big one. It's a cross-chain messaging protocol that's now living across 22 different chains. And so there's, we've put in a lot of effort in terms of like contributing to these open source initiatives. Pith is another one, which is a high fidelity data oracle that brings price information on chain. And then right now, we're contributing to FireDancer, which is a low latency validator client for Solana written in C++. On the ZK side, and the applied crypto side, we're sort of just getting into the space. And so last year, we participated in the Z Prize, which I'm sure you guys have heard of. So we helped accelerate, MSM and NTT on FPGA, as well as being like large sponsors. And right now we're working on a bunch of different initiatives within the team, including Silo, which is an MPC in-house custody solution that we use, basically on a day-to-day basis. And now we're looking to kind of expand these efforts, see what we can do with Zero Knowledge, and kind of contribute to the ecosystem with various different open source initiatives as well. So really excited to be here. Thanks, guys.
Great. All right, next up, I want to invite Alex to the stage, who's going to share a little bit about, or from Aleo, to share a bit about zPrize.
Hey everybody, how's it going? I'm Alex. I am the CEO of Aleo, and I'm also the co-host, I guess, of ZK Summit. I'm going to be on the side stage, so some of you might see me over there later. But right now, I'm not going to talk about either of those things. I'm going to talk about what was just referenced up here, which is zPrize, which some of you, well, anyone who's been to a prior ZK Summit has probably seen me give a variant of a talk about zPrize, so you may have heard of it before. But it's something that I'm really excited about because it's something that encompasses, I think, our entire space and our entire industry. And the intention behind zPrize was to kind of make an XPRIZE-like thing for accelerating zero-knowledge cryptography. We started it last year, ran a competition, that just some quick stats. We had 32 partners, 20 sponsors across both Web 2 and Web 3. We had hardware companies like AMD providing hardware and Samsung providing mobile phones. And you name, it's the who's who of people in ZK and Web 3. We had 140 people apply to compete, 24 submissions across 12 different prize categories. So overall, the goal was accelerating ZK, and we, I think, achieved that, at least through the lens of looking at hardware and setting some standards for some of these low-level algorithms, such as multiscalar multiplication and NTT. So really proud of the success there. We actually have for anyone who's curious and likes Anna's show, I have a little QR code here for the 2 episodes in which we covered hardware acceleration for snarks and did it through the lens of zPrize. We interviewed 1 of the architects and 3 of the competitors. And so you can find out a little bit more. And also, for anyone who's interested, all the entries, I forgot to mention a very important thing, all of that work was open sourced. And we have this repo here that I've linked in the bottom corner. And all of that, anyone who's interested in, what the fastest MSM implementation looks like on a Samsung phone, you can find that here, as well as all the entries that were submitted, not just the winning ones. Okay, so now, and I guess I should say the thing that there we go. I think the thing that I'm really happy about is that this is already, like I said, becoming effectively the reference and the baseline by which others are basing their work, right? So this was kind of, zPrize was meant to be the beginning, not the end. It was meant to be the foundation that others built upon. So it's great to see that already happening. Okay, so that's where we are. Now where are we going? So, zPrize started, it was a brainchild of me and a few other people about a year ago. And then, as I said, a lot of other folks came together to make it successful. Now, where do we go from here? So today, what this is a nonprofit, again, focused on accelerating zero-knowledge cryptography, right? I organized it along with a few other people. We basically, Aleo contributed a lot of resources, and of course, sponsors from around the world and across the industry contributed money. Where I would like to take this, and the direction we're going to start going as we look into the next iteration of zPrize, is making it decentralized, turning it into a DAO, having it be a community-owned, industry-wide project that we can all contribute to. So that's where we're going. And ideally, that will open up the aperture for many, many more people to contribute, and for many, many more people to contribute solutions to problems that face the industry as it evolves. So I'm going to talk a little bit about this here, but I would really encourage anyone who's interested in this concept or thought that zPrize was kind of a cool and interesting initiative and is interested to get involved to check out zprize.io. But the short answer, or the short form version is, there's a lot to do. This is building a DAO from scratch, right? So not only do we need to build a community, but everyone who who has the ability and or willingness to contribute absolutely would welcome your help. And yeah, on that path, we have a steering committee. Steering committee consists of myself, John Reynolds, who's also at Aleo, who helped me with some of the logistics, Anna Rose, who's volunteered to come on board and help this time, as well as Luke Pearson. And by the way, the steering committee is not limited to these 4. So if anyone has someone they would like to nominate for the steering committee, you can send me a message. I got the contact info at the last slide. But absolutely want this to be a group of people, leading industry experts, who can help define 2 things the steering committee will do. 1, define the structure of what the DAO will look like to ensure that it accomplishes the goals of zPrize. And 2, to run the second competition. So you kind of see these parallel track efforts on the slide behind me. So that's where we are now. There'll be a steering committee consisting of these folks and others that potentially get included that will run the second competition, bringing on sponsors, identifying architects, inviting competitors, judging all the results. And so we'll do Z-Prize 2 all over again, just like we did Z-Prize 1. But also, hopefully, by the end of Z-Prize 2, this thing will be a DAO that lives out in the world. And then the DAO will determine where it goes. Do we want to have a hardware focus? Do we want to look at applications? Do we want to do ZK, or do we want to open the aperture to focus on FHE or other things? All of these questions are going to be what the DAO contemplates. And this is kind of the way I think about it, is the Gitcoin for ZK kind of idea. So last thing I'm going to leave you with, my last slide here, is maybe this is some motivation for why you should think about doing this, if this is even of passing interest. This is a quote from one of the competitors who actually did quite well in the competition, won one of the categories. But this person had no background in ZK, had no background in cryptography. They just were really good at GPUs and programming on NVIDIA GPUs. And and they got into the space, and now they're actually they're speaking at a number of conferences about their work. And I think this was the really cool thing about this initiative, is that it brought new people in who maybe had never seen this before, but realized that they had something special to contribute. And so I hope that both in Z-Prize 2 and in the future Z-Prize DAO, we can continue to do that and grow the space with talented people that we'll need to ultimately succeed. So thank you very much. For nominations to the steering committee, or just to learn more, here's some contact info. That's my Telegram right there, and then you can use interest@zprize.io. Lastly, zprize.io, the website, you can go on, and there's a Discord group that you can join there. Thank you all very much. Oh, and here's some QR codes for the Discord specifically.
So cool. And Alex, we were kind of saying that I think at a previous summit, we had actually seen sort of earlier iterations of this, so it's so cool to see where it's going. I'm excited to be part of it. Awa from Anoma is now going to share a little bit about them.
See if it works. It works. Hey everyone, I'm Awa. I work on Namada and Anoma. So the question I've been trying to figure out for the last 2 years is, what the fuck is Anoma? And we're getting there. So actually, who here has heard about Anoma? Could you raise your hands? Wow, so everyone has heard about Anoma, and do you know what it is? It's like 10% of people who raise their hands know actually what Anoma is. So okay, I'm here to help you out. Anoma is an intent-centric privacy-preserving protocol for decentralized counterparty discovery, solving, and multi-chain atomic settlement. That doesn't help, right? But if you had to remember one thing from this tagline, just remember that it is an intent-centric architecture. So this is the key principle behind the design of Anoma, which is that users authorize their desired state transitions as preferences. They do not authorize transactions in the case of the Bitcoin model, or they do not authorize execution traces, which is the case of the Ethereum model and Ethereum-like architectures. So this gives actually birth to a third generation of architectures. And we actually think that this is going to bring in new economics and new market structures. Some of these examples are decentralized sequencing, pretty hot topic nowadays. Collaborative solving and block building. I think some of the teams are working on something like this. And this one you will find really interesting, which is decentralized markets for provers. So just remember one thing about Anoma. If people ask you, what is Anoma? Just remember to say an intent-centric architecture. So part of Anoma's architecture is Taiga. It is the unified execution environment. It's the part that has a lot of crypto. And there are a lot of questions that we get asked frequently, like what is the difference between Taiga, ZXC versus ZXC, so on? How does Taiga enable composable privacy? How does it enable decentralized counterparty discovery, and so on? I will not answer these questions. Go to Julia's talk later at the breakout stage at 11 UTC. Another part of the Anoma ecosystem is actually a project called Vampire. You can think of Vampire as the LLVM for polynomial circuits. And very important, Vampire is not Anoma specific. It is front-end and proof system agnostic. And our purpose behind Vampire is to have a project that pushes forward standards. So it is not going to be Anoma specific. if you would like to learn more about Vampire, Joshua is hosting a workshop on very hands-on on Vampire. And you might know Joshua for a really popular article that he wrote about Plonk by Hands. So it's going to be really cool. Here's an extra incentive. So we have the first edition, edition 0 of the Vampire stickers. These are from 2023. They're limited, they're really, really scarce. And we're only handing them out to people who participate in the workshop. There will be one workshop here, and there might be more this year. But the ones who get this year, and in the future, Vampire actually becomes a standard for second languages, then the ones who will know. So yeah, try grab them before they run out. All right, I am obliged to mention Namada, which is another project that we're working on. And Namada's purpose is to shape multi-chain privacy in providing the best privacy guarantees for the multi-chain user. And I have to tell you because we're launching mainnet really soon. So how does Namada provide the best privacy guarantees for the multi-chain user? I am writing an article that explains this like step by step. It's actually pretty interesting. But the spoiler, the TLDR of the article is that size matters, and then the shape too. So if you'd like to read this article when it comes out, just follow me on Twitter. I will publish it there, and follow Namada is probably going to be visible through there too. Thank you.
All right, so that ends the intro of the ZK Summit, and we will now be starting on programming. We are actually opening up right now 3 stages. So here, we're going to be hearing from Brian Redford from Risk Zero on future ZK, emerging use cases and key enablers. On the side stage, we have F. Flonk in the ZK EVM with Hector Masip. And on the breakout stage, we have lookup arguments based on logarithmic derivatives. So choose your stages, and we kick off. Yeah. And yeah. Do you want to, maybe we just get you set up, and then I'll do a quick intro? We'll give folks a moment to do a little shuffle.
Oh, I know. I was
going like.
Yeah. I'm just hoping I don't I didn't talk at Starfare and I was so jet lagged. No, I'm fine right now. Starfare when I was so loud.
Everything's great. I love your
I'm tired and I'm too hot, so I felt
you look great.
I'm going to take this off right now.
But I mean, you don't look tired.
I am.
I know, you don't look.
Brain is not working well. ZKpod.ai should have been doing this introduction.
Kobe needs to get
I
ZK
have
out.
so many plans for ZK10, which just like have other things. I think just in the back, can we have the slides ready? Perfect. Okay. Here, why don't you can already come up. I want to invite to the stage Brian Redford from Risk Zero. Hey, folks. Hey, everybody. Hey, hi. We're going to start. So if you could just start to be quiet. Thank you. Okay, Brian's going to share with us Future ZK, emerging use cases and key enablers. Welcome to the stage, Brian. Let's give him a hand.
Thank you, thank you. So I was inspired to make this talk because, well, I spend a ton of time thinking about it, and I think it's important to think about as we're building all of these ZK systems. You know, what is the future that we're driving towards, and how should we go about getting there? For those who don't know, I'm the CEO at Risk Zero, where we are on a mission to fix the internet by maximizing the utility of ZK technology. So what I hope people take away from this talk is that you can use cryptography to effectively make the world better. And I really want people to be inspired that, you know, ZK is not, we're not even, I don't think we're really past the start of our sort of journey to where this technology can go. There's a lot more to be discovered, and there's a lot more to build. So I'm going to talk a little bit about the state of ZK, current opinions about how it exists. Talk a little bit about why I think it's going to make the world better. And then I'm going to talk about key enablers, which are technologies and sort of capabilities that if we collectively work on will unlock more ability for ZK to impact the world. And then I'm going to walk through up to 3 emerging use cases that I think are really interesting. Okay, so the state of ZK. I interviewed not as many people as I would like, and then sent out a survey too late, but I still got a lot of interesting data from people, and I would like to definitely do this in the future, but I have a bunch of, well, I want to do it in ZK, but I'll get into that maybe later. So the first thing I asked people is what they thought the biggest opportunities for ZK technology were right now that had not yet been realized. So the first one, I would say far and away the one I heard the most was identity. And I think this is obvious to most people. You know, I'm personally quite sick of logging into things with my Google account. I don't really want a Google account. I want an account that I own, that nobody else, you know, that I basically am in control of. And I want to be able to design, you know, the recovery mechanisms that make sense to me for my life circumstances. And I think there's a lot of progress being made here, and a lot of companies and teams working on it, and so I think that's really promising. There's been a ton of progress in faster and more capable proving systems. And you know, you can see in ZK Hack the result of this, and that's that you can accomplish a lot more than you used to be able to. And if you look at the research that people are coming up with and just the improvements in Z-Prize and just techniques, this is going to keep going. So I don't think we're anywhere close to maximum ZK performance at all. And then I think, you know, a lot of people, when they first hear about ZK, you spend a lot of time trying to wrap your head around the axle of like, what does this actually do? And obviously it can be used for privacy, but it doesn't really solve as many problems as you necessarily want it to without some friends. And those friends are like MPC, FHE, or just regular HE, you know, all the sort of interesting cryptographic techniques that you can hear about on the podcast. So, disappointments. I asked people what they thought the, you know, most disappointing aspects of the ZK ecosystem were, and then people said that it was maybe too hyped and just not as useful as they imagined it would be or wanted it to be. But I think, yeah, I think maybe it will be if people keep believing. The bad DevX, that's definitely, that people highlighted that a lot, but I do think that watching, ZK hack, it was pretty impressive how far people were able to get, but then if you read the write-ups and part of the judging, you could see how many obstacles that people ran into that weren't really core to what they were doing in their project. So there's clearly a lot of room to go on that front. The fact that it's not being applied where it could be, this kind of gets into identity and opportunities to actually, like we still don't really have good privacy preserving blockchains that allow us to interface with the regulatory apparatuses in our country and countries in a reasonable way. But we could, maybe. Speaking of that, people complain that the timelines are much longer than they imagined for lots of things. This is obviously true. This talk, I think, took me much, much longer than I thought I was going to take me, and I would like to spend much more time on it. So, and then, there was a lot of concern around the sort of siloed and non-interoperable nature of most of the tooling out there. And I know there's a lot of work going on to try to form standards and things like that. And all of that's very positive. The next thing I asked people was like what their wackiest application ideas were. And I was going to highlight some of those, but instead, sorry, I got ahead of myself. Right, I asked people what they thought the most visible impact of ZK was going to be in the next 3 to 5 years. And I got like a couple, some people said nothing, and I was kind of like disappointed by that answer. But people also said nothing for 2 reasons. And one of them was that the amount of work, it's just not, we're not there yet. There's not enough maturity to really build something that's really going to impact the world. And then other people said cryptography, shouldn't have any impact. It should just kind of exist in the background and you shouldn't notice it. I think that's very much not true anymore, and I think it's increasingly not true. As we see, systems, as we start building ZK identity systems and we see how readily, advanced AI can replicate us in some, facsimile form, it's going to be important that people understand the contours of cryptography, I think. And it's a challenge for us to figure out how to explain these kinds of things to users. People did, in fact, think that we will have this sovereign identity system in 3 to 5 years. I think, 1.5% of Portuguese people have world IDs now or something. So, yeah, so people are making progress. Now, it might not be the progress people want, but, people can build identity systems. Now, I think, okay, people might argue that blockchains are public computing infrastructure, but I actually think that it's not. Like, blockchains are great, but there's a lot more we could be doing to increase access to computing for people around the world and ourselves. Okay, so ZK hack. Rather than talk about the wacky applications people told me about, I thought I would highlight some of my favorite hacks. So one of them was just building decision trees, which are a old school ML technique. It's not deep learning, but that's still useful. And there are actually a lot of non-deep learning ML techniques that are interesting in ZK context. So you can use this to build classifiers for various things. I'll talk about where that might be useful later. This Zero Gravity project, which is by far the best name, because it's weightless ZK ML inference. So it actually uses Bloom filters and maybe hop-filled networks. I'm not sure. There's a paper that I meant to link to down there that actually goes through this. I haven't read it yet. I really want to. But it's really cool idea. So if you have fast ZK Bloom filters, you can actually do more complex, deep, like neural network style inference. Somebody built a brainfuck interpreter, which if you're familiar with this language, it's pretty mind-blowing. And I think it's just a kind of a fun project. There are potential, interesting use cases for this, like competitive coding and other things. But it's cool that somebody was able to actually write an interpreter for language in ZK and then basically allow people to pass programs in as strings and then get a proof that the program was executed. So you actually prove that you know a brain-fucked program that has like less than 50 greater than signs that, I don't know, computes Fibonacci up to 10 cycles or something. Very fun. People did some work on interesting sharding protocols. There's a lot of applications for ZK to actually make a dent in decentralized storage. It's a very, very hard problem. ZK P2P, this blew most people's minds. Is that the one that won? Oh, yeah. So they actually used, it's like made a marketplace where people could choose to on or off ramp their fiat through Venmo. So it just kind of matches people with Venmo. And there's actually, I think this is a really cool idea for a lot of things. And then people started playing around with building reputation markets where you can actually, associate some reputation with a seller in a way that's a bit more transparent. Sorry, more private than Amazon or any of these sort of public things. So I think, as I mentioned a bit earlier, maybe, that ZK is one of the most salient technologies of this sort of current moment that humanity's in. And what does ZK do? There's a lot of ways to think about it, but it really does minimize the trust that we have to place in third parties that might be or often are counterparties and don't necessarily have our best interests in mind. So I think by removing the numbers of parties we have to trust, ZK actually enables us to trust each other more. And by giving us control, along with some of its cryptographic friends, of our information, we have trust that our sort of projection into the digital world is more under our control, which lets us do more, lets us build stronger communities, and gives us more voice in those communities. And this is basically my pitch for let's replace Twitter with something better. Cool. So key enablers are ways I think about capabilities of ZK systems that are very relevant to building better applications more quickly and sort of moving the space to the next level of maturity. So I just kind of lumped these into three categories. Parity, which is making ZK systems more like regular computers. Flexibility, which we'll talk about. And then combining ZK with other kinds of technologies for more enhanced application potential. So I think of the sort of parity category, these are the slightly older slides, that's okay. The most important is compute parity. So this is the idea that you should be able to run any program anywhere and have it fully utilize whatever hardware is available to it. And this is a big task, A lot of teams are working on this. We're obviously very focused on this at Risk Zero. Some people think it's impossible or very far away, but it's really, I think, necessary to do a lot of the things people want to do in a reasonable amount of time. So there's also sort of parity along the tooling access, and I think this is something people are building lots of amazing tools in the crypto space and in the ZK space, but fundamentally there's so much work that's gone into other frameworks and so many programmers that are familiar with other frameworks. It's really important that we start to let people use the programming frameworks that they're most familiar with in a ZK context if we're really going to let people build new applications. Instrumentation and debugging, just look at what people ran into at ZK Hack, and you'll realize pretty quickly that it's very opaque, like what's going on in most of these computing systems. And it's going to be really hard to let people build advanced applications if people can't get to a place where their ability to understand what's going on while they're coding is on par with other systems. And then standards is not really tooling. That meant it's supposed to go into another category. But I do think that establishing standards, especially for like proof request formats and things like this, is going to be critical for the ability of all these different potential proving marketplaces and proof systems to work together and for developers to actually use them rather than us continuing to, say, focus on a more siloed approach. So there's other kinds of glue that I think would be really interesting. You know, building support for OpenID and JWTs and other kinds of connecting technologies and web oracles, as people call them, I think really useful. And then also the ability to potentially, this is like a hot take in crypto, but let people bridge their systems to the sort of existing old cloud through zero-knowledge cryptography. Yeah, so flexibility, this is like the ability to make trade-offs when you're considering a proof system. Many proof systems were designed with blockchain in mind. And you know, if you're building something for blockchain, the requirements are, you know, the proof should be small as possible. You should be able to verify it very quickly. And it should be very secure, because you've basically created a log of everything that's happened. And you know, the consequences of getting that wrong are quite high, most of the time. So we'll talk about the ZK PID in a little bit. A PID is a kind of control circuit. So you might imagine that, we'll see why you might want a ZK PID. But for these kind of devices, you might not need very much security. You usually have very low power. But you need very fast proofs a lot of the time, you know, maybe even faster than 10 milliseconds. That's not something I hear people thinking about very often. And then for Ethereum proving, you know, obviously you need very high security to build a ZK L2. However, for bidding, doing like ZK MEV and bidding on blocks for like flashbots, how much security do you really need? Like really you just want to be able to say, I would like to bid on this block, and here's proof that, you know, there's enough value in it for me to pay for my bid, and that's it. And as long as somebody can't make a fake one of those, you know, inside 12 seconds, it's basically perfectly secure for that use case. So it's entirely possible that you could enable more decentralized sequencing by reducing the security. You know, maybe it's less than 64 bits. I just made these numbers up. And then ZK audit logs, which are just blockchains, basically. You want lots of security. You don't necessarily care about how much power you consume getting there, et cetera, et cetera. And like for the decentralized sequencing, you know, maybe you do care about how much power you're using because you want to make sure that people with normal GPU rigs can actually participate. So all these else proof systems tend to have, you know, maybe they support one VM, one hash function, on and on. I think it's really important that people start, you know, letting these things be parametric, and this plays into some of the standards concerns if we actually want people to use ZK broadly. Okay, so other things that you can combine with ZK to make it fun, ZKML, tons of people into this. I think there was a lot of, I got immediately excited about it because there's so many application potentials. But people were like, that's never going to happen. But I think that was like 3 months ago that people were saying that, and now there's like tons of projects building on it. So it's very exciting. There's a lot of stuff coming, advancements coming out, and I think there's probably a lot more room to be made on the performance side there. ZK database is interesting. ZK big data, very interesting. Being able to build big pipelines using ZK technology. And then obviously, you know, there's lots of research that's been done on ZK MPC and trying to make MPC more efficient by pairing it with ZK. And MPC is fundamentally a very useful primitive for a lot of applications. ZK FHE doesn't exist yet, sadly. One hackathon project almost got there. But it will soon. You know, it might not be useful for very complex computations in particular time frames, but it will actually, you know, be a thing that exists. And witness encryption is just really cool. Okay, so talking about some emerging use cases, I had to pick 3. I don't know if I'll get through all 3. But this one, so the ones I'm going to talk about are decentralized control planes, community compute, and then some authentic identity related use cases. So for decentralized control planes, we're going to start there. Like, what the heck am I talking about? Okay, there's this paper. Everyone should read it. It's only 3 pages long. It's very accessible. It's called Zero Knowledge Proof-Based Approach for Verifying the Computational Integrity of Power Grids. Power grid controls, sorry. So what the heck does this mean? Well, so this is what this is actually put out by the National Renewable Energy Laboratory, if you look. And the problem with renewables, or one of the problems, is that you've gone from a system where you had like 4 power plants for the west coast of the United States or whatever. I mean, there's way more than that. But there's very centralized power generation points. And when you move to renewables, you distribute the power generation points all over the place. Now, this can cause problems because the power grid relies on getting accurate information from devices, especially production devices, at pretty much every level in order to not break and or like catastrophically fail. So you have these individual device levels here at the bottom, and they basically have like ZK PID controllers on them, or PID controllers. They run some control algorithm that says, okay, here's my voltage variance. I don't know exactly all the data in them. And then they report that up to this next level, which makes other decisions, and then reports derived data up to the next level, which makes even more complicated decisions, and then reports it up to the next level. So this is a pretty common, you can imagine self-driving cars also work the same way. Any kind of autonomous systems tend to have architectures similar to this. So, okay, if you say the world transitions to renewables, that would be great for a lot of reasons. But then, oh, that slide's not in this version. It's okay, I'll try to explain it. Okay, so the threat model for this system, like, why would we care about using ZK in this system? Well, if, say, you were a nation-state level actor and you were really interested in making somebody's power grid vulnerable to a cyber attack, you might think about covertly replacing all of the software at the sort of edge using malicious over-the-air updates. So this is a software supply chain problem. And then get those power sensors to, when you want them to, start lying about what's happening and then melt down the power grid. Like, difficult, but possible. So the people at NREL wrote this paper about trying to use ZK to solve this problem. Is it possible? Probably. We're hopefully going to be doing some work with them to figure that out. But what do you really need from these enabling technologies to make a system like this work? So you probably need to run C and C++ because there's a bunch of proprietary algorithms written by Honeywell and Siemens, and maybe they'll port them to CIRCOM and other frameworks, but probably not. You probably need to run on any OS and any hardware, and you need provable compilation, which is pretty wacky. And that's the idea that if you take known source code, like these highly audited and approved algorithms, which are often also, as I said, proprietary and somewhat private, developed by Honeywell, you need to know that the result of those is actually running on your controllers at the bottom level. So first thing you have to do is actually take that source code, compile it in a ZK system, and produce proof that the binary that you have was produced from the source code that you expect it to come from. And then you need to actually run that in a ZK context and produce proofs that the readings coming from my power generation device are running the algorithm that you expect them to. That way so each progressive level of the power grid in this example can basically trust the information that's coming from the devices in the network at scale. It's still possible for somebody to go mess with one solar controller or mess with one battery, but that's not enough to melt down the entire power grid. The problem is if you can replace the software and massively kind of change the behavior. So you need to be able to run these proofs on these little devices very fast, every couple of milliseconds. However, you don't really care. So if you have to report a new power signal every 10 milliseconds. If it takes you 2 minutes to lie about it, then that's, what, like 600 reporting intervals, or 6,000 reporting intervals you'd be missing to make one fake one. So you could lower the security of your ZK-proof system a lot in order to sort of achieve the desired outcome, because the rest of the grid, like if you can only fake one out of every 6,000 signals, you're probably not going to melt down like a complex control system. On the right-hand side, that's also from the wrong slide. So that you don't really need any of those things for this. How am I doing on time? Cool. I'll just kind of breeze through this one. This is the idea, community compute, that everybody in a neighborhood, country, worldwide, whatever, could install an agent on their phone or just decide to participate in some program where they're part of a cloud platform. Like, I'm going to just volunteer one computer to be part of a cloud platform, and as a result, everybody gets access to free cloud computing, free or low cost. So the things you can do with this are like build games with your friends. I was talking to Jim Barry the other day, and he's like, I love building games, but it's impossible to deploy things on AWS. Not impossible, but it's hard, right? You have to hire a DevOps engineer, and it really reduces access to the fun parts of computing. Also, it's really hard to run like public goods. Say you wanted to build like Nextdoor and have it not be completely toxic. You would have to, like, it can shift the sort of economic incentive point for a lot of these kinds of projects because they don't need to sell you in order to make money, and they don't need to continually engage you in order to make money, because there's no like money necessarily to be made in the app. And if you don't need money to run the infrastructure, then it can all sort of work. So, like, the most important thing you need here is like a trivial proving market. So you kind of need a blockchain. You basically need enough of a blockchain to be able to like keep track of who is providing compute, who's consuming compute. It doesn't need to be super precise, and then you need the ability to run arbitrary codes safely, which is what ZK is definitely good at if you have compute parity. And then you also need to be able to prevent abuse, which is people deciding to use all the computing resources for whatever reason. I don't know, ad spamming Google, you know. And then you also want users to be able to kind of opt into what kind of content they're willing to allow on their network, and or sort of preemptively prevent it from ending up in a, you know, on a message board. So in order to really get to a place where we could build something like this, yeah, you need to be able to run almost any code. You probably need to support JavaScript in ZK. You need to be able to run on mobile and in a browser. You definitely need some kind of way to easily bridge your identity. And you probably do also want like variable security, and you want provers that maybe, you know, people can configure to not use every single thread on your machine, because while it's hard to play a game with your friends while your entire computer is being used to produce ZK proofs for other people. So, yeah. And then obviously you need ZKML to do this kind of content filtering and abuse mitigation. Like the decision tree models are used in like major public clouds to do this kind of analysis and abuse prevention. And they wouldn't be needed in this scenario too. Yeah, so that's very interesting. So I'll just end with this kind of wacky idea I had, which is called a pop-up, which is a proof of personhood up. And it's like, I figure if people can make orbs that scan retinas and have all of this kind of verified like chain of technology, you could make like a very like obviously small room that has nothing in it except for a ZK computer and encased in polycarbonate. And using strong identity, you could actually like prove that you're a person, go into this tiny facility and say record a podcast, and have this facility produce proof that, you know, you were actually in this thing while you were recording the podcast, and then possibly sort of regain some control over, you know, who people associate with digital content, and have it be associated strongly and cryptographically with yourself rather than, you know, the AI-generated version of yourself. So anyway, speaking of hype, Gartner says we're near the peak of inflated expectations. I'm hoping we're a bit farther down there. We'll see. We'll see. Cool. I think that's, yeah, all I have. And Bonsai is the computing project we're working on. It's a network that can run ZK on any blockchain, fully generically. And the team's all out there and happy to talk about it. Thank you.
Brian, thank you so much for that talk, and thank you for being sort of the first speaker on this main stage, talking about this kind of broad, these broad topics. That room of personhood, Brian, I'm just curious, is it a bit of a reflection on the zkpod.ai, stealing my voice? I have no control anymore, but I could record in there. Okay, nice. All right, I think I'm looking for our next speaker, There's two of them. There you are. Fantastic. I think we're going to maybe we'll take just a minute to set up, and then we're going to kick off. I'll get you guys mics too. We'll need two of them.
Yeah, how will we do 2 mics?
We should have. Oh, yeah, we have two mics. You do have two controllers. They both work, but they're sort of sticky.
So is it
It just means like they'll.
forward and back? Oh, one has a laser.
Yeah, but it's more that they're like clunky. Is it weird to now see me?
No, I've seen you before. Okay.
Oh, no, you should actually, why don't you do this? No, I think you should do it, but I want to introduce you. So before we introduce this talk, I actually want to introduce my co-host for the stage, Guillermo, who's going to be sharing sort of introduction tasks with me. So here's Guillermo, and he's going to introduce our next speaker.
Hello. Oh, yeah, that's right. Well, I'm gonna have to go to mic. Anyway, so for this talk, we're actually going to be talking about foreign field arithmetic and I guess bridging blockchains. The two speakers are Anais and Joseph from O1 Labs. Good luck and welcome. And here's, I'll steal this one.
Yeah. Hello. I guess we will start. What time is it? Yeah, I guess it's fine. Yes, so welcome everyone. Thanks for attending this talk. My name's Anais Querol, and he's my colleague and coworker, Joseph Sparavecchia. We're both cryptography engineers at O1 Labs, and today we wanted to present an ongoing project, and we entitled this talk, Bridging Blockchains, Foreign Field Arithmetics. So I'll leave it to Joseph to explain high level what this is about.
Hi. So yeah, foreign field arithmetics, that seems like quite a low-level thing. It's also an interesting problem in cryptography. But to understand it, we want to kick things up to the high level, really high. And we also want to do a metaphor. Since we're in Lisbon and we have these beautiful buildings, tiled buildings, they're very unique here, we thought it'd be cool to do it that way. So we'll talk about blockchains as buildings in Lisbon. So the analogy is that the bricks of the building are the blocks, and instead of verifying blocks, we're verifying the structural integrity of the building by verifying each individual brick and checking its structural integrity and getting the integrity of the whole building that way. So the problem is if there is a problem, then this is expensive to detect. So right now, on most blockchains, to get full blockchain security, peers need to connect to the blockchain and download all the blocks since last time they connected. they need to verify those blocks. And if it's a smart contract platform, then they need to rerun computations that are happening. So all of this is very expensive. And we wonder, is there a better way?
Yeah. So now I'd like to ask in the audience, feel free to just speak up if you're, if you're brave enough. So as a user, in order to verify the blockchain, it's a bit tedious to just go block by block, checking them all. So we're at ZK Summit. Do you know any idea that we could do in order to make this computation a bit easier? Yes?
I think several years ago, Opera had a solution that take a snapshot for...
A snapshot?
Yeah, every a certain period of blocks, and then this snapshot, the root of this snapshot is packaged into the consensus protocol.
Okay.
So that makes things happen, but I mean, that's several years ago, so it should be better now.
Okay. Wow, that was a solution, maybe a complex solution. That's not the solution that I was looking for, but thanks a lot for participating. I guess there's someone else there. Yeah, I guess that could work.
Recursive proofs of the block headers?
Yeah, you went to the very next slide. So yeah, thanks. You're a bit ahead. So yeah, actually the concept that the very basic concept that I wanted to introduce is snarks, right? We are adding snarks on top of complex computations to make the actual verification simpler, right? So we're in Lisbon. I'm sure you've seen these tiles on top of buildings. Voila. So yeah, what happens if we put a tile, like a ceramic tile, on top of that facade of the building to check the integrity of the blockchain? So if there's any problem with that building, the ceramic tile will basically break. So you, as a verifier, it will be very easy to realize if there's something wrong, because you will just spot it very quickly if the tile is broken. So this is what snarks could be used for. So this is very good for verifier, but it's not so good for a prover, because now every time you add a new block, like a new brick to the building, you have to remove that tile entirely and build another one for the increasing computation. So that's not very good for the prover. So can we do anything better? Any idea? And I guess, I don't know your name, but he suggested something which is called recursive snarks. So that's precisely the solution that I wanted to talk about. So in recursive snarks, we are trying to split that computation into incremental steps. So instead of having like a huge ceramic tile covering the whole facade, we're adding smaller tiles, like in Lisbon. So now, in recursive snarks, you have one smaller proof there, the blue one, and that tile attests for the validity not only of the current brick that you're adding to the blockchain, but it also is connected to the previous proof, like it's connected to the previous tile. So inductively, this means that one single tile, one single recursive snark, attests for the validity of the whole blockchain up until the genesis block. Okay? So this is what recursive snarks could be used for. And this is not something that we just imagined today. This is actually being used in practice. So this was all to introduce the Mina blockchain. This was the first succinct blockchain that allows verifiers and provers basically to have a proof of the whole blockchain by having one iterative step. So you just have to download one single proof, and that single proof will give you the security that the current block is fine, but also the previous proof was fine until the very end. So yeah, this is what Mina is about. And the actual tool that performs this computation is Pickles. So this is a protocol that takes care of the recursion step, and it uses the pasta curves, Pallas and Vesta, in order to provide support for the Halo 2 incrementally verifiable computation style. But the actual snark that runs inside is a Plonk-like proof system with 15-wire witness that we call kimchi. it has support for lookup and runtime tables to support more efficient computations, and a number of custom gates to extend the functionality of the type of circuits that we can prove things about. And just to give a bunch of more details, the polynomial commitment scheme inside Kimchi is based on the bullet proofs inner product argument, and this is to support fully trustless setup. And now my colleague will explain how, as a user, we can profit from these benefits.
Okay, so cool. So we have this great platform, a succinct blockchain, a great proof system that's got a trustless setup. But we want to do more than just verify transfers between users on a blockchain. We'd like to do smart contract functionality. And so for that, we've developed a tool called Snarky.js, which lets users specify essentially a zero-knowledge smart contract. And then that can be compiled down into a ZK app, which lives on the blockchain. And this has two really good features that come along with it. First is privacy. So when users interact with a zero-knowledge ZK app, then they're able to hold some information, whatever they like, private, and just generate a zero-knowledge proof that interacts with the ZK app and allows it to update the state on the blockchain. That's the first good thing, privacy. The next cool thing is that we're able to save a lot of computation. So in a normal smart contract blockchain, every time you interact with a smart contract, those instructions need to be replayed by all the nodes in the network. But in Mina, we just need to do it once. That could be by the user if it's a privacy-centric kind of interaction, or it could be done by snark workers in the network. But the point is the computation happens once to generate the proof, and then from then on, the nodes just need to verify that snark proof. So that's pretty cool. Even better, because we're doing recursive snarks, we don't have to verify individual proofs. They're all compressed into the one blockchain proof. So this is very, very efficient. So this is great. We have this cool platform. But we're still not done. And how does this relate to foreign field arithmetic? Well, that's going to begin now. So we don't want Mina to live in isolation on its own and just be this internal thing. We want it to actually be able to reach out to other blockchains and even real-world things and interact. And so this brings us to the idea of bridging. And bridging is pretty cool. And you can look at it in a lot of different ways. And in our case, we're focusing on a bridge between Mina and Ethereum. And if we look at the Ethereum side of the bridge, we have some really cool new things that are possible. Because Mina is a succinct blockchain, we're able to do really neat things like upload a proof of the Mina blockchain state into an Ethereum smart contract. So actually, within Ethereum kind of lives a Mina full node. And this is only possible because Mina is succinct. Then smart contracts on Ethereum can interoperate with Mina in a trustless and decentralized way. No trusted third parties, no committees of nodes to trust. So that's the Ethereum side, kind of injecting Mina into Ethereum. On the other side, within Mina, well, unfortunately, we can't trustlessly verify Ethereum in Mina because Ethereum isn't a succinct blockchain. So, Mina would have to download all of Ethereum, which is not going to happen. But there are still lots of really cool and useful things we can do. And one of the things we'd like to do is verify things in Ethereum. And one thing is signatures. So what we'd like to be able to do is to create a proof of the verification of an Ethereum signature in Mina. So this is the goal and the subject of this talk.
Yeah, but that's not easily done, right?
No, there's
there are
a
problems.
problem.
Yeah.
So the problem is that Ethereum and Mina, they use different cryptographic primitives. In particular, they have different algebra. And so we need a way to solve this problem.
Yeah. So they're pretty incompatible in nature. So you can see that cloud, it's raining. That's a problem, but we can solve it. So yeah, let's take a look at that cloud. This incompatibility comes with the shape of an ECDSA algorithm. Elliptic curve, digital signature algorithm. So basically, we want to verify SECP256K1 ECDSA, but over pasta curves. So that sounds already a bit tricky, right? So in order to do this, we basically need support for group addition and group doubling, where the group is different to that of your own language, that of your own proof system. We will also need support for key tag, like SHA-3. This is a very snark and friendly hash function. Yeah, this is a pain. So we basically have to encode all sorts of bitwise operations, such as XOR and bitwise rotation. This is a pain. Very simple, very fast to compute, but very difficult to verify. But this is not the focus of the talk. Instead, we want to take a look at the actual foreign field arithmetics. So in order to address group addition and group doubling, we realized that we need support for two primitives, two functionalities, which are foreign field addition and foreign field multiplication. And in particular today, we wanted to explain a bit high level what this foreign field multiplication is really about. So yeah, I'm trying to make things simple, and actually they're pretty simple. So I really hope you can follow, and if at some point you have any questions, please feel free to ask, okay? So this is the actual problem that we are facing at this point. So we have two numbers, A and B. They are 256-bit length, and we want to multiply them. That's it, okay? So we want to generate a C, and C could potentially have 512 bits. Okay, things are getting pretty long already, and this is integer multiplication. But in cryptography, we barely ever work over integers. Actually, we work over modular arithmetics. Yep. But not only that, but in foreign field arithmetics, we work over a foreign modulus. So we work over a field whose module is f, and basically this f could be larger or smaller than our native field. So in particular, for a use case in Mina and Ethereum, it happens to be the case that 256 bits for the ECDSA is 1 bit larger than the 255 bits of pasta. So yeah, there's an issue here, and it's pretty obvious. I guess anyone could say it. So we have a space problem. We have many things that do not fit in our buckets. So yeah, we basically have to find a mathematical way to solve this space issue. And we basically have two tricks that Joseph will introduce, and that will help us sort this out. Go for it.
Yeah, so yeah, as Anais said, we have two tricks. And this approach is an approach that was developed by Aztec, but we've adapted it to Kimchi. And the first trick we use is the Chinese remainder theorem. And that says that if you have two coprime values, and if the equation above holds for both of those terms, then the equation holds for their product, modulo their product. The next trick we have is we need to do arrange checks. We need to check that each side of the equation is less than the product of the moduli, n times n. So in order to do that, we do the range checks. And if that's satisfied, then this equation holds over the positive integers. So putting that together.
Yeah, so putting it all together. Yeah.
We have the situation where we've done the range checks. We only need to check the equation holds modulo n, which is our native modulus, so that's cheap. You don't need to worry about that. And modulo m. So we need to find an m such that we can, when we take the product with our native modulus, we can fit all the foreign fields that we'd like to support.
And also it's cheap enough in our case.
And also cheap enough. Because if we choose, 512 bits, we end up with, well, it's a detail that isn't presented here, you end up with a lot more constraints and it's harder and more expensive to constrain. So we need to choose something that's efficient in kimchi, our proof system. So it turns out that 264 bits works very well for us. It covers the use cases we want. But wait a minute here, this is still bigger than our native modulus, which is 255 bits. So what's going on here? Well, that's okay, because it's less than the 512 bits if we did it in some naive way. What we do is we take the 264 bits and we split it up into 3 limbs. And again, this 3 is something that turns out to be optimal in kimchi. So now we've split up our foreign field elements into these 264-bit values, which are comprised out of 3 88-bit limbs. An important thing here is that when we build out our constraints, we need each limb to fit in the native modulus, but we also need, it turns out, the product of 2 limbs to fit in the native modulus. And in this case, this is satisfied because we have 2 times 88, which is 176 bits, which also gives us plenty of space in the native modulus to do our constraining.
Yeah. So we basically have to decompose numbers and then treat the equation accordingly. So this is the equation that we really are caring about all the time. So we basically want to split those numbers into limbs. So here we have the high limb, the middle limb, and the low limb. Here I'm referring to the least significant bits on the right and the most significant bits in the left. So yeah, we basically decompose them, take the common factor, giving us the limbs position. We get that out. So we have like a nice picture of what's going on, basically. So yeah, this starts feeling a bit complex. There's a lot going on. There's a lot of multiplications. There will be lots of numbers going back and forth. So yeah, there's plenty of room for mistakes. So we have to figure out what's the right way to treat this correct so we preserve soundness and completeness. So one first step to do that is let's take a look first at the very top part. So let's take a look at what's before the equal term. So A times B plus the quotient times the foreign field. So let's take a look at that, and let's just compute that. So if we do that, we will have limbs being multiplied with each other, duplicating the length of those products. So we call these terms intermediate products. This is like an auxiliary value that will help us constrain this equation correctly. You might wonder why we only have 3, because there seems to be many more operations here going on. But the good thing is that since we are doing operations modulo m, which is 2 to the 3l, anything that is larger than that is congruent modulo m. So we can basically skip that. And that's a reason that this type of constraints will be somehow efficient. That's why we chose such an m. So yeah, we basically have these guys. And in order to do the computation easier, we'll just place them nicely. Like we will lay them out in a bitwise fashion. So yeah, this is the type of operation that we are now interested in. We basically send the result to the other side of the equal. And basically, if we're facing a real witness, then that operation should be 0, right? Because this is just the definition of the multiplication. So yeah, this is what we're looking for, and we just have to constrain that. So I think we can already see another problem, which is the same problem over and over again, which is, I know you all know, which is size, right? If we cannot have 2 to the power of 3L elements, we for sure cannot hold 2 to the power of 4L elements. So yeah, you know, we have to do something clever about this. So what can we do? Because we can only represent up to here, right? We can only fit up to here. So what can we do? We can just split. Yeah, we split. So we will split this equation into halves, bottom half and the top half. So since the whole equation should be 0, also the halves should be 0. So first we can constrain the bottom part. So we constrain that these equals 0. And then if there's any carry, which might be, we propagate it to the top half. and then also the top half will be 0. So yeah, by doing this and constraining that this is 0, and I'm purposely missing some details here to make this simpler, but the idea is that if this is 0, then you know that the foreign field multiplication equation also holds. So that was it, foreign field multiplication, but this is not the only gate that we need in order to support ECDSA. And he will be giving you some details about the rest of the gates that we had to include.
Right, cool. Okay, so we have a foreign field multiplication custom gate in Kimchi. But to do the elliptic curve operations required for ECDSA, we need a lot of other custom gates. So this diagram gives you kind of a pictorial representation of some of the metrics of these new custom gates. So foreign field multiplication, this is taking up 2 rows, and it's using one 12-bit lookup that's represented as the dark blue flowered tile. Then we have a range check, a foreign field addition custom gate, which doesn't use any lookups, and it's only a single row. And then to do the range checks, we kept referring to a multi-range check. And the multi-range check is what you see at the bottom of this figure. It's 3 range checks, and each of those is range checking 88-bit values. And this requires 4 rows to do it in Kimchi. So this gives us the gates, but on top of the gates, we have more work to do, and that is to build out the elliptic curve algorithms. So group addition and group doubling that you heard about at the beginning of the talk. So to give you an idea of the kind of costs of these things, group addition is taking 3 multiplications, 12 additions, and 12 multi-range checks for a total of 72 rows per addition. Doubling is taking 4 multiplications, 14 additions, and 16 multi-range checks for a total of 94 rows per.
Yeah, so as you can see, most of the complexity comes from the multi-range checks, and that takes most of the rows. So we're thinking about ways to optimize this. So if you have ideas, we will be open to discuss, because we want to reduce this number of rows. This is just an unoptimized version, but we're working on it. So yeah, feel free to reach out to us.
Yeah, so there we have another version. It's experimental that requires fewer multi-range checks. There's also been some interesting work published, casting out primes that we've been looking into. So this is a work in progress, but we already have implemented all the gates, and we're working on the gadgets, and then eventually building out ECDSA and Ketchak. So yeah, thank you for listening, and we're really happy to answer questions.
Thank you both for this great talk. I believe we now have a break. Am I right? All right. So we'll be taking a half-hour break, and then we meet you back here, in half an hour for the next talk, which is a guide to teaching zero-knowledge cryptography with Thor.
have it here, don't we? And do we have slides? What's up? So more slides. Oh, look, slides may or may not appear.
A volume amplifier has appeared. Test. Hello.
And then, where are... There it is. All right. I see people kind of trickling in slowly, but I guess just to kind of keep time, let's start with the next set of talks. So right now we're going to have Thor learn us how to teach some cryptography, which I'm actually very, very curious about. Thor has been working on a project which attempts to do this, and I believe it's called Hashcloak, right? Uncloak, sorry. Uncloak is the OG, in which case I think he knows a little bit about this. So welcome, Thor.
And I'm looking forward to Guillermo's later talk about how he reduces it all to linear algebra. So.
Me too. Okay, we got a clicker? Yeah, got a clicker.
Yeah, so welcome. So I'm Thor. For the last several months, I've been working on specifically a course teaching cryptography and zero-knowledge cryptography to an audience of developers who are sort of looking to do more in ZK development or understand cryptography at a sort of more general level. So in this talk, we're going to sort of take a bit of a high level, but we're going to try to break down sort of the fundamentals of what ZK primitives are built on, take a look at some of the definitions, try to make them approachable, and hopefully you'll leave this talk with a sort of better sense of how ZK is sort of constructed from a high level, and maybe some learning approaches to thinking about zero knowledge as a sort of topic area. So I am Cryptograthor on Twitter, and the project is Uncloak, and we've been running open courses through our Discord server and posting weekly to our YouTube channel. So if you'd like to find those communities, you can approach me after the talk. And yeah, let's get started. Button. Yeah, so who's this talk for? Well, this talk is basically for, I think, people who would like to develop ZK circuits, who would like to understand ZK circuit programming maybe a little bit better. Educators like myself, since I think there's a sort of large gap of sort of new paradigms to understand. So ZK is a fundamentally different sort of set of primitives than we're usually exposed to as programmers. And it's for the too embarrassed to ask. And I want to really thank Guillermo for being both embarrassed and asking anyway. So hopefully we'll be able to clear up some stuff. And it's for the guy at the party who thinks that ZK is pretty neat but doesn't know how to explain it to everyone else at the party. So goal. You want to be the guy on the left. Yeah, left. That's the one. And hopefully we'll get you there. Now, for the starter example, I think that you've probably all seen the starter examples in ZK before, but it's okay to kind of wander back through them and use them for context setting. So in this sort of basic sort of example of how we want to start thinking about zero knowledge when we're thinking about this, is we want to think about the three definitions of zero knowledge, which are completeness, soundness, and zero knowledge, all of which are fairly well demonstrated by the color blindness example. And so as I'm sure at least many of you are familiar, the color blindness example is the prover, Bob, says that he sees color, and Alice says, no, there is no color. There will be no color. Color does not exist, and I need you to prove this to me. So the prover says, yeah, I see color. So Alice says, okay, here are two balls that look exactly the same, precisely the same, and the prover says, okay, yeah, I think I see a difference. And so he says, no, you didn't switch them. And so they go, okay, prove it. And he says, no, you didn't switch them. She does it again. And they do this 80 more times. And every time Bob gets it correctly, of course, Alice says, well, if he was just guessing, there was only a 50% chance, but if he does it 80 times, then he has to get basically 2 to the negative 80 chance of being lying. So obviously, we get a pretty good sort of sense that Bob is now a very, very good guesser or is probably correct that colors exist. And so Alice might be forced to say, okay, color might be real, grr. And so to go back to these definitions, we have some sense that ZK is the synthesis of these three properties. We have completeness, soundness, and zero knowledge. And so when we're thinking about the context of ZK circuits, we're also going to run into these three properties, where we want to convince the verifier that I know some program and I've computed some program, just as Bob in this context has proven that color exists to Alice. And we are going to say, come to circuits with this same paradigm. So in the context of these definitions, just to sort of expand on them, ZK is the synthesis, or zero knowledge proofs are the synthesis of these three primitives, or these three definitions. Completeness is that Alice is convinced by an honest prover that if Bob actually does see color, then Alice is convinced that color exists and that Bob can tell the difference. Bob can't cheat and still convince Alice. So soundness is that if Bob is lying about the existence of color, he can't obviously convince Alice, except with very small probability. And finally, the ZK property is that Alice doesn't really learn anything except the thing that Bob wants to reveal. And the ZK property is sort of the hardest to explain the sort of technical definition of, because it involves terms like a simulator. But the core of the idea is effectively that Alice learns nothing. And so this is sort of like a good example because all three of these properties are very clearly depicted. With the Waldo example or the cave example, they can be a little bit harder, I think, to get out. So next we're going to move to something slightly more mathematical. We're going to move to Schnorr's sigma protocol for proof of knowledge of exponent. And in this example, I sort of want to demonstrate a more actually applicable zero knowledge proof than I see color. And we're going to say that Bob knows the exponent in a discrete log. So, as before, Bob is going to claim to know something, this exponent x in the discrete log problem. And this is actually a fairly fundamental protocol that gets used in things like polynomial commitment schemes. In fact, we can take any sigma protocol and turn it into a convenient polynomial commitment scheme. But if you don't know the word polynomial commitment scheme, that's okay. The sort of core thing to focus on is that we can take this slightly more mathematically involved example and still understand the basic premise that zero knowledge, completeness, and soundness are preserved by this new protocol. And then we can apply that to the context of circuits, which we'll do next. So in this context, Bob says, I know x in some public key, capital X equals g to the x. And Alice says, as before, nah. And so next up, Bob says, well, I'm going to have to think really hard about how to demonstrate that I know x. But he might come up with Schnorr's sigma protocol. And if you've seen a Schnorr signature before, this will look actually fairly similar because the protocol is basically just Bob sends a Schnorr signature that proves that he knows the private key. But if you don't know Schnorr signatures, it's really quite simple. Bob throws some randomness at Alice. Alice throws some randomness back. And then Bob takes the randomness and smashes it all together in the element z, where Alice can't peel the secret key back out of z, because the randomness that Bob chose lives behind a shield. And so it lives behind this commitment, where we generally think the discrete log is a fairly useful thing, because it lets us say, force Bob to select R without revealing what R is, and then get Alice's inputs back and say, okay, well, Alice can verify that Bob is bound to this element, and Alice can verify that z equals a plus x, or ax plus r, inside of the exponent. But Alice never gets the secret private key out. So I'll leave this on the screen for just a couple more seconds before I continue nattering. But the sort of core idea in this protocol is interactivity. And we actually use this core idea of interactivity in proofs, despite the fact that we don't actually use interactive proofs in practice. We use non-interactive proofs. And the sort of way we do this is that most interactive proofs look basically like this, where Alice chooses some random element, A. And if we can say, if we want to enter the sort of paradigm in which non-interactive proofs are constructed from interactive proofs, the verifier is basically just an abstraction that we use. In fact, we can say, if Bob can say, generate some randomness from a public source, say a hash function, where Bob gets to choose the initial seed, then we can sort of say Alice is a convenient abstraction, but at the end of the day, Bob is just going to treat her as this source of randomness that we can then swap out with a hash function, or a random oracle in more cryptographic slang. So the sort of core idea here that I wanted to communicate is two things. First, that we have like this idea of interactive proofs that we can render into non-interactive proofs by treating Alice as just a source of randomness that we can then swap out with a hash function. And then second, that the way that we use hidings in the exponent is sort of something that we can then expand upon in commitment schemes, which we'll get to in a little bit. So back to the definitions. So when we talked about the definitions for the color protocol, we introduced these three terms that are the sort of core sense of what a zero-knowledge proof is. We have this sense of completeness, that Alice is convinced by an honest prover, and if Bob does indeed know the exponent x, then he can indeed compute ax plus r. And so a convincing prover satisfies completeness in this context. That soundness is satisfied, that Bob can't cheat. If Bob does not know x, then with only very small probability will he be able to convince Alice that these exponents are aligned, because he'll just be guessing at values of x. And then finally, zk. Alice would need to break discrete log to actually obtain information about the secret key x. And so these are, again, useful things to keep in mind when thinking about what we're actually trying to achieve when we're writing these zk circuits. And so it is now circuit time. And Boolean computation is the thing that we're all kind of used to working with when we think about, okay, I want to compute a program. Now, Boolean computation is not what cryptographers like. We like fields, finite fields to be quite precise. We don't like infinite fields, and we certainly don't like floating point arithmetic. But we love fields that we can do multiplication and addition over and never have to think about a Boolean operation like an OR or an AND gate. And conveniently for us, there is a way for us to pretend that George Boole never existed. I think his name is George, I could be wrong there. That Boole never existed, and that in fact we can just treat everything as an addition and a multiplication operation, right? So the way we sort of do that is that we say, okay, well, if we take the bits, B0 and B1, and we can just say, well, and is just the multiplication of these bitwise elements. That's convenient. And OR is just the addition of two bit elements minus their multiplication. So we get this very like, okay, yeah, they're perfectly equivalent. And the answer to the question, can we translate Boolean logic to arithmetic, is yes. And the etch of Alan Turing here saying nice is a gesture to the fact that with Boolean arithmetic we get a Turing complete machine, but since we have arithmetic that is equivalent to our Boolean logic, we also have a Turing complete machine that we can do inside of just arithmetic over a finite field by doing this simple translation. Now, the next thing we might like to do, and this is sort of trying to gesture at the direction of what are we doing when we write a program. And don't take notes on this assembly, because I kind of scribbled it out and made it up. But when we write our program in a high-level language, we need to say, let's do some memory operations, let's load some value from memory into a register. Let's do some operations over those registers, maybe bitwise operations, XORs, ORs, ANDs, NANDs, whatever. Maybe some addition or whatever. We're going to add registers to constant values or other registers. And the way that our high-level program is going to get translated is eventually going to be into some assembly-like instructions, right? And so in our previous example, like the goal was to sort of say, well, if we have these equivalents of addition and multiplication gates in OR and AND gates, well, then we can say, instead of translating these into Boolean logic, we can translate it into finite field arithmetic. And so now we're starting to see like the direction that circuit arithmetic is getting us towards, is that instead of translating everything into ORs and ANDs, or more precisely from the hardware level, everything is in fact a NAND gate, but that's somewhat a tangent. We're going to translate it all into a circuit, an arithmetic circuit. But there's an issue. And the issue is that if we have, say, an 8-register machine or some number of registers in the machine, for each register, or for each operation, there's going to be a new layer in our circuit. And for somewhat arcane reasons involving polynomials and multilinear evaluations that we will not get into, we really want a short depth circuit. So if we have O of n instructions, we're going to get O of n layers in our circuit. And that's kind of a bummer, because this basically means that if our prover wants to prove something, they need to hand an O of n operation check to the verifier. So when we actually write our circuits for ZK DSLs, we usually are writing either, we are doing basically exactly this. We say, well, let's write our assembly. If we're writing an assembly ZK circuit like CIRCOM or Miden assembly, or let's write a high-level program that gets compiled to some assembly, like NOR or RISC-Zero's high-level machines. We're going to translate that to assembly, and it's going to get translated to this not very, this kind of long circuit. But we don't want long dogs, we want short dogs. So we have one trick left in our arsenal when we talk about how can we do everything succinctly, because this is what we're trying to get to when we're talking about zero-knowledge proofs, is this premise of succinctness. And that trick in our arsenal is that we shove everything at the base layer. So if we have an honest prover, they are going to compute the intermediate values in our circuit. And in fact, we can shove a lot of those intermediate values just back onto the base level of our circuit. And this means that instead of getting a long circuit, like the one that we would have originally programmed, the circuit that is O of n in length, where n is the number of operations, the number of assembly instructions, we can get a short guy. And our short guy is going to be succinct to verify, because it might be only O of log n, or depending on our transformation, even O of constant time, if we do this transformation, moving everything onto the base layer. And what's sort of left here for us is that the things that were really simple for us to do were arithmetic operations like addition and multiplication. And I'm going to just briefly gesture at things that are not simple to do within the context of a circuit. The thing that is the least simple to do in the context of a circuit is memory accesses, because those are not arithmetic. They're not Boolean logic. And that's sort of where lookup tables enter in, if you've heard that term, like P lookup from Aztec. Where those sort of enter into the picture is that there are some operations that don't neatly translate into arithmetic operations like addition and multiplication. And so what we need to do there is we need to say, well, the prover needs to say, here is the ordered sequence of accesses in memory. When I store something into memory, it needs to be the same thing when I go load it later. And this actually could be an issue, because the prover could lie about, well, if I stored something into memory and I got to the end of my circuit and I really need this to be a 3, but in fact I cheated and this is 376, we need to bind the prover to the fact that this is in fact whatever it's supposed to be. So we use a Merkle tree, and that's sort of where the circuit arithmetic hash functions come in. We need to include in these witness values the W's that have moved onto the base layer. We need to commit to a Merkle tree inside of our new circuit down here. And this can be the source of like some additional height, right? Because our Merkle tree is going to be logarithmic in the total number of witnesses that we need to put in. And so our new circuit will be perhaps logarithmic in the new number of witnesses, but not linear in the total number of operations that we need to calculate. So this is a pretty significant improvement when we think about what our ZK circuit should actually be able to accomplish. But what we win is succinctness. And this sort of transformation here is basically that we can change our writing a circuit C of x equals y, where x values were these things on the left. We get C of x equals y, where y is some claimed output of the circuit on some unknown inputs x. And we can transform the circuit into a circuit satisfiability instance, where circuit satisfiability means in this context, the prover had claimed to have some value x, satisfying C of x equals y. Circuit satisfiability is a sort of different kind of circuit, where we just need to say, does there exist a vector w, such that this new circuit, which I might have been polite and labeled C prime for this convenience, does this new circuit that we use a transformation for have a satisfying additional vector w, such that the same thing is true after we perform our compilation step from C of x into C of xw. And so that's where we sort of do our transformation into R1CS, or do Planck-ish arithmetization schemes, where we need to satisfy this circuit satisfiability instance. And then we can compute the values for x and w, which is simply computing the original circuit C of x equals y. That gives us our values for w, because our w's are our intermediate values, plus some extra overhead for the I/O operations that I mentioned. And then finally, when we compute our proof pi, our proof pi is this sort of complicated step that I'm sort of eluding in this context, because that would be another 30-minute talk. But I will briefly gesture at it. The way we actually prove anything in the context of our circuit is that we need to say, well, the verifier is going to know y, but they aren't necessarily going to know the inputs x1 through xn. And we can do this operation row by row over the layers of our circuits in what is called the GKR protocol. We can take the GKR protocol and say, like, do this layer by layer evaluation of our circuits, relating the outputs at each layer to the outputs at the previous layer. And at the final layer, we need to have the verifier know something about the actual inputs, and that is where polynomial commitment schemes come in. So come back to my next talk, and we'll talk about the GKR protocol and polynomial commitment schemes. And then finally, we have the prover compute the proof pi, attesting to the knowledge of x and w satisfying this expression. And to go back to definitions, we have this model of completeness, soundness, and zero knowledge. Well, the prover would never be able to convince if the prover actually does this transformation, they will always know the intermediate values of the original circuit, the w's, will always be able to compute the transformation, will always be able to prove to the verifier that their circuit is satisfied. For soundness, a cheating prover would need to say, that circuit is too hard for me, I'm just going to come up with a bunch of w values, and the circuit satisfiability instance will be difficult for the cheating prover to abuse. And then finally, for zero knowledge, if the verifier is attempting to learn the values of the w's, the verifier would have to completely determine all of the values of the x's and reevaluate the circuit to obtain these. So we get completeness, succinctness, and zero knowledge for this circuit. And that's pretty much it. So thank you, everyone, for coming to my talk. And if
Cool, cool. We have about 5 minutes for questions. If anyone has questions for Thor.
I'll just dance while you think about your questions.
No one has any questions? No ideas? No notions? Constructions? Ah, there we go. All right, there's one. A brave soul indeed. Okay, and we have a runner, so.
Okay, so I have a bit of silly question. What exactly is W?
Was the question, sorry, could you repeat the question?
What is W in the...
What is W? So the W stands for the witness. So when we're talking about, looks like the slides are gone. The W is what we refer to as the witness. In our original circuit, when we say C of X equals Y, the X values are usually the thing that we're trying to not have to send entirely to the verifier because they can be very long. When we extend the circuit with this transformation from C of X equals Y to C of XW equals Y, the witness values are all of the intermediate values and potentially other things too. So if the circuit doesn't have a convenient way to, say, compute the inverse of some element, where we would have to do, say, the extended Euclidean algorithm to compute the witness inside the circuit, what we can do instead is we can say, include some values in the witness that weren't necessarily intermediate values, but are what are called advice values. So there are a couple of things that go in the witness. First is things that were intermediate values in the original circuit. Second is things that are advice values that are like maybe the inverse of some element, where instead of saying do the entire circuit computation of the inverse, we just check that that new element times the thing it's the inverse of is equal to 1. So that's a fairly easy optimization that we can do with advice values. And then finally, we need to have, like I mentioned, the lookup table elements need to have some proof that they are, in fact, the valid transcript of elements of the I/O operations. So those things all tend to live inside of the witness W. And if the prover has those things inside of his head, he has computed the original circuit and transformed it into this subsequent circuit where he has these new vectors of values that he can run through this new circuit that we create. And this new circuit will be low depth, so it will be efficient for the verifier to run their operation. The verifier's time is linear in the number of layers that there are in the circuit. So we want those values to be all living at the flat bottom and have a short circuit. And that's kind of what we get for this transformation. Did that help?
Yeah, and one more question. On one of the slides, you have like 2 circuits. And yeah, if you could show. Yeah, so this purple unlabeled, is this a sum or a multiplication or some other operation?
Is what, a sum or a multiplication?
Yeah, like you have these purple blocks that are not labeled.
Yeah.
And
so I didn't put things in this box because I was lazy, but ultimately I did put the equals 0 at the top. So for our circuit satisfiability gates, we're going to be saying, well, is the addition of, in this first left example, is the addition of x0 and x1 plus whatever we put in the witness 0 box, is that equal to 0? And if the outputs of everything is 0, then we have achieved our circuit satisfiability instance, where we are trying to find some inputs for W's that achieve this everything equals 0 argument.
Okay, thank you.
Yeah.
Cool. We have 1 more minute if anyone has any last questions. If not, well, thank you, Thor. Everyone give a round of applause. Okay. Aha. Yeah. There we go. All right. Very good. Cool. Oh, yeah, go for it. Sorry. Feel free to go on stage. What is the name of your talk, actually? Oh, adding reflections to the EVM with Axiom. Okay, well, I know your name, but yeah, that's fine.
Is there clocks?
There is not, but do you want time for questions? You have 30 minutes. Yeah, 5 minutes for questions. I can give you, so I can give you a 10-minute and a 5-minute. Okay. Yeah, so 5-minute would be 10. Can you give me a 15 minutes? You can give me 15. Awesome. 15 will be dead. Be weird. 50, that works. Great. Awesome. Yeah. All right. I'm gonna wait like 1 more minute. Just 10 minutes is too late. Yeah, it's game over. It's been done, you know. Have you been around Pages 5? Just yesterday, but I found slides. You're next. What's up? You're next. I think not this one, but like after the thing, it's like, oh yeah, it's like coming up quite soon, unfortunately.
Since this goes into lunch, I think right now is the switch, right? We should see if side stage is done.
Okay.
Then maybe we give you like just a few minutes to make sure there's not too many people moving.
Between each. So do we want to wait like?
I would like
2 minutes, 5
if
minutes.
that's cool for you. Do you want to?
Yeah, sure.
Start a tiny bit late on that.
Sounds great. Yeah.
Because like you have lunch right after, so it's not like.
Yeah, there's not like a hard cutoff. So I'm gonna do the follow-up. Yeah, exactly. It could be like a full-on stats lecture or something at the end of this.
I always go under. I'm worried about
Really?
Well, then this is good too if we go late.
Yeah, because then you can just kill it real time. But I'll give you 15. Yeah, 15 is fine.
Wow. Yeah, this is the ticket number. No, 526 people.
Holy fucking shit.
For me, that's crazy.
That's extremely impressive. I'm going to be around because we have a few minutes to go my way up. And then this here before it just rolls off elsewhere.
Hey, everybody, we're just taking a second to let people sort of switch stages, but we're going to start in about 2 minutes, I think. Yeah.
I don't know if I should I just like, you don't remember the name of your talk. Because like this thing is tiny. It's like really hard to read. Yeah, it's like lighting reflection of the EVM with Axiom is like, all right. Well. Hey, so welcome back. Next talk is by Yi, who will be telling us about how to add a reflection to the EVM using Axiom. Everyone, round of applause.
So today I wanted to talk about a new capability that ZK actually enables for blockchain computing. And that's something I want to term reflection. So before we get into what reflection actually is in a blockchain context, I want to review a little bit how humans actually access information about the chain. So the special property of blockchains is that all execution and state, at least at present, is transparent and publicly verifiable. And so as a normal user, you would typically access a blockchain by first finding an archive node, either one that you're running yourself or perhaps run by a service like Infura or Alchemy. Then you would sort of query this node for the historic on-chain state, and then you would view that in your eyeball. So in my language, archive nodes really are there to feed on-chain information to human eyeballs. And as the ecosystem has developed, users demand sort of increasingly more sophisticated ways to actually understand this information. So at the most basic level, you have a variety of archive nodes that provide answers to JSON RPC queries. You can choose Geth, Aragon, Nethermind, and soon you'll probably be able to choose Reth. But as users use more sophisticated on-chain applications, they actually want to understand what the raw data they're querying actually means. And so for that, you would turn to an indexer like Etherscan, the Graph, or Covalent. And we're now seeing a new wave of different ways to look at the chain that give very context-specific information. For example, there are wallets like Blowfish and Stello that will actually simulate a transaction you're about to run on top of the current state of the chain to see if you're actually getting hacked and going to lose all your NFTs. So the general trend here is for users to view the chain with more and more processing on top. Now, let's think about the situation of a smart contract viewing the state of Ethereum. There, it's quite different. If you go to an application like OpenSea and you try to identify which of the pieces of data on the page are actually accessible to the OpenSea smart contract, you'll find that there's exactly one number on a listing page that's accessible, namely the current owner of the relevant NFT. And this is a more general phenomenon. So there's all this historic information about past states, transactions, and receipts on the chain that's fundamentally unavailable to smart contracts. And that's not an arbitrary decision. There's a very good reason for this, which is that all validating full nodes need to have this type of information in random access in order to validate a transaction. So we really cannot force these nodes to have to keep historic information and still maintain the ability to run them on reasonable hardware. Secondly, even if we could access all this data, it's very difficult to process it in a blockchain VM. You know, as every smart contract developer knows, the EVM, or actually any blockchain VM, is pretty limited. There are certain types of operations that are made artificially cheap via precompiles, but there's a whole world of other interesting operations that for whatever reason are not included as precompiles and become pretty difficult to use in your application. Again, this isn't just arbitrary choice, this is to maintain the consensus stability of Ethereum, or in principle, any other blockchain. So the situation looks pretty grim for blockchain computers. They're pretty limited on historic access and also compute. But they actually have a special weapon to combat this. So unlike most other types of computing, blockchains have commitments from the current block to all previous blocks, and thereby all information contained in all previous blocks. So if you have access to a current or recent block header of Ethereum, in principle, you have some type of cryptographic access to the entire history of Ethereum. And so to sum this up, blockchains have this special property of cryptographic memory. And what does this mean? Well, it means that we can actually allow blockchains to reflect by accessing this memory. In Ethereum, this would work by first taking the current block, decommitting a pretty long chain of blocks back to a past block containing the information that you want to access, and then providing some Merkle-Patricia trie proofs to access a specific piece of information about state, transactions, or receipts. And I like to think of this as kind of a baby version of reflection because it's quite expensive to access each piece of information. Maybe if you want to find data about one storage slot in the past, that's okay. But if you want to scale this, it's going to be prohibitively expensive. So what we're doing at Axiom is adding reflection to the EVM at scale using ZK. We wrap that whole process of providing a Merkle-Patricia trie proof and a Keccak chain of block headers in ZK. And from this perspective, the verification of all of these proofs is compressed using the succinctness property. And that allows us to think a lot bigger and address much more powerful statements using reflection. So we've packaged this into something we're calling a ZK coprocessor. And what we're building is something to allow smart contracts to trustlessly access and process all types of this on-chain data. So let me tell you how that works from a developer perspective. When you query into Axiom, we divide your query into some historic on-chain reads and compute on top of that. So I already told you that the on-chain reads are reaching in to the committed memory of the chain. And then on the compute side, we allow developers to apply different types of primitives on top of the data that they access. So this ranges from pretty pedestrian things like basic analytics to kind of wackier things like cryptography or machine learning. And finally, in parallel, we're generating zero-knowledge proofs that all of this was done in a correct fashion. And we verify those proofs on-chain. The end result of this is a kind of different smart contract computing paradigm. You have a smart contract. You send us a query to a coprocessor. This picture is a picture of an actual math coprocessor from the 1990s. You'll notice it's made by Math Co. So this is kind of a throwback. But in our coprocessor, we'll do the reads and the compute. And finally, we put the verified result on-chain for a smart contract to use. And so we think this is a new delegated data read and compute paradigm for smart contract applications. So let me talk a little bit about how we specifically achieve this. So there's essentially two tasks. The first is to actually be able to access historic block hashes at some scale. Doing this from scratch for each query would be pretty expensive, even in ZK. So we maintain a smart contract that caches a Merkleized form of all historic block hashes on Ethereum. The idea here is that the EVM, for whatever reason, allows you to access the last 256 block hashes, and we systematically reverse that Keccak header chain to cache every 1,024 block hashes. The end result is that our smart contract, which you can view on mainnet today, actually contains a verified Merkle root of all past block hashes from Genesis. The day we did that, we were the #2 gas consumer on Ethereum, which is a rather dubious distinction I hope to not repeat. Now, when we actually fulfill a query about specific historic information into Axiom, we can verify proofs against this cache of block hashes. So all we need to do for single queries is Merkle-Patricia trie proofs that are verified in our smart contract against these Merkle roots. So the resulting ZK-based reflection type system differs from standard smart contract computing in some pretty critical ways. So our view is that smart contracts are generally powered by consensus. What that means is that they're very good at providing synchronous access to a pretty limited amount of on-chain state. On the other hand, they don't give you any access to historic state, and your compute is pretty carefully metered. On the other hand, if you use a zero-knowledge powered reflection type system, you don't get any access to the current state, since it's a fundamentally asynchronous operation. In return, though, you can actually do unlimited compute on historic data, so long as you're willing to pay for the proving, and you get async access to the entire chain history. So we think we're presenting a different type of trade-off for developers here. All right, so that was a lot of very conceptual talk about new primitives. What can we actually do with this? So we think of this in stages, and I've drawn a rough plot of the amount of data read for an application on the horizontal axis and the amount of compute that's required for an application on the vertical axis. The first class of applications are things that are generally possible in the EVM today, whether by doing single storage proofs directly or by adding caching to your application. So this would be things like reading historic consensus level randomness from the block header, verifying your account age, or reading a historic Uniswap spot price or TWAP price. If we scale up, though, to things which require much more data complexity and much more compute complexity, then we get more novel applications which really are not accessible in the EVM today. This would be things like adjusting parameters of your DeFi protocol by applying some basic machine learning algorithms to the historic performance, rewarding your protocol's participants by doing a trustless evaluation of their on-chain track record, or actually computing an on-chain credit score in a trustless fashion instead of relying on a centralized provider to put that number on-chain. And we think that these applications, because the scale of the data read and the compute is so much beyond what you can think of on-chain today, they're actually hard to think of, and we think as developers try to use this primitive of reflection more, they'll find new ones. One thing I want to note on this basically made-up graph of my estimate of the complexity is that the data complexity of an application is actually intrinsically quite tied to its compute complexity. Essentially, if we offer you access to a huge number of data points, then it's very hard to use that without a commensurate level of compute. Similarly, if you're going for an application that does very sophisticated compute, for example, some type of neural network inference, you very likely will have to access quite a bit of data in a trustless fashion to even get the input. So at Axiom, we're going after applications in this top right corner. So if you have any ideas that aren't on this list, definitely come talk to me after the talk. Now, for the rest of this talk, I want to talk a little bit about what would be next if we finish this entire 2D plot. And what I think could be next is something that I want to call introspection. So we've talked about reflection as the blockchain looking at itself. And, well, what's introspection? For a human psychology, that's sort of thinking about your actual mind and thinking about what you might do in some hypothetical situations. And so for a blockchain, I will take introspection to mean doing simulation of what hypothetical activities could happen if you were to do different transactions on-chain. Okay, so this will require doing much more access as well as much more compute than anything that I've written on the slide. And in this case, we think that it will require, first of all, something like a ZK EVM, and can allow application developers to make much richer statements about blockchain activities. Just to list a few examples of things that are kind of pie in the sky today, but may be possible down the road, you might be able to test whether a hypothetical property would happen to your protocol if a user were to execute some type of transaction. In the context of insurance, we think the highest possible standard for whether you should be entitled to a claim for insurance is when you try to withdraw your money from a, let's say, lending protocol, if you can prove that you are not able to withdraw, then you're certainly entitled to a claim. On the other hand, if you are able to withdraw, perhaps you shouldn't get paid. Similarly, if you're a white hat hacker, you want to get paid a bug bounty, but maybe you don't trust the team to actually pay you. So there, we think the highest standard would be to prove that you have knowledge of exploiting transactions, which would allow you to violate certain protocol level guarantees. If we go more to the infrastructure level, you'll sort of see that this proof of exploit is actually quite similar to the notion of a ZK-based fraud or fault proof. In an optimistic rollup, a fraud proof is nothing more than a demonstration that the state that is arrived to on-chain, or that is claimed on-chain by a sequencer, is actually not the correct application of a sequence of transactions. And finally, in the domain of MEV and block building, we think that doing hypothetical execution of transactions that are being submitted in a mempool to be put in a block could be a way to actually provide accountability or some sort of performance evaluation for block builders. For example, you might be able to prove that of all the transactions in some set, you actually built some block which is good by some type of arbitrary performance metric. So in general, I think we're very early about thinking about the implications of introspection for applications in the space. And we're pretty excited to see what developers can come up with once this sort of idea is even possible. So I want to end by coming back to the beginning of the talk and drawing an analogy with what's happening in the more user-facing side of crypto on data access. So we started with sort of off-chain access to basic primitives via an archive node. And things in that area of the space have really moved to beyond that, to tracing archive nodes, to full transaction simulation, and all sorts of very fancy indexers that are coming to market now. And at Axiom, we're bringing the very basic blocking and tackling applications of on-chain reflection via co-processing for smart contract applications. And as things develop, we're excited to explore the implications of that for on-chain introspection for smart contracts. So just to finish, we're hiring pretty aggressively. So we have a bunch of job listings for both engineering, ZK, as well as developer relations and BD roles at our job site. And we'd love to have you guys join us in building the foundations necessary for smart contract developers to build expressive and powerful trust-minimized applications on-chain. So I think there's quite a bit of time for questions. So yeah.
As you said, if anyone has any questions, please feel free. Oh, you got one. Yes, she is coming to get.
Thank you for the talk. You had great slides in there. Could you say a few more words about the architecture? Because it would seem like everything happens on chain, but I guess there are things that happen off chain too, right?
Yeah, definitely. So there are two pieces to the architecture. The first is that we have to keep our cache of historic block hashes. Well, first we have to initialize it. So to do that, we provide zero-knowledge proofs of the valid Ketchak chain of block headers in groups of 1024. So we do that historically, and then we also have to do that on an ongoing basis to maintain this cache. So actually, you can look on mainnet today, we're running a zero-knowledge proof every 30 minutes to keep this updated. So for the historic access, we did some tricks to actually do a batch import in groups of about 128,000 at a time. Now, the second thing is for the query fulfillment on-chain. So let me find the right diagram. So what happens here is that a smart contract will make a query into our off-chain system. We'll pull the data and run the compute to find the result of that query. And in parallel, we'll generate a zero-knowledge proof that we did all those actions in a valid fashion. And because we've built this cache of block headers, we're actually able to verify that proof on-chain and then check that the appropriate block hash information matches the verified block headers we already have in our on-chain contract. And so in this way, we're offering essentially delegated data reads and compute to our off-chain coprocessor.
Thank you.
Anybody else have any questions?
Thank you. I have the impression that this system could have huge implications for MEV and MEV simulation. Is this true, or is this only an impression?
It sounds like you know much more about MEV than we do. So first of all, we'd love to talk to you about that. One area where I think it could have some implications is that we're able to access, for example, the ordering of transactions in an actual block. And I've been told at least that, first of all, in MEV, this is what people care about, but also that this might have implications on driving some accountability for various systems in MEV. So I'd love to talk further about that.
Thank you.
That's right here.
Hi. And I would like to know what type of proving system are you using? I mean, which system, or are you using recursion, or I don't know, because it seems that performance is really important here.
Yeah, definitely. So we're using Halo 2 with the KZG backend. So we're using the same fork of Halo 2 as PSC and Scroll are using for the ZK EVM. And definitely we're proving pretty big statements. So we make pretty heavy use of non-native aggregation and recursion.
Okay, thank you so much.
And if you want to see the gory details, we actually open sourced all of our code, so you can check it out on our GitHub.
Could I bring my own data? Meaning, at some point in history, the hash of my data is included in the chain. Could I bring that data and bring that into the proof?
Yeah, so I think the question is, like, if you have some committed data that's sort of hidden, can you somehow provide it as a witness?
Yeah.
That's, in our system today, you would have to do that in smart contract land, but we are exploring ways to allow not just committed data, but just arbitrary private inputs that users provide. Another example where that's interesting is if that data is a user-provided signature.
Yep, cool.
Any last burning questions? Ideas, notions, comments, constructions? No? Well, one more thank you to Yi. This was great. Thank you so much. And now we'll turn it over to Anna to say something fascinating.
Fascinating, fascinating. Thank you, Yi, for that great talk. Okay, so this is our lunch break. I just wanted to point out two things. One is, I think we've run out of all the ZK9 swag. I don't know, sadly. There is, so you might have noticed there is some ZK podcast swag, but we're selling it. And I don't know if that's allowed in this community, but anyway, but it's on the other side. I just want to make sure you know about that if you are interested in it. I also want to let you know about the after party. So we've sent an email out about this. We have an after party at a place called Suspenso. Please look it up. Look for that email. We've given you all the instructions. To get in, you need one of these two wristbands. So if you have it, you're set. But just to get that on your radar. And I think we're starting at around 8:30, so you should probably go eat and then go there. It's not gonna be a full meal, but it will be a party. It's the first time we do that. So anyway, yeah, so I think have a good, now we can just break and we'll be back here in 1 hour. Is this correct? Yes, with the lightning talks. Whoa.
Oh no. Oh God, help us all. Alrighty.
That means I'm up for these two, and then you do those two.
Yeah.
So, hello everyone. We are going to start our afternoon program with 4 lightning talks. So if you want to take your seat, we could get started. Just before we do that, I want to tell anyone who doesn't know this, we are doing an after party to this event at 9 p.m. with our partner Alio. If you have a wristband, you can get in, and I assume all of you do. So don't cut them off if you want to come. And it's at 9 p.m., so you're meant to kind of go eat and then go there. Cool. So let's kick off the afternoon here on the main stage. So we have 4 lightning talks. Each one we have like 15-minute blocks. I think we're aiming for kind of like 10-minute talk, 5-minute Q&A if there's time. But no pressure. And our first speaker is also the co-host of this stage, but I'm going to introduce him. So Guillermo is going to come up and share a little bit about linear algebra and zero knowledge. Welcome, Guillermo, back to the stage as a speaker this time.
And the speaker this time, for better or worse. I guess we'll find out next. Yeah, cool. So this is work done jointly with Alex, who's actually right here. So if there's any mistakes on the slide, please direct them just straight at him, not me. But I really do hope you catch some mistakes, because I'm sure they will exist, and I would prefer to not have them. All right, great. So with that, let's get started. So very quickly, what we're going to do in about 10 minutes is we're going to do a hilarious amount of things, which is namely generalize a number of things that we know in ZK to just way more broad situations. So specifically, ZK depends a lot on the fact that polynomials have this very nice structure. They have this property that if you test a specific point of a polynomial with high probability, if it's 0, then with high probability the coefficients of the polynomial must have been 0, blah, blah, blah. We're going to show that actually none of those results depend on polynomials at all. They're actually properties of something called error-correcting codes. And the idea is to do this with something called, hopefully, good notation, linear algebra, and just a tiny, 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 salt-based sprinkle of ECCs. Okay. So for anyone who is not well aware of linear algebra is very, very nice over the real and complex numbers. Everything is lovely, your intuition makes sense, the sun is shining, the ponies are out. Unfortunately, linear algebra over finite fields is an eldritch monster with a lying smiley face in the front that says, yes, sure, you can do linear algebra, come in. But it will eat you extremely quickly, so beware. Okay, so unfortunately, in order to get everything in 10 minutes, you have to eat a few vegetables before we can get to the dessert. So let's get started on that. So what we're going to say is we have probabilistic implications. This is kind of a weird thing that only exists in data science, and I'm just going to pretend it exists everywhere else. What does it mean? It means, so we say PR, which is a statement that depends on some randomness R, implies another statement, QR, that depends on randomness QR prime, with high probability if that implication is true or is false with probability at most P. So if P is very small, it means that the implication is almost always true, right? So there's a number of interesting downstream consequences. This is just, this is what people call soundness error, but here is like a calculus for these things, which is you can chain implications together. There's a simple variation of this. It says if P implies Q with probability P, and Q implies T with probability P prime, then indeed, kind of as one would expect, you can chain those things and say P implies T, but the probability here is slightly larger. It's P plus P prime. So as this is kind of an extension of the normal notion of implication that we all know and love, which is that if a thing implies another thing and that thing implies something else, then the original and the last thing are implications of each other. So many other things follow. This is kind of going to be the only one that's important, but we have to carry around this extra error term. Okay, so what is an error-correcting code? I'm going to just put it out there. A linear code is just a matrix, and the matrix has m columns and n rows, m rows and n columns. We say we encode a vector, x, into a much larger code word, g of x, and here's my shitty drawing of an encoding, which says you take an x and then you blow it up to some larger message, or in this case code word, g of x. Okay, the trivial code, all it says is here's my encoding, you give me a message, congratulations, you get the message back. That is a perfectly reasonable encoding under our framework, although it won't be that interesting, but the probably more common encoding in ZK is the Reed-Solomon code. What it is it says, if there's anything you get out of this talk is forget all of the linear algebra, What we're going to do is we're going to say x is the coefficients of some polynomial of degree n minus 1. G of x means you're going to encode that polynomial, or encode that message into a polynomial, and gx of r says evaluate that polynomial at a point r. That's it. So this is the one, if you ever get lost in the sauce, like I would recommend just go back to this one definition, and this will kind of set you back on the right track. But this is true for arbitrary linear codes, and there's many of them that are not just Reed-Solomon codes. Okay, we're going to use exactly one definition from coding theory, and that is the distance d of a code. This is d of a code is a very weird but actually useful thing that says I'm going to encode all possible messages. So there's a list of messages that are all possible messages, encode all of them, and then find the one that has the minimum number of non-zero elements. That number is going to be called the distance. So the idea is, if you think about it, if you have a vector and it has some error, right, the encoding, if the distance is large, will actually expand that error into a bunch of other places in the encoded vector. And this is kind of, going to be useful because if you have some error somewhere, you want to have high probability of catching it by just checking the output or a very small portion of the output. And that's the point of an error correcting code. Okay, so the trivial code is just an example, has distance 1. Of course, any non-zero vector will have distance that's not 0 because it needs to have at least one non-zero element. But it's going to have distance exactly 1 because there's, take a vector with only a single 1 and zeros everywhere else. The Reed-Solomon code actually has this funny little distance, which is, you can think about it as a message with length n can be encoded into a degree n minus 1 polynomial, right? So it has at most n minus 1 zeros, n minus 1 roots. So because of that, if we think of the set of all possible evaluations of the polynomial, it's going to be 0 in at most the field, which is all possible evaluations, minus the places where it can be 0. So it's going to be non-zero in all of those spots. So it's potentially a very, very large number. Okay, we've eaten all the vegetables. Let's get to some interesting results very quickly. We're going to do a bunch of ZK in 5 minutes. So the usual zero check. What are we doing? All right, take a vector, x, encode it, and then check a random symbol from the encoding. Check if it's equal to 0. If that's equal to 0, then with high probability, the original thing must have been 0. Why? Well, that's kind of the definition of distance, right? The definition of distance says anything, whatever it is going to have very large distance, d, right? And with high probability, if that thing is non-zero, I must have, if d is, very, very large relative to the size, with high probability, I'll hit one of those non-zero entries. So for a Reed-Solomon code, this is exactly the same as the one-dimensional Schwarz-Zippel lemma, if one wants to think about it. But the point is you get exactly the same bound that you would expect, which is what's the probability that a non-zero polynomial evaluates 0 at a point, at a randomly chosen point? Well, it's the degree divided by the field size. So a generalized zero check says, okay, well, I don't want to check if a single vector is 0. I want to check if a bunch of vectors are 0. What are we going to do? We're going to smash all the vectors together in this particular way. We're going to choose a random row of G. I'll give a diagram for this in about a second. Choose a random row of G, and then use that as the coefficients for a linear combination of these zeros, of these vectors, sorry. So you have y1 through yn. You want to check if all of them are 0. I don't want to check if each individual one is 0. What we're going to do is we're going to smash them all together, right, and then check if that resulting vector is 0. To do that, again, we pick a random row. We use that as the linear coefficients. We smash them all together, and then we check that that resulting vector is 0. And indeed, if that resulting vector is 0, then with high probability, the original vectors must have been 0 in the first place. In fact, the probability bound is exactly the same as the original one for the original test. And for a Reed-Solomon code, this is exactly the same thing, the degree of a polynomial, or the length of the message minus 1, divided by the field size. Okay, the picture, of course, is we have m rows. We choose a random row uniformly at random, and we use that row as the coefficients of the linear combination of y1, y2, all the way to yn, and then check if that's equal to 0. The high-level proof is kind of silly, but it says, look, okay, I'm going to take a linear combination of a bunch of things that are non-zero, then with high probability, that the places that are non-zero are going to be kept in the final vector. That's, again, just from the definition of distance. Okay. Now, you could be like, haha, I'm very smart. What am I going to do? Here's a bunch of math. I have a thing that lets me check if a single vector is 0 by checking a random element, right? I also have a thing that says I can take a bunch of vectors and smash them all together into one vector and check if that thing is 0. So why don't we just put the two things together, right? I'm going to take a list of vectors. I'm going to smash them together into one vector, and then I'm going to encode that vector and then check if that element is 0,
right? All we're doing is we're kind of concatenating the two previous things that we talked about into just one single protocol. And indeed, what you find is, of course, by the fact that we can have these very nice implications with additive soundness error, we get the probability of this final check, kind of written out in math, not super important, is actually at most, p plus p prime. And it turns out, actually, if you guys are familiar with this, this is exactly the Schwarz-Zippel lemma. And it turns out that this actually shows that it's not tight, and it's generalized also to arbitrary linear codes. So it does not depend on the fact, Schwarz-Zippel does not depend on the fact that polynomials are in the mix. It's actually true for any general linear code. Okay. Finally, we'll say one interesting thing that I don't actually think is known that says, let's say I want to check that a list of vectors each belong into some subspace V. How can I do that? Well, sure, I can check that each individual vector belongs in subspace V. Instead, I can do the same trick that I did before, which is I pick a random row of the big code matrix. I use that as the weights for a vector combination. And then afterwards, I check that the resulting single vector is in the subspace V. And that indeed, high probability, will imply that the original vectors must have each been in the original subspace. For a Reed-Solomon code, again, same probability bounds. Okay. Finally, we're going to so you might say, okay, the probability bounds are all the same. That's kind of silly. Maybe we know a few of these things, maybe we don't. Let's some quick sparsity results. And these are going to be very similar to those of Ligero, very similar to those of Fry and Sperrit. So the sparse zero check says, okay, I want to check if a vector is sparse. There's many ways of doing that. Of course, I can go through every entry of the vector x and then check if the number of non-zero entries actually matches the bound that I want. Instead, I can just say, okay, I'm going to randomly sample a bunch of elements from X and check if all of them are 0. If all of them are 0, then with high probability, you probably don't have that many things that are not 0. And indeed, the bound is kind of exponential in the number of tests that you have. So S here is a uniformly randomly chosen subset of the entries that you are checking, and P here is the probability, which is exponentially decreasing in how many indices you test. So this is Ligero Light, which says, okay, I not want to check if one vector is in this is sparse. I want to check if a bunch of vectors are individually sparse. And lo and behold, the same trick happens to hold. You take a random row, you sum all of the vectors using those weights, and then afterwards you check if that one single vector is sparse. And with high probability, that will imply that the original vectors each must have individually been sparse. This is, again, kind of weird, right? The same trick is popping up over and over and over again. We have it all in the same notation, all in exactly the same way. And indeed, actually, you can show that this implies the original claim. And finally, we have this generalized Ligero. So this is almost but not fully proven. But the point is, a classic thing you want to do is you want to check that a bunch of things are close to a certain vector space. One way of doing that, again, is checking that every individual element is close to a vector space. But that's a bad thing to do because that requires a lot of work. So instead, you can just take a bunch of random linear combination of all of those things, and then check that the resulting linear combination, which is a single vector, is close to the vector space itself. That will, again, hopefully, with high probability, imply that each of the individual elements must have been close to the vector space in the first place. There's a condition on how far, how sparse your thing can be, but that, we'll punt it for later. The point is, actually, this part of this proof is still open, and for technical reasons, I'm happy to get into later, so please come and chat with us if this is interesting. Anyways, so we just did 7 checks in a little bit over 10 minutes, very fast, so hopefully everyone got it. There's going to be a quiz at the end of this. Many of the generalizations here, but the point here is all of these things are kind of straightforward, right? You write down the math, and everything looks kind of exactly identical, and you're just doing the same thing over and over and over again in a bunch of different things, right, in exactly one framework. So we can replace the point here, second point here, is that we can replace Reed-Solomon codes with general linear codes, and we kind of don't really lose anything. So there might be codes that are more or less computationally efficient that might be interesting to use in certain parts of proofs, depending on what's needed. And finally, and most importantly, we can understand many of the systems or many of these individual proofs that we all end up dealing with all the time in just one single framework. So with that, the paper will hopefully come soon, although I make no promises. Okay, I make a few promises, but with high probability promises. And then I just want to say thank you for listening, and thank you to Aki for actually some of the interesting conversations. Cheers.
Should we take one question? I think I had you start does anyone have a question? on this? Yeah.
I think everyone understood
Maybe,
everything.
Everyone understood, right?
100%, right? Great, okay. Oh, you got one.
Okay. Oh, just 1 second. I think we're going to bring you a mic.
With regards to this, codes themselves, do they have to be MDS or it can
Nope.
be any linear?
Any code. Okay. I didn't even define MDS, actually, and that wasn't just out of spite. That was actually just, that was actually not required. Cool. That's a great question.
Thanks.
Cool. Okay. Fantastic.
Thank you.
I don't think we really have time for another one anyway. So thank you so much, Guillermo. I'm doing this. So next up, I'm looking for Marcus. That's you. Great. So Marcus is going to be telling us about Poseidon 2, a faster version of the Poseidon hash function. We actually learned about Poseidon 2 also at ZK Hack because some folks implemented it. So yeah, take it away.
So yeah, let's start. So first, this is joint work together with Dimitri and Lorenzo from Ethereum and Ponos. And yeah, welcome. This talk will be about Poseidon 2, which is a faster version of the Poseidon hash function. So let me first give you a very short motivation. So Poseidon, the hash function, some of you may know it, has been widely used in practice recently in the last couple of years. And why is that? Well, it has proven its efficiency in many use cases, sorry. So it's also implemented in many ZK protocols, and well, the good thing or the nice thing about Poseidon is that it can be represented by a very low number of constraints in, well, most proof systems. Not all of them, but most. And it also has quite good plain performance. Of course, not like SHA-2, but it's good for what it is. However, when designing Poseidon, when we designed it like 4 or 5 years ago already, I think, there were some things we completely ignored. So we just focused on rank 1 CS, so rank 1 constraint systems, but we just completely ignored, for example, the plain performance or other proof systems. And in the last couple of years, we asked ourselves, well, how can we make it faster? Or can we even make it faster while still being very close to original design and maybe even just as secure as the original design? And we are going to talk about that in this talk. But first, let me give you a very short recap how Poseidon actually works. So it's essentially a cryptographic permutation. You can see the design on the right side here. And in the beginning, we have these, we call them full rounds because we apply the S boxes or the nonlinear functions to the whole state. Then we have some partial rounds, and then we again have these full rounds and these monomial functions for the S boxes. And the important thing here is that every matrix, so every M, this is a matrix multiplication, is actually an MDS matrix. And all these things, so the permutation then gets used in a classical sponge mode to, for example, build a general purpose hash function or even encryption if you want. All right, so these are the observations we made, and these are the most important ones. These MDS matrices are actually quite expensive, so they're very good in terms of statistical security. This is related to things like the branch number and so on. But actually, it's for our purposes, of course, something like too good. So it gives very, very good security, but higher than can actually be achieved. So our question was, can we find a cheaper matrix, which is more efficient to implement and more efficient to compute, but which still provides the same security level? And the second observation is then we can also use all of that in a compression mode, which has been done also recently, for example, in Jive, like half a year ago. All right, so first, in a nutshell, what are the changes? Well, you see these highlighted in blue. We essentially exchange the matrices with two different ones. So first we have the ME matrix, which is used in the full rounds, and then the MI one, which is used in the partial rounds. And we also add an initial linear layer at the very beginning. I will come to that also in a minute. So why do we do that? Well, in some settings, it can improve the performance by a factor of up to 4. It depends, of course, on which state size you have, which prime sizes you have, and so on. And it's also much more efficient in the very classical Blanc, where you still have like a limited number of columns. All right, so how is this done? Well, let me give an introduction to these two matrices. So ME, essentially, we took some inspiration from lightweight cryptography, from hardware actually, where we try to minimize the number of XOR gates, and this is quite similar to what we want to achieve, because if we don't have many additions, then likely we are faster also in plain. So this ME matrix is exactly that one here. So it's a circulant matrix built by 2 times this M4 matrix and then just repeated the M4 matrix. And this now may seem very, very random, but it's actually taken from this DL18 paper. And actually what this does is, or what this enables us to do is, we can compute the multiplication by that matrix by using just 12 operations in total. And that includes both additions and also multiplications. So we repeat that for a number of steps for the whole state, and then we do the circulant matrix, and in total we only need 5 T operations again. And this also includes additions, and so both additions and multiplications. So we have some number of operations which is linear in the state size, which is of course better than the naive approach where you have a quadratic number of operations in total. All right, so that's the matrix for the full rounds, or for the external rounds. Let's call them like that. And then we have the matrix, the new one for the internal rounds. So we took inspiration from a recent permutation, which is called Neptune. This Neptune permutation uses this matrix quite differently and also has like a different structure also for the nonlinear layers. But we essentially found that it can be used also in Poseidon, this matrix. And the nice thing for the partial rounds is that as a designer, as a cryptanalyst, we don't need to focus on statistical security anymore, because this is done by something which is called white trace strategy, and is only done in the external rounds. So what we can focus on is actual algebraic security. So we are trying to find a matrix which provides dense polynomials in the output and which prevents subspace trails, which essentially allow you to skip an arbitrary number of rounds. And we found that this matrix is, so if you use the right values in the middle, it actually allows you to do so. And it's quite efficient because, as you can see, you just need to like compute the sum and then just add the sum to each intermediate value, and then you have the new state. So this is even more efficient than the matrix before. All right, so we also did some additional changes to Poseidon. So first, since there was this optimized implementation where you just add the partial or the round constants to the first word in the partial rounds, we now do this directly. So the optimized version is not needed anymore, the more efficient implementation version. And we also add a linear layer to the very beginning of the permutation. And the reason for that is that there have been some attacks in the past which essentially allow you to skip, I think, up to 2 nonlinear layers. Without increasing the cost a lot of the attack. So we do this like as a precautious measure. But let me emphasize that the original Poseidon, which does not do that, is not in danger. So it's still safe to use the original Poseidon. The change is very minimal in that regard. And finally, also we propose a new compression mode. So this is very, very old, so to say. Instead of using the sponge function, you can just do 2-to-1 compression or 4-to-1 compression and so on. More directly by using such a compression mode. And if you're building a Merkle tree, for example, this can help a lot. And finally, a very nice message for all the developers and implementers. So this efficient transformation of the partial rounds is not needed anymore. Actually, it makes the whole thing a bit slower if you do that. And the good thing is that all the hundreds of constants you need to store all the matrices for the partial rounds, so that's all not needed anymore with the new version of Poseidon. Okay, so in a nutshell, what are the changes? Well, we add this linear layer at the beginning, the ME one, then we exchange all the matrices for the full rounds and also for the partial rounds, so 2 different matrices in total, and we do the round constants more efficiently in the partial rounds. However, some things stay the same, and that's the nice thing actually. So you can use the same round number both for Poseidon and for Poseidon 2, which means essentially that you can use the round number script of Poseidon 1, you get some output for the round numbers, and you can use them also for Poseidon 2, so they're the same. And yeah, also the nonlinear layers and the S boxes and these GCD conditions, this is all the same as the original Poseidon. Okay, so something about performance. We have 2 tests here, one with a 255-bit prime and one with a 64-bit prime. And we see already for 255 bits that Poseidon 2 is consistently faster. And also for the 64-bit prime, we see, for example, that we're always below these 5 microseconds here. And let me also emphasize here, it depends a lot on which prime field you use. So for example, if you have a prime field where multiplications can be done very, very quickly because you have an optimized version of the reduction, And then, of course, the performance difference is a bit is not the same. So essentially, this focus is very generic. And also, if you move to a smaller prime, which makes you essentially increase the state size, then the performance difference is even larger compared to the original Poseidon. So even for 32-bit primes, for example, it may be very beneficial to switch to the new version. Yeah, so we can have up to 4 times improvement here. And the code is also available here. You see the link below. All right, so before actually concluding the talk, let me also, besides the conclusion, let me give you also some outlook. So, well, first the conclusion, right? So Poseidon 2 is significantly faster than Poseidon. The biggest change is actually in the linear layers. And we're also working, or we have finished working also on a gate for Plonky 2, which essentially switches from Poseidon 1 to Poseidon 2. And what we found, or what we've been seeing in the past, and this is now the outlook thing, is that there are many modifications also to the original Poseidon which focus on plane performance. So for example, there's this modification using the circulant MDS matrices, which doesn't change the specification of Poseidon, but makes it a lot faster. I think ×2 improvement, something like that, for a 16-word size. So it's pretty nice. And what we can learn maybe from that is that plane performance is also important. So not only circuit friendliness, but also plane performance. But with all these modifications, we are still not getting close to the traditional hash functions. So not to SHA-3, let alone SHA-2, which is even faster. So the question is, of course, can we close this gap? Can we find some hash function which is both circuit friendly, but also like very, very fast? And currently we're working on a successor to reinforced concrete, which also works with smaller primes. So this is called RC64, but we're also aiming for 32, 31-bit primes. And we're trying to close this gap. And yeah, well, I want to close this presentation also with a question, maybe, can we even reach SHA-3 like plane performance? And maybe in the future, maybe even SHA-2. Let's see. Thank you very much.
So I think we do have time for questions. Okay, we have one over here.
Thank you for the presentation. It was very nice. Yeah. Hey, our team was doing actually 3 implementations of Poseidon 2 in ZKX, so we went digging into the paper. And I think we have different questions. My question would be around the 4x4 matrix, which you use also for example, 8x8, you are using a circular extension of that. Did you look into other sizes? Whether the paper that you've used have these kind of figured out, but I haven't seen any generalized results behind those.
So if I understood the question correctly, it was about this M4 matrix.
Yeah, the M4, which is kind of, you use it also in multiplies, but you don't have other sizes, and even for 8, you are using this in a circular fashion.
Yeah,
okay. You are not using a generalized results of that to 8.
Okay, if you looked for alternatives there.
Yeah.
Yeah, so that's a good question, yeah. We did look for alternatives. The reason is that, and this is also closely related to lightweight cryptography, that the larger the state size gets, or the dimension of the matrix, the harder it gets to actually find an efficient one. However, for example, if you are thinking about these circulant MDS matrices for Poseidon, which you can use for the original Poseidon and improves everything, you can actually also use the circulant MDS matrix for this M4 matrix. So a very famous one is simply the AES matrix, which is circulant MDS. So maybe instead of doing that here, you can also do like 3 or 4 or like ×2 FFTs, and then maybe you're able to even accelerate this version. Yeah, but that's an excellent question. Yeah, thanks.
Thank you.
Are there any other questions? I think we would have time maybe for one more. Let's see. Well, I guess if not, then thank you so much for this talk. So next up we have Sai Dang. Hi. And he's going to be presenting ZK Tree, a ZK recursion tree with ZKP membership proofs. Welcome to the stage. We'll just give them a second to get your slides up. There you
go. So in the talk today, we are going to tackle two problems using ZK recursion. So the first is the high cost of ZK verification on EVM. The second is the long proving time for large ZK circuits. So let's see two examples. Our company, Polymer Labs, is working on ZK IBC, and for both ZK IBC or ZK Bridge requires continuous verification of ZK light client circuits on EVM. And currently, the cheapest ZK stock verification takes around 230K gas per proof. And if we assume the gas price 25 and the ETH price 1,600, then the cost per verification is around $9. And if we want to achieve a good user experience, we need, like, for example, 30 seconds per verification. Then the yearly cost becomes around 10 million. So the question is, can we share the cost with many users while still keeping the low latency? Another problem is the long proving time. Some background on the light client. So light client checks the consensus state of a blockchain, and on-chain light client verification enables communication between different blockchains without relying on a trusted third party. And for example, the Tendermint light client, typically we need 32 top ED255 Lightning signatures to be verified to reach the consensus. And if we use ED255 Lightning circuit, it takes about 12 seconds to prove a signature. So if we want to verify 32 signatures, it requires more than 6 minutes. And that's too long for our use case. So the question is, can we reduce the proving time still with the same amount of gas? We are going to solve this problem in using recursive ZK, but let's see some definitions. So this is a typical non-interactive ZK proof system. The prover takes public input X, waitlist or private input W, and produce the proof pi. Verifier takes public input X and the waitlist to generate true or false. In recursive ZKP, a new prover, here prover prime is added. It takes the X and the old proof pi as input and produce a new proof pi prime. And if the verifier verifies the new proof pi prime, then both the old proof pi and the new proof pi prime are verified. And there are commonly two types of recursive ZKP. First is recursively prove one ZKP inside one, and the second is recursively prove multiple ZKPs inside one, and they have different use cases. For example, the first one can be used to compress the proof size, and also can be used as incremental proofs. The second one can be used to aggregate proofs. It is used in the Mina and also the ZK EVMs to handing off the computation. Our contribution in this project, first we introduced the ZK tree structure, which enables efficient aggregation of a large number of user proofs into one root proof, allowing users to share the constant cost of on-chain verification. And second, we prototyped the ZK tree recursive proving pipeline using Plunky 2 and significantly improved the prover time. Third, we demonstrated the practical application of ZK tree by verifying tandem consensus in a single proof on EVM. So in ZK tree, there are 3 types of proofs. The first is user proof. It can be produced by any ZK protocols, such as Plunky2, Groth16. Currently, we are working on the support of pairings, so we will support Groth16 and Plunk. The leaf proof is used to recursively prove the user proofs and produce a standard ZK tree proof that can be verified in a ZK tree load proof. The load proof is the main type of proof that is used to build the ZK tree. Both ZK tree leaf proof and load proof are implemented in Plunky2. So this is an example of a ZK tree with 4 user proofs. And when building the leaf proof and the load proof, we will not only recursively prove the child proofs, we also calculate the input hash and the circuit hash of the user proofs so that we can build 2 Merkle trees of the input hash and the circuit hash. With these 2 Merkle roots, we can run the membership proof of, for example, if we want to prove user proof 4 is included in the root proof load 3, we can supply the Merkle path, which includes the input hash, circuit hash of load 1, leaf 3, and user proof 4. We implemented ZK tree using Plunky2, which has very fast recursion speed. It takes about 1 second to build a ZK tree load proof. But it's very expensive to verify on EVM because it's based on Fry, which has large proof size. So we added a recursive proof here to recursively prove Plunky2 into a Groth16. So the proof size reduced from 130 KB to 200 bytes. The recursion time takes about 55 seconds. We also prototyped the distributed proof generation pipeline. In ZK tree, the ZK proofs generation at the same level are independent. There's low communication cost. And in theory, the ZK tree generation time is log n multiplied the proving time per load, so which is 1 second. The total communication cost is squared multiplied the proof size, which is around 130K. The ingestion pipeline is very flexible. For example, we can customize the load distribution based on workers' hardware configurations. We can make it a data stream engine to make it possible for immediate inclusion of high priority user proofs. In this case, we will locate a balanced binary tree in this case. And for the final Groth16 circuit, it can be split into multiple sub-circuits with the trade-off between the prover speed and on-chain verification cost. So this is the result of our current pipeline. It takes about 17 seconds to generate each ED2519 proof in Plunky2. The ZK tree generation time is 5 seconds. The rest is the recursion, Groth16 recursion. And total time around 77 seconds with 320K gas cost. And the time with the star mark can be reduced by split the circuits. In this case, we will get higher on-chain gas cost because we will deploy like multiple on-chain verifier. But we can reduce the total time to around 30 seconds. And also remember that we can distribute the gas cost among multiple users. So we can still like verify it at a very low cost. So that's it. We open sourced most of the code, and they are available here. And you can find more implementation details and more results in our ZK paper. Thank you.
That's great. I think we do have a few minutes if there are any questions. Just put your hand up if you have a question about this ZK tree. Doesn't look like there are any, so thanks so much.
Thank you.
Cheers. So I think we are a little bit ahead of schedule. How many? It's 40 right now? What's the, I don't bring it up, 42. Well, do you want to just go? Okay. We could wait, we could start. I say we start. So Raul from Jump Crypto is going to share with us Zero Trustless Light Client Infrastructure for Blockchains. Oh, you changed the name? Yes. Oh, Biscotti, since then, wow, okay. Yeah. Here's your mic. Cool. It should be, just try it.
Cool. Okay.
Yeah.
All right. Yeah, so it's going to be kind of, the topic is sort of similar to the last presentation, but I wanted to kind of present something that we've been working on for quite some time. So it's called Biscotti. We love Italian cookies, apparently. So this is basically trustless light client infrastructure for blockchain. So what we're looking at is essentially some of the stuff that everybody in this room has been talking about for a while. How do we build efficient ZK light clients for different blockchains? I should mention also, this is joint work with a bunch of folks at Jump Crypto over here. So, all right. So we started with Ethereum, obviously, because I think most people in this room understand why. So I'll just give kind of a brief overview of why what the consensus protocol for ETH looks like and what we're trying to actually prove. So the Altair hard fork introduced this light client specification, which allows cheap verification of the chain's consensus with minimal bookkeeping. What that means is basically you have this sync committee that has a set of 512 validators that are uniformly subsampled from the entire set of validators, which is around 400,000. All right. So here are the few components I think that that are in this proof of consensus. So we have the BLS SIG verification. We have the simple serialize and RLP. So simple serialize and RLP are the serialization libraries that ETH uses. SSE is for the ETH2 consensus protocol, and RLP is for the ETH1. There's a few components underneath, the Merkle inclusion proofs that you need to do, and the SHA function implementations that you need to do all in circuit. So take a quick look at this, but I'll kind of dive into each one of these components, and then we can kind of feel free to ask questions on these as well. Okay, so what does the architecture actually look like? So let's take a really simple example. We have a trusted block, we have an attested block, and we have a finalized block. Okay, so I wrote these in the order in which you might think about proving them, not necessarily the order in which they actually happen when you're actually running this protocol. So let's look down at the component diagram below. So the trusted in the trusted stage, you're basically doing a bunch of Merkle inclusion proofs. You have to do these Merkle inclusion proofs also in the finalized stage, but effectively we're doing something that was similar to what the ZK tree folks talked about, where you're basically doing these inclusion proofs within your circuit. And then we also have the BLS signature verification. So I won't delve into kind of the details of exactly what you need to prove in this, because it does get a bit hairy, but this is kind of the sort of keep this basic architecture in your head. All right, So what does the implementation look like? Obviously, I think a bunch of folks in this room also understand kind of what the various proof systems look like in the world. This was kind of our criteria for choosing a proof system. We want this to work really fast and really well in production. So we obviously need fast recursion. We don't want a trusted or necessarily universal setup. We want super fast proof generation. We want the developer ergonomics to be really nice. And the other thing that we're looking at is kind of community support and interest, right? We want to go with the things that people are kind of converging on in the industry, like where's the puck going, and we want to be there. All right, so this is kind of the breakdown of the primitives that we have built in circuit in Plonky 2. So we have SSE, RLP, 2 hash functions, SHA-256 and Ketchak, and then obviously the BLS signature implementations, which I'll also dive into, which contain a lot of different components, including the base and scalar fields, the extension fields, doing hash to curve, doing the pairing, all in circuit. So let's talk about the non-native operations for a second. So as many of you know, Plonky 2 is written over the Goldilocks field. So this is a 64-bit field. It's great for super efficient recursion. It's also great for efficient proof generation, but it doesn't really support these like non-native field operations that you really need for some of the work that we're doing, especially with BLS signature verification. So the ECC operations like point addition, whether it be affine or projective, you have these point multiplication, affine or projective, and then you have these extension towers that you also need to build in. So we have to build in like the quadratic extension, the quartic extension, the sextic extension, and the 12th degree extension, all for doing the pairing, the Miller loop, and the final exponentiation for the BLS signature verification. So all of these components didn't exist in Plonky 2, and now they're available. The code will be up soon, but these are kind of the different components that we had to build in. All right, so let's talk about the hash functions for a second. So there's 2 main hash functions that we need to use, SHA-256 in the RLP case, and then the Ketchak hash function implementations in circuit. I won't delve into the details of like exactly what we did with the hash function because we're going to be talking about this in more depth in future posts that we'll make. But effectively, we have an optimized hash function implementation using like interleaved bit representations that make doing these computations in circuit much faster. So the high-level overview is that if you represent a set of bits as like this interleaved representation, you effectively interleave them with zeros. You can do an AND and an XOR operation in a single sort of addition instead of relying just on doing these separately. So all right. Okay, now let's go into the BLS signature verification. So as many of you know, also the ETH2 beacon block signatures are constructed over BLS 12381. And the BLS signature verification algorithm uses a pairing. And there's a bunch of different components within the pairing. So first, with the Miller loop, that contains doing things like line add or line double, and then evaluating those. But all these operations are kind of in your 12th degree extension. The final exponentiation also requires, just sort of like simple exponentiation, doing like Frobenius, doing like these operations over the 12th degree extension as well. And then we also want to check that the signatures are actually within the right group. So we have to do an efficient like sort of subgroup check using, there's a few papers out there that we've looked at as well. And so this requires you doing like an endomorphism. There's another component with hash to curve, which requires a bunch of different components as well. And so I just kind of wanted to give a sense of like what the complexity looks like when you're trying to implement BLS like within Plonky 2 or within some of these proof systems. All right, so this is the last component that I'm pretty excited by. This is something that we've been working on more recently as a result of working with a bunch of these different proof systems and like, how do we not use sort of the syntax of the proof systems directly so that we can actually have a nicer experience using these proof systems, and hopefully we'll make this tooling, available to other people as well. We're working on a sort of like simple embedded DSL within Plonky 2 that evaluates the expressions in your language as in CPU values and also compiles those same expressions to in-circuit targets. So you can see like right there, this is like a super simple expression language. Let's say you have like a constant like big uint. You might have a bool. You might have like want to add 2 things together. You might want to multiply 2 things together. But kind of the advantages of this is like it sort of like abstracts the semantics of the builder interface that you have within Plonky 2 away from like the person that's actually implementing this stuff. It also improves the auditability and readability of these in-circuit programs. So every time you do something like builder.add and you try to put your operations there, you don't need to do that. You don't really need to do that anymore. You're just sort of just kind of, you look at the paper that you're trying to implement, take that stuff and copy it over into Plonky 2. It makes it a lot easier and nicer to use. It also improves like the test and validation efficiency and life cycle of your program. So instead of having to just sort of sit there and say, okay, I'm gonna write this test and validate it against this other library, like I can write like 50 tests, you know, in a few minutes, as opposed to just a single test that takes an hour because you're just, you know, playing with bit strings all day. So the other thing that I think is super exciting about this is that we can sort of encode proof recursion directly into this DSL and abstract that away from the implementer as well. So instead of having to write these generators that are allowing you to do your proof recursion, you can sort of just encode that in the compilation step. So you just say, okay, I would like to add recursion at these lines, at these levels, and at this level of granularity, and it should just do it for you. And I think that that's going to be very exciting, especially as you know, people start using these different libraries, want to do proof recursion super efficiently, but don't really want to think about like what are the real intricacies of using these different like tools. Okay, cool. So another thing that's super exciting about this this framework, or I guess framework of embedded DSLs, is like kind of new optimization paradigms, right? So this is kind of like a more PL term, but hash consing basically is this idea of like, you know, abstracting over the semantics of your program and the structure of your expressions. So let's say you have an expression in your program that you've already seen before, right? Instead of just like evaluating the expression again, you should just be able to look up the value, right? And so this kind of like allows you to do that. And this is sort of like a standard sort of trick that's used in PL as well, and that's something that we want to bring to the Plonky 2 ecosystem and so to some of these different proof systems. The other thing that we can do is actually directly encode optimizations at the evaluation step. So instead of just, you know, adding, let's say, 2 in-circuit representations together, using whatever operator exists within that proof system, we can just evaluate the addition or whatever operation in CPU and then construct the in-circuit representation from that. Another example of this is like, let's say you're doing scalar multiplication or exponentiation. You can just directly encode the most, you know, inoptimal algorithm for doing that, right? So the naive implementation is like exponential. If you use double and add, it's linear, effectively, right? So it kind of reduces the complexity by an exponential time, but you can just directly sort of encode this in the evaluation step. So every time you use that function, it's already being optimized. Yeah, so another example of this is like simplifying in-circuit conditional. So a lot of you have probably come across this canonical example in circuits where like you have to represent, you know, both cases of your conditional, and that's sort of, and then you sort of have to like add these 2 cases together, and that's not really how you think about programs when you're, you know, programming in the non sort of like circuit world. And I think this is going to be like something that people will hopefully find a lot easier to write. All right, so what are we trying to do with all of these things? So let me just summarize. So we worked on a bunch of stuff related to like sort of like Merkle inclusion proofs, you know, ETH serialization, and then kind of doing signature verification of BLS. I said why we started with ETH, but obviously we want to move to other chains as well. And so working on, you know, some of the ZK light client infrastructure for non-EVM chains, you know, Ethereum, non-Ethereum chains. We want to work on some of the cryptographic primitives that enable this. So like, let's say EDDSA signature verification or ED25519 signature verification, or let's say like Cosmos or entitlement consensus. And then we want to work on faster and more optimized proof generation for this stuff. So there's a ton of work that was going on the Z Prize last year, especially on FPGA acceleration and GPU acceleration. We want to take some of this stuff and kind of at least enable some of these primitives to work on hardware as well. And then, again, improve developer ergonomics and additional sort of like DSL features so that people, when they're using these proof systems, don't have such a horrible time trying to bootstrap into the ecosystem. All right, that's it. Thanks.
I actually have a question. The DSL, does it have a name? Is that Biscotti?
So it doesn't have a name, but if you have a name of an Italian cookie you'd like to use or dessert, we'll
Let
highly
you know.
consider that. Yeah.
Okay, it doesn't have a name yet then.
No, it doesn't, yeah.
Okay. Which like biscotti though, is that the larger construction? Is that the name of it?
It's the larger thing.
Okay, got it. Are there any other questions about this? Oh, we have a few questions. That's perfect. I think we have time.
Oh yeah, I was wondering if you could comment a bit on kind of like the performance, especially compared to some other sync committee implementations, like succinct, like how many gates, like on-chain for cache things like that.
Yeah, so we're not releasing any numbers right now, but we will soon. I just don't want to like talk about the performance yet until we have the full thing, sort of like where you can like review the code and look at it. So.
Hey, thank you very much for the talk. I'm just curious, what was the motivation for starting this project?
Yeah, there's a few motivations. I think, generally speaking, light client infrastructure is sort of like lacking within the ecosystem. I think a really efficient way to do this, obviously, is using ZK. For a long time, it didn't really seem like that practical to do this, especially because you need super efficient proof generation. There's a lot of other applications, for example, bridges, cross-chain messaging protocols, ZK oracles. Like a lot of this stuff requires some of this infrastructure, and like so, a jump, we try to contribute to a lot of infrastructure. So this is the motivation for that.
There's one more here.
Hey, thanks for the nice talk. So you're building ZK Lite prime proofs for the Altair sync committee, not an alternative to it, right?
Yeah, this is for the sync committee in particular, yeah.
And specifically for bridges.
Sorry, could you say that again?
Specifically for bridges.
No, this is sort of just generally like,
okay.
This is general like light client infra, yeah.
But so for bridges, the problem that you've got is, so the sync committee can post, can sign the correct block on-chain and can sign a fraudulent block for the light clients, and it doesn't have any way to prevent that.
Yeah, so the sync committee, there's no way to prevent that. This initial implementation uses the sync committee. We plan to expand it to the full validator set.
Okay, great.
Yep.
There was another question over here. And if there are any other questions,
Hi,
just put
thank you for the talk. Have you thought about the business models and whether you are looking at this as a infrastructure, public infrastructure, or more of a proprietary software?
Yeah, we have no plan so far in terms of like, there's no business model attached to this. This is just sort of like stuff we've built, so,
There's one over there. If there are any other questions, just put your hands up now so I can. You have one? You have one? Okay.
Yes, I wanted to clarify. Right now, it's not available to to play with it. Is it It's not released right now, as I understand. But is it available to dig into it deeper somewhere or not?
Yeah, so we'll release the code soon. It'll be up on GitHub, and you can look at it. So
okay.
We just haven't released it yet. Yeah.
There can follow now to find out updates just on Jump. Yeah.
Sorry, so could you say that again?
There can follow updates on this topic. I don't know. Do you have some specific?
Oh yeah, check out our Twitter.
Just Twitter. Okay.
Yeah.
Okay, there's one here, and then one there, or then one there, and then one there. And then I think we wrap up, because I think, yeah, we're kind of at time.
Who's the first?
I have a quick question. Why make the DSL in Rust, or like this quasi layer on top of Rust, instead of a language that has nicer metaprogramming abilities?
Yeah, one reason is that because, we're already working with Plunky 2, we're already working with Rust, and this is more of it started out as more of an internal tool. We just were very frustrated with using the syntax that exists already, and so we said, why not just do this? I think the other thing is that there are already a lot of, sort of ZK DSLs that exist and are out there in the ecosystem, and we're not necessarily trying to compete with them, we're just trying to provide better dev ergonomics in a particular way, right? And for a particular proof system in a particular language, so.
There's a question over here.
Hey, are you familiar with the Unison programming language?
I am not.
Okay, I wondered if you'd taken inspiration from it because it reminded me of what you were talking about. Unison, it's a functional programming language where the names of functions are determined by a hash of the kind of combinator primitives that go into it. And there's all kinds of benefits that you get out of that. You're probably discovering some of them with what you're doing, so it might be worth looking into. They've been working on this for a lot of years. They've come up with a lot of kind of cool things you can do once you're in that kind of world.
Cool, take a look.
Okay, we have one back there. And then I think we'll wrap up on that. I think if that's okay. I guess after, if they have more questions, they can chat with you directly, right? Perfect.
Have you done sort of benchmarking on how long it would take you to prove 400,000 signatures right now?
We haven't done a benchmark on 100,000 signatures, but...
Do you think it's plausible in under 12 minutes?
Potentially. I mean, I have a decent idea of like what kind of hardware you would need to do that. I don't think you need to... When you say prove, on the order of 100,000 signatures, like, that's not really what you're doing because you have, like, in the Ethereum protocol, you have like a set of like aggregate signatures that you need to prove, and so it's mostly just doing a bunch of aggregation and then doing a bunch of, let's say like a few hundred, signature verifications. So that I think is probably feasible, but no comment on the other part.
All right. Thank you so much, Raul. And thank you all for these questions. So that wraps up our lightning talks on this stage. There is another lightning talk batch on the side stage at 5. But yeah, for now we're going to take a nice break, go have some more coffee. And I did want to let you know, if you weren't yet aware, there is a shop at the back that sells ZK podcast mugs and shirts, if you're interested.
Hello. All right, well, welcome in. I guess we are probably going to wait maybe 1 more minute until people finish arriving. If you haven't noticed, I am just happy to be walking around with a cool ZK mug and just drinking out of the ZK mug. And these things, just if you find them very cool, happen to be for sale outdoors or outside. Sorry, not outdoors. Don't go outdoors. Outside. All right, out here somewhere, I think. Anyways, I was just told to do this by Anna, so blame her for this. But the point is, these are very cool, and they will summon the ZK gods who will make your proofs work and then make everyone happy. So you should definitely buy one. I give no guarantees, only probabilistic ones, other than that. But okay, so kind of now that people are more filling in, now we're going to learn a little bit about fuzzy knowledge, which is fuzzing snark circuit primitives by Innocenti from Aztec, right? All right, let's get it up.
Hi, my name is Innocenti. I work at Aztec, and I'm going to be talking about how we added fuzzing to our circuits so that they became a little bit more secure. Before I start, I'd like to thank Guido Vranken for helping me with this project. So, to start with, let's look at what security of circuits is. To me, it's like this hellish tower of complexity, which can tumble from the smallest touch. At the bottom, we have the basic base field primitives, which, for example, in our code base are implemented with Montgomery. Then on top of that, we have all kinds of stuff, such as elliptic curves, multi-scale multiplication, FFTs. On top of that, we have scalar fields, where we actually start implementing the circuit logic with various gates. For example, we use Plonkish arithmetization, obviously. And on top of the gates, we can finally build some of the basic primitives which the application developers that are using our systems to create final proofs will actually use. So this whole tower of complexity, very easy to break one thing, and if you break even one small thing, then you can disrupt the correctness of the whole algorithm and the whole proving system. So let's see what we can do with the circuit security. So one of the traditional ways to kind of cover the security is to do unit tests. It's the most basic thing. You should always do it. For example, our code base is simply covered with them. And they do ensure that you do just the smallest, the most basic security. It means that your circuits will not suddenly fail on the most basic of functions. So, for example, you know that addition works the way you intended, that no new changes to the code base, especially if you are actively developing. On top of it, no new changes actually break all of the old stuff. So, yes, it's a nice place to start, obviously not enough. Then we have the end-to-end tests, which kind of help you cover the base that the whole system works as intended, at least for the thing when you are trying to ship. So this, for example, we added it to our code base when I understood that, yeah, unit tests are definitely not enough. Sometimes there are still small things that fail. So an end-to-end test help you see that what you are deploying is actually working. But then we actually want to improve on the security. We don't simply want to check that our code base is working. So the first thing that most people do is internal audits. That means that either the person who implemented the classes, implemented the code base, or somebody else, for example, somebody who wrote a similar primitive, a different part of the code base, comes and looks into what you've developed, suffers a lot, takes a lot of time to look into this stuff, but kind of holistically checks that there are no strange assumptions, no weirdness that another person implemented. And usually it is quite an in-depth check, but obviously this never covers anything. So what do? We go to external auditors. And one of the issues is that with external auditors, you always have a very limited time frame, which means that even the best teams, of which, well, there are some, but I think there are more projects than there are auditing teams that can actually check those projects nowadays. So those teams have only a very limited time, so they can look at a small primitive and maybe ensure that it's correct, but that's the limit of it. Obviously, they can't cover the whole code base, especially such a huge one as our Breitenberg library. So even after all this, the thing that we have is this, which is not enough. We'd simply like to check our code base even more, especially the core primitives that we're using. So for example, we have several core circuit primitives which are very important to us. So what do we do in this case? Well, we need something automatic. That's a very important thing. We can't simply delegate to various auditors, internal or external, because that means that we spend more and more time on human resources. Our code base grows. We need to spend even more. And any small change to any part of this code base after the audit can completely just right away all the money that we spent before that, because a new bug is going to be introduced, and now all of those checks are useless. So what do we do? Well, in the last 10 years, apart from the ZK Cambrian blow-up, there has also been a Cambrian explosion in gray box fuzzing. So you can look at it this way. Originally, you have this very simple way of testing, which is called a unit test. We are testing a very small primitive. We're checking that it simply works. Then we have black box fuzzing, which we'll go into detail a bit later, but the idea is you stress test a small part of your code base. You do a lot of computation on it with different random data to check that it is operating correctly. And what you do next is, at least to me, when I started learning a bit more about it, seemed like magic, because now you have some sort of algorithm that learns itself what it should research and how it should test your code base. So let's start with the basic black box fuzzing harness to see how the system actually works. So let's say we have this very small program which simply checks that a particular string is being encountered in an input. If a particular string is being encountered, then it writes out, then it triggers an abort. So this would be something like a bug in our code base. Basic black box fuzzer would fuzz this function in a very simple way. It would generate some random data. For example, we are taking this random data from the system randomness, or if we are more efficient, we are using a pseudo-random number generator. And then we are sending this new created input data to the program under test, this function. Then we see if this has triggered some sort of bug in the function. And obviously, if we've triggered the bug, we found something new, great for the fuzzer. If not, we go on to the next iteration and we continue doing this. The problem with this approach, with the black box fuzzing approach, is that, especially for this ladder-like style of code, however good your generator is, there's always a very low probability of the black box fuzzer reaching somewhere deep inside your code base. Like, for example, with this function, the first step takes around 1 divided by 256 probability. The next one is even less than that. It's 1 divided by 2 to the power of 16. And so it continues. So if you had 8 steps in this code, then you'd never reach them on a single core, on a single machine in your lifetime. It would simply be impossible. So obviously, this has a serious drawback. So what do we do? Well, with gray box fuzzing, there's a small change. Instead of simply generating the inputs to the function, we now use mutation. So let's say we start with no information about the process and about the program initially. We have what's called an empty corpus, and the corpus is just a collection of interesting test cases for us. We take something from this corpus. Right now it's just a simple zero-length test case, zero-length input. We mutate it. So that means that we are changing it in such ways that at least some part of the original test case, of the original input, is left. So it doesn't completely generate something new, it updates something that was before. Then we send it to the program under test. And this mutated test case operates just as any other input would. Then if a bug is triggered, we do it just as in the black box fuzzer, we just output the bug. Finally, we found something. If not, then instead of just repeating the loop like we did before, we send the coverage data for analysis. And coverage data here means that either we collect the information about various branches being taken or maybe various comparisons being taken. Then we look if any particular branch on this new execution has never been taken before. So for example, in this case, if we are starting from scratch, we see that, oh, the first if has actually been passed through. So we found a test case that starts with an A, and we save that test case. So now we've actually changed our probability distribution, because in our corpus, we have a new test case which has already found the first symbol. So to find the next one, now if we pick this test case from the corpus, would have the probability that originally for the black box fuzzer and for this fuzzer was to find the first symbol A. So we continue like this, and after several steps, we trigger the abort. So the basic info is we have an algorithm that remembers where it stepped. If it steps somewhere new, it also remembers that, and then it tries all of those different test cases that it found and updates them instead of just forgetting about them and running along with something new. And this is a very powerful technique. Since 2014, when AFL, American Fuzzy Lob, was published, it was kind of the first open source. I'm not sure about 100% that it was the first, but it was the most popularized at the time fuzzer that used this mechanic with coverage. There has been just an explosion in various vulnerabilities found in open source projects, just because people started using this technique and applying it everywhere to each project that there was. So now, about the primitives, I'd like to introduce Bigfield as an example of a primitive that we'd really like to fuzz. So today on this stage, there has already been a talk about this field arithmetic that is non-native to the scalar field that we are operating on. It is a big headache for us. At least it has been for some time, and though we're using it kind of in a different way to Mina, we're using it for the rollup. The base principles are the same. So we are trying to emulate these base field element on top of scalar field. For that, we need actually 5 elements. That's because we're using the CRT's formulas, which I'm not going to go into detail here about, but we're using one scalar field just for the scalar field modulus and 4 for 2 to the power of 272 modulus. We also have tracking uints, which are used to optimize constraints in our circuits, because if we just do it straightforward in our code base without trying to optimize this a lot along the way, it will just cause an explosion in the number of gates. So we need to optimize this quite a lot. So yeah, constant source of headaches, tons of bugs found at various stages there. So how do we fuzz Bigfield? Well, let's start with a simple, stupid black box fuzzer. Let's pick a function. For example, here we see a basic addition function. We take 2 random elements, convert them to the Bigfield elements, add them, and check by creating the proof and verifying it. Seems pretty straightforward. So this is the simplest thing you can do. This is something that you can start with. You just run this function in a loop, and you have a basic black box fuzzer. But obviously, there's lots of room for optimization. The first thing is, well, creating the whole proof. Each time you want to check a simple circuit primitives is way too much effort. So, for example, if we were to use the Planck proving system, it would mean that we'd have to commit to stuff. So that's multi-scalar multiplication. Then we'd also have to spend a lot of time on FFTs. We'd have to do Fiat-Shamir to just check a few, like maybe less than 100 gates. Well, in Planck, maybe 1,000. But yeah, that's just a lot of effort to check a very simple primitive. So instead of that, we do the simulation. In our case, it's just going through various gates, looking up the values of variables, substituting the witness values there, and checking that all of the gates hold for concretely for our witness. Having done that, we've already increased the speed of our fuzzing a lot. I think when we did this, the speed went up by a factor of 100. So what do we do next? In our C++ code base, we use the function LVM fuzzy test one input, which is something that's provided by Clang. There's this very nice library, libfuzzer. It is very simple to add fuzzing to your project. If you're doing Rust, there's libfuzzsys cargo package, which basically does the same thing. So you can do absolutely the same stuff. So what we do here is we receive some data from the libfuzzer backend. So our fuzzer is already supplying to us mutated data this way. We check that the size of the buffer is enough for us to take 2 elements in the base field. We deserialize them into the base field elements, set big field elements from that, and after that we add the values, check the circuit. Also, one of the nice features of the fuzzy is that you can simply return -1 if there's some sort of problem on which you want to trigger the fuzzer to say, okay, some assumption has been broken, something's bad here, and you simply return 0 if there are no issues. So that's already pretty good. Now we've added very simple gray box fuzzing to our code base. We're checking it automatically creates coverage. So the only thing is you have to compile with particular flags. Now you have coverage. Now you have an automatic fuzzer that checks that your circuit is correct and goes through all the various stages to look for the correctness of a very simple function in your circuits. So. What's next? Well, there's this concept of oracle in gray box fuzzing. It's quite different from the oracles that we encounter in crypto. The basic idea is this. You have some sort of security policy you'd like to adhere to. For example, in binary fuzzing, you'd like to check that you haven't read any uninitialized memory, or you don't have any undefined behavior. Once again, I know for Rust people it's not as important, but for us it is. So there are these oracles, but we can also add cryptographic oracles and oracles specific to our code base. So in this particular case, we not only check that the circuit holds, but also that the value produced during this simulation is also the correct value. So we choose to check that the value produced in the big field class is the same as the base field element that is also done through the summation of the original elements. So now we have already gray box fuzzing, we have a simple oracle. This is probably the most you can do with one function by just using libfuzzer. But one of the problems with libfuzzer, and one of its greatest features for binary mutation, is that libfuzzer has very binary specific mutations. So there are 3 classes of mutations in libfuzzer. On the left here, we can see the individual value mutations. So, for example, when you take a particular test case, in this case it's coffee, that's one of the few words you can write in hex. There are several things that you can do. One, you can flip a single bit in the test case. You can flip a sequence of bytes. You can substitute a particular 1, 2, 4 byte chunk by a special value. For example, there are values like OXFFFFF or values like OX2, which are special because there are lots of constants like that, because there are lots of underflows that can happen like that. Then you can also treat some part of the test case as a uint of size 4. You can do small additions and subtractions on that, and that's basically what what the value mutations are. Then you can also do structure mutations on the test case. You can insert bytes, you can duplicate bytes, you can shuffle some bytes in the test case. And the final and one of the most important mutations in libfuzzer is splicing, where you take 2 test cases and you start picking sequences of bytes from one of them and from the other. So you're kind of mixing them in together. This is done so that you can take features from both of them and maybe find some new code paths inside a class by getting information from some other code path. So this is very powerful, but this is not very efficient for the cases that we are talking about. So we are working on we are working in field elements. So we want field elements. So one of the first things we did was introduce specialized mutations. And here there are several things that we can do. The first one is we treat the values as field elements. Then we choose whether we want to treat them as something that needs to be converted to Montgomery form first or not. The point here is a lot of the time when we are doing this fuzzing stuff, we do comparisons, somewhere in between. libfuzzer can do that. So for example, it can look at these comparisons somewhere in the code and check, oh, this is a nice value. If I can substitute this value somewhere in the test case, then I will probably pass this if statement. And that's really powerful, but not when you have a Montgomery form in your code base. When you have some sort of form which is very nice for addition, multiplication, very nice for actual arithmetic, but that is not the actual value that you're outputting, not the actual value that is present in the test case. So to use this powerful feature, like half of the time when we are mutating a particular field element, we first convert it to Montgomery, then we apply the mutation, then we convert it back to plain to save it in a test case. And then we have three choices. One is to delegate to libfuzzer mutations to use those powerful features. The second is to use additions and subtractions with small values but modular our base field prime, because we know that the arithmetic is different here. And the final one is to substitute special values, but special values that are special for the base field, because obviously they are different from the binary ones. So here, these are various roots of unity to the scalar field that we are working on, because that is a very special value that can also break some stuff. So just various special values. And yeah, then we either convert back to the plain form or continue. And this already has produced some so this already produces some very powerful mutations. We apply several of them at the time. So both in libfuzzer and in special mutations, not just one mutation is applied every time. There are several mutations usually applied in a sequence. So for example, in libfuzzer, it's 5. So now we have a very specialized fuzzer, which for one function, we have an oracle, we have coverage, and we have specialized mutations. And now there's really nothing that we can do for just one function. So what did we do next? Well, one of the problems with big field is that it has an internal state. So that means that if we take two values of our base field and we construct a big field element from them, we might never reach some of the internal states in big field by just doing one addition. So obviously we are not checking for all the cases, all the problems that could arise there. So the next thing that we have to do is basically substitute this one function fuzzing with fuzzing the whole system of the big field. So instead of fuzzing just two field elements, which you see on the right, we create this instruction vector. And the instructions there are pretty simple. So we can store a witness or a constant value in big field to a particular stack that we're using just as an intermediate. So for example, here the stack is all 4 elements. And then we have different, basically all the various methods and operators that we have in the big field class. Multiplication, addition, division, assertion that something is equal to a different value. And by using this instruction vector, we are basically manipulating the different interactions that can happen within the big field class between all the different methods that can happen. So for example, here on this slide, we see an instruction vector where we first store a witness into the 0th position, store a constant in the first, multiply them together, store the result into the 2nd position on the stack, add the results from the 0th and the 2nd, and store it back to the 2nd, and then divide the 2nd position by itself, and store it in the 3rd. So just using this instruction vector and mutating it, we can explore all the various different states that can happen in big field. And at the same time, coverage and libfuzzer is guiding us. So obviously, mutating it is a bit different to the mutating just the big field element. So what we have to do here is once again reintroduce value, structure, and splicing mutation. The splicing mutation works in the same way, only it operates on instructions instead of bytes. So for example, you take the first instruction from one test case and the first instruction for the other. You can just go like checkers. You can take different sequences. With the value mutations, we mutate either a particular index on the stack that an instruction is taking inputs and outputs into. So for example, we can substitute the index from 0 to 1. If it's a storing instruction, then we can change the value from witness to a constant and back, or change the value. And there we delegate the value change into the thing that we saw before that, the way we mutate the field elements. And with structural mutations, yes, they're kind of the same. We can swap two different instructions together in the test case. We can duplicate instructions, delete instructions. And this way, we are exploring everything that can happen in big field. Obviously, it's not formal verification, but it is very efficient in practice. So, yeah, one of the last things is we have to update the bug oracle, because we don't just have one function here. So because in the big field we are tracking the maximum value of limbs, because we are tracking the maximum value of the whole big field element, and since we are checking that the value of the big field is equal to the value of the base field, these are the checks that we implemented. That no limbs ever overflow the maximum value, that there are no overflows to the whole maximum value, and that it's always equal to what we're actually trying to simulate. So, yeah, apart from that, one of the things that we introduced is a random seed instruction. So apart from storing and all the instructions in the various methods, this is a very simple instruction that allows us to cycle through various constructors through big field. There are various ways to initialize a big field element. This allows us by changing one value to switch between them so that we can holistically check all the states. Then we also implemented instruction weights at some point, because multiplication is obviously much harder than addition, and we don't want to use tons of multiplications at once, because it will degrade the speed of the fuzzer. And one of the cool features that we used in libfuzzy is the length control, because if you limit the size of the length of the instruction vector initially and you allow it to grow slowly instead of just quickly explode, it means that your fuzzer has more time to explore individual cases before it degrades speed and reaches more complex situations before going through all the easier ones. And I'd like to finish with what kind of bugs we found with this. So even though we had an audit for our base arithmetic before that, we found actually Montgomery squaring bugs. That's why it was that blank in the beginning. That's why it was that problem. We actually saw that our basic big field formula is not always correct. We found a case where it was broken. It was a very low probability edge case, like astronomically improbable, but somebody with a particular mindset could have used it for something bad. Then some of the infield assertions have been broken. We had several range constraint overflows, segfaults because our code base is in C++, and Winston constant inconsistencies. So this is a case where a lot of the time when we're building circuits, we are writing the circuit primitives for a very particular use case, and we are not checking that the witness and constant stuff is actually 100% identical in logic. So because here we are cycling through whether values are witness or constant, we are kind of ensuring that they are identical in logic. So yeah, and that's it. Thank you for listening to me.
Cool. Thank you so much. Unfortunately, we do not have time for questions, but I would love to introduce our next speakers. Thank you, by the way, for the talk. So our next speakers are Alan and Ferdinand from Triton VM/Neptune. And what will you be telling us about? Something about a red wedding, if I recall correctly. Oh, well, that sounds terrifying, but good luck to...
Chilling.
Indeed.
Thank you very much for the introduction. Hi, everyone. My name's Ferdinand. Next to me is Alan. We both work at and for Neptune, which is a new cool upcoming L1, and we also both work on Triton VM, which is a zero-knowledge virtual machine using Starks, and this is also the topic of today's talk. Right, we're going to start with a short summary of the talk. So obviously, we're going to be talking about Starks. Now, Starks have obviously use Fry all the time. For the purpose of this talk, we'll be treating that as a black box, sort of delegate stuff to our vessel, and I'm sure that's going to go all well. Oh, I guess these are a slightly outdated version of the slides. There's supposed to pop up the word fry now. You'll see it in a bit. Starks also extensively use AIR, or algebraic intermediate representation, which encodes the rules of the computation that the Stark is talking about. Now, there is a very well-known trick to accelerate the computation of this AIR, which is deep AIR, and we will be presenting this here also, but we claim no novelty here. But as far as we know, for the first time, we'll also be throwing Planck into the mix. And this final construction will give us the red wedding, and once we have that, we can use that to lower the degree of our AIR, which is really quite cool. Why do we want to do that? Well, speeding up Starks is just generally cool. But more importantly, if you want to have recursion, you really want the verifier to be as fast as possible, because that means that you have fewer cycle counts and that the recursive verifier is even, like, it benefits from this largely. And a short note on the notation that we're going to be using. So we say Planck because that was sort of the working title, or the word that we used during development of this. You can use Planck, but you're not limited to that. It's basically any snark, and for the purpose of this presentation, just imagine that we will be using Fry also for this snark. So it's not limited to Kate commitments or anything like that. And we will also be using that as mostly a black box. Right, let's quickly review Starks so that we're all on the same page. So a Stark works by initially having the execution trace of your virtual machine. This is the AET. Every row is a state that the machine had at some point, and every column corresponds to a single register as it evolved over time. The first thing you do is to low degree extend this. This amounts to evaluation of interpolation of every column as to get a polynomial and then evaluating it over a larger domain, which then gives you what we call the base tables. The prover commits to that by doing a lot of hashing every single row and then putting all those digests into a Merkle tree. Sending that commitment to the verifier allows, then the verifier gives some randomness back, and that allows the prover to extend the base table, which then arrives at the extension table. And the semantics of this is basically to tie together several otherwise separated parts of your base table. So in the case of the VM, you can imagine that you have a main processor, and maybe you have a chip, like a hash coprocessor and random access memory and so on. And this extension table allows you that these components can talk to each other in a manner that is sound. The prover also commits to this table in exactly the same fashion, and then evaluates the error constraints to get a bunch of quotients. This is essential to prove that the rules of the virtual machine were being upheld. The prover then also commits to this entire quotient table in exactly the same way, gets some more randomness from the verifier, sums up all the columns, and then runs fry on the resulting combination code word, what is abbreviated CC in the slide here. Running fry produces some indices where the verifier would like to get knowledge about the concrete row that is being used. And so the prover reveals all those rows to the verifier. Upon receiving one such row, the verifier first checks that this row had actually been committed to. And then it evaluates the AIR circuit itself to check that the row is actually consistent. And it does that for every single row that it receives. Lastly, the verifier also sums up every individual row to get the combination code word, the parts of the combination code words where the green arrows are pointing at, and runs fry over that. And that is a basic Stark. And now we will start hacking on it. Alan, take it away.
Perfect. All right, strap in, because this picture is about to get a whole lot more complicated. So, first thing, instead of computing the combination code word, we want to verify it. So the prover is going to commit to it, giving us a new Merkle tree. This Merkle tree was already there because it was part of fry, but we were treating fry as a black box, and now it's the same Merkle tree, but now the Merkle tree is no longer inside the black box, it's outside of the black box because it's there before fry starts. So the prover supplies the Merkle tree, and the combination code word is going to be verified. So we're going to pull out this summation symbol, the green summation symbol, and plug it into the circuit, which we can totally do. So the circuit is enlarged with the summation. Next up, we're going to compress the quotients. Given that the circuit already contains a sum with random weights, we can actually move a part of this sum earlier on in the circuit and shrink the shrink the quotient rectangle down to a single column. Boom. Yay, now we have more space on our slide. There we go. Okay, up next. This is the deep trick, which we claim no novelty over. I think it was first used in ETH Stark, maybe even before that. The idea is the fry verifier supplies a bunch of row indices where it wants a point in order to run fry. The deep trick, you can think of the fry verifier is indicating a new row, but this row doesn't live in the table. It's an out-of-domain point that does correspond to a row because you just evaluate the polynomials in that out-of-domain point. But you can think of it as a row that doesn't live in these tables. And then the verifier really just runs the circuit on the single out-of-domain row, thereby generating a new pink point corresponding to the evaluation of the combination code word in that out-of-domain point, and it can use that pink point to update the fry points using the deep trick. So we went from T many evaluations of the circuit down to one evaluation of the circuit, which is a big deal because the circuit is kind of big, and we want to avoid having to do that work more often than necessary. The next step is not really changing much of the mechanics, it's just observing that some of the columns are redundant in a very particular sense. That sense being they are fully determined by other columns. And so they don't really contribute much in some sense. For example, oftentimes we have constraints of this form. If A equals 0, then stuff happens. And the way you algebraize that is if A is different from 0 or something happens. And the way you arithmetize that is by introducing a new variable called B, which contains the inverse of A if it exists and 0 otherwise. In the end, you get multiple constraints, and the key takeaway is that B is fully determined after A is known. In fact, you can write B equals A to the power P minus 2. And so B doesn't really contribute that much more information, and the prover can't even cheat with a high degree polynomial corresponding to B because B is bound to A. And so we don't even need to prove the low degreeness of B anymore. So we can omit B from the sum in the combination code word. So basically, we have fewer summands, less summing to do. Yay. Small win. Also, the prover doesn't actually need to transmit the entire out-of-domain row because the deterministic columns can be computed by the verifier from the variable part. So, in effect, the rows become shorter. Yay. More win. This principle reminds me of something, should remind you of something also. The only reason why we're including those deterministic columns is because we need them for the circuit. But for all other purposes, we're trying to hide them. And that's sort of what snarks are supposed to do. In a snark, you're allowed to commit to a very long input with a very short string of cryptographic data, effectively hiding all the witness information. And so the question is, what happens when we try to mix snarks, plunk, into the mix? Well, the prover now has to evaluate the circuit, and it has to prove the correct evaluation of this circuit on a commitment to the out-of-domain row. The purple point corresponding to the quotient and the pink point corresponding to the combination code word still have to be explicit inputs because the sequence is important. The prover commits to the out-of-domain row, then gets randomness, computes the quotient, then gets more randomness, and computes the combination code word point. In this construction, the circuit is still not committed to. So in order to prove this circuit is satisfied, the prover has to run through every gate, and so does the verifier. So the only thing that's achieved by this is actually shrinking the row, shrinking the proof size effectively. And the verifier gets to verify this partial plunk, but still it's a rather slow verifier because the verifier has to run through every gate of the circuit. Now, this point is rather artificial because once we're introducing a commitment to the row, well, we might as well commit to the circuit as well. And that's where we're getting the biggest speed up from. Essentially, we're replacing the explicit representation of the circuit with a polynomial commitment to the circuit. This allows us to outsource a lot of work to the indexer, and so the online prover doesn't have to do that work anymore, and certainly the verifier doesn't have to do that either. This is where the big speed up for the verifier comes from, because the verifier no longer needs to run through every gate of the circuit. It can just run the Planck verifier. And that is, by assumption, much, much cheaper than running through 5,000 gates of the air circuit. But this is not where it stops, right? Because the entire orange row is hidden by a commitment. And so we don't really feel the cost of a long orange row. And that allows us to lower the degree of the error. For instance, if this is a constraint a times b squared minus c, this constraint has degree 3 in 3 variables. What we can do is we can introduce a new variable to lower the degree of this error at the expense of one more variable. This represents the same circuit, but the circuit, that's not part of the slide. The circuit is not as tall, but is wider now. But it's fine. It's still equivalent. But the nice thing is that a lower error degree means a smaller blow-up factor, and therefore gives tables that are not as tall. And so we have to run NTTs on smaller tables. So that's the nice thing about chilled error. Yes?
And we need to do less hashing, and the fry domain size is smaller, meaning fry is faster too.
Indeed. So the picture changes quite dramatically. We start from the algebraic execution trace, and we extend this to the base table, which is a lot less tall. And we only care about the variable columns to begin with. We extend those to the extension table, and so on. Still a single quotient column, still one combination code word. The rest of the picture is much the same. The key point is already in this part of the slide. The tables are a lot shorter, which gives rise to a speed up for the prover, which was not the objective of this entire exercise, right? We were trying to speed up the verifier, and we succeeded in speeding up the verifier, and somehow we ended up with a faster prover too. Yay, I guess.
Absolutely.
Yeah, so the picture doesn't really change that much. The point is you can get away with an error degree of 2 at basically 0 cost. Oops.
No, that's all right. I think we're there. Right. Thank you very much, Alan. If I may. So we prepared a cost summary for this entire thing, and this slide is a little dense in information, so I'm not going to run through the entire thing. It is more meant as a consultation for later.
You mean this slide is the dense one?
Yeah, I figured this one is probably one of the most densest ones. So the point of this slide is showing that the verifier and the prover both are faster. And as Alan said, well, did you? I'm not sure. Let's highlight it again. If you have a faster prover and a faster verifier, for the recursive verifier, which is both, that means that we have a compounding effect. So in a sense, the original goal of like getting a faster recursive verifier was very much achieved in that. And I would like to leave you with about 3 insights from this talk. The number one is put a snark inside your Stark. It shifts workload from the verifier to the prover, which is generally good. The second point is that the verifier does not need to know the out-of-domain row. It only needs to be convinced that it exists. And the third realization is that deterministic columns exist, and that fact can and should be taken full advantage of. That was the Red Wedding. I'm glad that you all made it through. Thanks for having us.
And with that, we have a few minutes for questions. Does anyone have any questions for Al? Oh, all right. Let's get started with Zach. And there's someone else in the back as well. If you have any questions, raise your hand now, just so I'm not like real time pointing at people.
Hi everyone. Ooh, loud. I was wondering, would it be possible to articulate kind of the key differences between the Red Wedding and just basically like doing the kind of the stupid brute force thing of like taking the entire Stark verification algorithm, including opening all the commitments, etc., and just shoving that inside a snark? Does that make any sense?
It does make sense. You would have a huge circuit for your indexer, but since that's done offline, that cost is tolerable. I don't think I've thought about this line of questioning. Have you? No. Yeah, I'm afraid the cost comparison slide was already full. So we weren't looking for questions to answer in addition to the costs that were mentioned already there.
Sorry for adding confusion. Okay, so, sorry, I'm very sleep deprived and sort of munching up time. But like, would it be possible then to say like, so what specifically? Could you repeat again what specifically are the algorithms that you're shoving inside the snark?
What specifically are the algorithms inside the
snark?
Snark.
Like the snark circuit you're creating, because it's like a subset of the snark verifier.
Yeah. So the circuit in the snark corresponds to the air constraints of the stark.
Okay. Great. Thank you.
That was it?
I think so.
Okay.
All right. There was one question in the back over there, if I recall correctly.
Hi, thanks for the talk. So is there any generic algorithm to do the automatic degree reduce?
Yes, there are. You just iterate over a description of your multivariate polynomial, and you find the first monomial with degree higher than 2, and within that monomial you find the first factor with degree higher than 2, and you introduce an extra variable z equal to that factor, and apply that substitution throughout.
So after apply that substitution, you always get the highest degree of 2, right?
Yeah, you can't do lower than 2, unfortunately.
I can do lower than 2. I didn't get that, but anyway, I get answer. Thanks.
Does anybody else have any more questions? All right, Jeremy.
So just in terms of the snark inside the stark, so you're basically verifying a single row of the stark's circuit using a snark inside the stark. What, like, commitment schemes, so don't you, in order to make the snark verifier run inside the stark, you have to have some commitment scheme. What sort of commitment scheme are you using for that inner snark? Or am I missing something entirely?
We would be using fry again, basically, or still, I suppose. And then you can even batch those fries together. Does that make sense?
Oh, yes. Okay.
So in the end, you even only have to run one fry. I'm happy about that reaction.
Cool. No more questions from the audience. Well, in that case, I guess you're being released from your, presentation early. Thank you both so much. A round of applause. Anna, do you have some words, ideas, notions?
I think we are now taking our last break of the day, and then we return for our last 2 talks of the main stage. We're coming back with Sangria, which is relaxed Planck, and scaling trustless DNN inference with ZK snarks to GPT, ResNet, and more. So come back for that, but for now, take a break.
Thank you.
First of all, getting rid of computable rows is like an easy trick that I don't know why we don't already do that. We don't actually. It's also super easy. I have no idea why we're virtualizing all those extraneous things. I know. And we end up computing in the circuit anyway. So okay, that's good. Okay, so you're basically I'm still trying to figure out exactly how the inner snark size the verification of snark is being faster than the verification of the start directly.
So the truth of the matter is we don't actually, we're just,
yes.
but the way I see it is that you are able to boil down super complex set of equations with the air into basically, I don't know, how many equations are text were as long as it's 7 or something.
Yes, exactly.
So that's sort of reduction.
You see, right. So then you take that row. So then you just do another round. And you take that row, and you effectively take the row and you translate that into commitments to all of the whatever the 7 or 8 polynomials which exist in the long argument, right? And then you take those long argument things and you add them as commitments and then eventually boil down to the right anyway, right? Okay. I think I get it at a concrete level enough, but it's going to take me like sometimes write all the bits down in like detail. I think I mostly follow that.
That was the objective to some Jeremy and Zach.
Yeah. So like some of the stuff obviously so we're already using all the deep stuff. We're already using all the easy tricks. Because we're also currently already using an extra layer with the communication argument post the we already do it right now. We take the commit to this like sort of data section of the start. But we want in that data section the memory trace. Right. We want to do a solution to the memory trace. We have the memory trace, and we then have the computed memory trace. We commit both of that, and then we do the communication on the installation of that another sort of call. I wanted to do the same instead of calls to start reading another one after that. We may need another
The trick is describing how to permute it.
yeah, exactly. Because we're not the only ones who do that.
Not in person.
Yes.
We're doing well. I mean, I like this one. Some science is a nice break from overcast activities. Software progress. We're happy with the rate of development, but some breathing down from actual
I owe your response. So, we say the 74. Is it, so when you said 74, you mean the air
Great job, that was really fun. We don't do the trick where they make which means that we actually get one before we do the so we only do it so we read 5 before it. So we don't It's like, which columns so a bunch of our columns are capacity, like we actually have that literally we want to reduce that. There's a zero gadget, and that gadget basically computes the input of another element so that they multiply the bar with zero. Yes, exactly. But yeah, I will have to think about exactly how to operationalize the idea of doing because I mean, you've already moved all of the work of doing the verification to this, extension of the large screen right here around the corner spot. But if you can actually reduce the circuit, the other thing is that a bunch of stuff is dependent on the verifier. So right now, the constant, so if you look at our verifier, especially if I've done it first, in case we care about the most, right? The verifier spends something like 60-ish% of its time on the actual verification of the fry part of it, but it spends something like
only fry, which does include some hashing, or fry and hash?
Fry and then hashing for fry.
Okay, fry and hashing for fry.
Yes, exactly. All the market trades, but the effect of the deal is that a lot of that, and then we spend a little bit of the time hashing the significant portion of the time hashing columns from the valley, right? But then good like 30 or 40% of our total time is spent verifying imagine up this, row or this set of columns, the row that is out of domain. That's the out of domain row, and you verify that out of domain row during all of your meaning polynomial or your main constraint set, which is evaluating the error. Exactly, it's evaluating error constraints. So when you do that, I mean that costs us 30% of our total time to verify just do that. So if we can remove that, also that circuit complexity is something we have to push down really aggressively in order to prevent like versions of automatic. So the other thing is we'll do it this way.
You should. You know, by any chance, how many arithmetic gates are in your layer? Like not only multiplication, but also.
It's like order. Let's see. It depends on what's for the. It's like 8 No, we're seriously considering Goldilocks. We're considering Goldilocks, and we've been constantly considering Goldilocks, and we keep like slowly moving toward it. But every time we do, one, there's more code that needs to get genericized for control. But also, the more we run into places where, like, okay, so for example, prior to recently, we currently moving in the risk files institution. We do an instruction decoding where we basically take the risk file instruction and look at like a bit field and logic. And that logic is very expensive in terms of the number of gates. Yes, exactly. Now, what that means is that most of those things end up being bits, you know, there's a big constraint or whatever. Which means that moving to Goldilocks, because it's a bigger field, means that the memory usage of a bunch of stuff doubles. The number of constraints don't go down at all. Because we're just sort of a bigger field, the instruction decoding doesn't get any better. So we were like, oh, well, actually, Goldilocks, keep it those things. But now we're looking at doing pre-decoding where we actually, where we transform at like tile time, after you generate the ELF, when we put the ELF, we take a code section of the ELF into the special state of memory where they're pre-decoded. So we can basically actually have the nicest sort of representation of a RISC-V instruction. They still map one-to-one RISC-V instructions. They're no longer, the instruction point is no longer pointing to memory that has a 32-bit value. It's now pointing to memory that has a set of field elements in it that represent the instruction, which means that all of the actual logic to run it. So what that means is the encoder gets thrown out of the circuit, and when the encoder gets out of the circuit, then the number of things we're doing that are like bitwise goes down, which means that all of them that are not bitwise, like multiplies, where a 34 multiply can big circuit can connect. Like if you do the limbs and then you have carries and all sorts of crap, but 34 multiply Goldilocks is like trivial. Now suddenly, but previously the overall percent of our circuit that was like bullshit binary crap was high, and the amount of doing actually multiplies was smaller. So Goldilocks just made this part smaller, this part didn't get any smaller. It was all twice as big. Now we get rid of this junk, then suddenly the only thing that matters is multiplies. So Goldilocks is more win, the circuit gets smaller. So anyway, we're basically about to do another major rev in the circuit, and when we do,
and when you do, you might as well switch to the client.
Yeah, I know. Yes, I know. Were you guys involved in that or at all? Oh, really? Okay, because I love that app. Like, I mean, I think Poseidon 2 is more like fundamentally it's still part of what Poseidon is far too great. And like the lookup mechanism in 5. Like, I actually am really glad you guys did that because I have been ever since I think the Southern reinforcement concrete
incredibly well done, by the way, like the whole thing. Yeah, reverse engineering some things, yeah, like reading certain papers that like not so many people read and so on, yeah, and like really doing that. Wow. Yeah, great.
I still think there's a huge educational thing on starts because I think that many people I talk to have no how snarks work, but that very straightforwardly, and they are very intimidated by starts. I think that I think maybe Ellie's original stuff, things like that, were just very opaque to people, and I think that it's getting better. Understanding starts. It's true.
The reason why you write those papers so inaccessibly is to pass peer review. Because readable papers don't pass peer review. There's nothing to do with quality.
I recently had an idea of how it might be possible to go from presenting smarts to stars in not in a iterative fashion.
Yes.
As in not completely start from scratch. Because basically the circuit description in your smart is the AT per star.
Yes.
And the constraints, I don't know,
I think
so on are linear.
Exactly. I've been thinking about. I actually have been noodling on the same thing, although I have not ever done anything about it. It's one of those things that I like a new patch that seems like a cool idea, but I'm not. But I feel like there's someone could write a starts for snark people that was it
reminds me of the books my lifetime for the baby, right?
Yeah.
Quantum physics for babies, general relativity for babies. We should write Starks for babies.
Yeah, stars for snarkies or something.
Yes, exactly. There's a lot of things that are, if you wanted to try to explain starks from ground zero, there's a bunch of stuff that you have to get to that is quite hard, but if you talk to someone with snarks, interactive oracle proofs, they got it. You don't have to explain that part of it, or you don't have to explain, fiat shamir, or what a commitment is, or all that stuff. But you do have to explain, there's all these arguments related to distance, mostly correct polynomials, right? The idea of a mostly correct polynomial is not something that you ever think about in the case of snarks. Prove that it is absolutely correct polynomial, except for error or minus plot. Whereas in the case of the star, got to just show that it's mostly a right polynomial. So I think there's that. Plus, also, yes, I think the idea of here's a circuit. It's not just a circuit; it's the same circuit running over time. What do you guys call the things that read on the row prior? We always call it tabs.
Since we only have 2 rows ever to compare, we just call it current or next row,
I see.
or just ending previous row.
Yeah, we mostly only care about one of that, except for the shot to 56 itself.
Alan, you guys have dinner plans? So Rick, right, who's on the FAT, will have dinner, whatever.
Yeah.
Could I come in and have dinner?
I don't have plans, but I was just planning to follow the guy.
Yes.
And your perspective, I guess.
Yes. But yeah, the other thing, by the way, that we're working on, which you guys might think is interesting, is that if you look at the, so currently we have this notion that we're putting a bunch of these accelerators where it is a RISC-V circuit, but it also has other, we repurpose different columns based on whether some other flag is set to represent different kinds of multipliers.
Or the same columns.
What's that? Yeah, in order to columns, yes. So we increase not deterministically, right? You on the SHA circuit, it's going to receive the question and answer the answer. But then what you do is you commit to both the SHA circuit and the RISC-V circuit. And then you use that commitment to generate a random multiplier to then produce a permutation argument of the two buses to show that the things that went over this bus now go over this bus instead of the flip-flop. And then you can use recursion to combine. So basically, you can make two separate circuits talk to each other with high bandwidth, but they can be completely independent circuits. And then you use recursion to prove that they're compatible. So then it lets you move all the complexity of accelerators into separate circuits. It makes them much more expensive. It's like a multiple chips. It's like multiple chips on a bus. Where all the stuff goes in. That's right. Yeah. How do you guys like that one? You gave me a bunch of good ideas. Yeah, definitely. I'm excited about the sangria thing too, because I've been like, yeah.
Do you work with the topic as well?
I mean,
you very well.
I work with all the topics.
Awesome.
I don't know any. I talked to someone here who explained the very rough version of sangria. I think I somewhat understand, but I completely talk about it.
You said you work with the topic in sangria?
Start, yeah.
Oh yeah, I mean,
built the RISC-0 system.
Yeah, which is basically a Stark. It's a Stark. We built our own Stark implementation, but I've also built a Stark implementation because basically before I started the company, I've been interested in zero knowledge for like 7 years. What I kept doing is reading the latest papers, trying to understand what the hell they were about. It took me a couple of times because I'm more of a developer than a mathematician. And then writing implementations of the papers and trying to get them to run fast enough, with my feeling that in order to make the system really useful, you had to be able to get to a recursion time on the order of a second. And that until you were there, it wasn't practically useful. And as soon as I felt like we were at the point where that was possible, which I think was a start.
Michael.
Oh, yeah, Jerry. Nice to meet you, yes.
You didn't mention it.
Just another like scoop.
We have been mostly talking about it from maybe there.
Did you see this? So I haven't figured out. I think there's a trick though that I haven't figured out yet. Which is hold on. How do I contacts? What is where's the button where I? Oh, I.
What's the highest order of
If you do 2 to the 30 minus 1, even though 2 to the 30 minus 1, 2 to the 31, 2 to the 31, 2 to the 31 and 32. No, exactly, we have checked. So 2 to the 31 minus 1 doesn't have any good unity, right? But the quadratic extension is all of them. So 2 to the 31 minus 1 times 2 to the 31 minus 1 is 2 to the 64 minus 2 to the 32 plus 1. And so that one, it's basically, well, it's not.
It has the same number.
It's the same, yes, exactly. So it's like a half of plot.
Yeah.
Well, it has one less. Oh, sorry, it's 2 to the 62. It's 2 to the 60. Yes, exactly. It's 2 to the 62.
Okay,
yes, exactly. But the short version is that it has a ton of roots of unity. So basically, you do your FFTs in the rate to extension of the field. So, but I think there's a trick. I think there's a trick where you can take and you can do 2 rows. You can use the field extension to do. Anyway, currently it's not a win as far as I can tell, because the fact that you have to do the FFTs with the range to extension makes the FFTs too expensive. The FFTs are significantly more expensive. So I don't think it's a win over Bayfair currently, but I think there's some tricks you can do with the FFT that I've not yet figured out. Because the word on the streets
go through the whole like reverse engineering how a start would be there?
Yeah, I mean, I had to read all those papers to figure it out.
Wow. Like how many months are we talking?
It took me well over a year to like actually get the whole thing down. You know, especially because if you're reading like the original fry, deep fry, you know, like and then like the whatever read stuff, proximity gaps for read solving puzzle, whatever, like that stuff is like extraordinarily dense. And I didn't really understand it. Basically my trick is when I read a math book and I don't understand it, I try to implement it in code. And as I do that, I figure out which parts I don't understand because I can't write the code, and it like helps me like narrow down the questions, get very concrete. Like so, I just keep trying to implement it until once I implement it, then I can actually understand it. And then I go back and I read it, and I'm like, oh, this almost makes sense. Like, why didn't I understand this the first time I read it? It's like, yeah, it's a whole. But yeah, it's still like, it's a whole. But I feel like it's getting better at people understanding of what starts with life. It's not still really much more accessible. It's becoming more accessible as time goes on.
Because people have learned how to use it.
More accessible. I didn't put together until after getting back from dinner. I was like, that's the guy who wrote the anatomy of a star explainer.
I didn't get that reaction 3 times today.
Yeah, I had wondered in reading that explainer, I was like, what's this guy working on? Vitalik wrote the one, and you had the other. Well, basically, when I started, the only two like readable I guess there was the like Stark Math series, but it's not all of them. Yeah.
You could actually take Vitalik's story and implement it.
Yeah.
You wouldn't get something that's pure, but you'd get something that resembles.
Yeah, yours was super helpful for some details. Jeremy kept just telling me, just read the deep fry paper. Okay, Jeremy. I'll try again.
Me and my wife met really like 2.5 years ago. And then I was like, I kind of took like, for the favor, I traded a feeling Bitcoin to it. And we were like, tell us. Yeah. It was fun. I had a deal with Andy Pilestone, because he was also like, how do you start? And he was like, I'm going to read up about it and know it in 6 months. Let's talk about it on the 28th of December. Yeah, I was like, Andy, like, you know starts now. He was like, no, like, we can't talk about it. No, it was funny.
I'm going to go get the rest of it quick and take it back. But I think this
It's an open row. It's not like I mostly don't like I fight. You know, it's fine. You can be up there.
Hello, everyone. Please take your seat. We are going to start up again with our last block of programming. So this is kind of the final stretch of the main stage for ZK Summit 9. So yeah, I'd love to invite Nico to the stage, who's going to share with us that Sangria is relaxed Plonk, a Nova-like folding scheme for Plonk. Yay!
Thank you. Cool. So I hope 5 p.m. is an appropriate time to have some sangria. It's not the kind that you might want, but hopefully you'll like it. I'll start with a bit of an overview. Don't worry if you don't understand all the terms that are in here. This is kind of bird's eye view. We're going to define them. So sangria is a folding scheme, and folding schemes were introduced in Nova. And they're like a cryptographic primitive, and they're the key to getting cheap recursion in Nova. Nova shows how to do folding schemes for R1CS specifically. What a folding scheme does is it compresses 2 instances of one problem into just one instance. So let's say I solve 2 Sudokus. Rather than showing you the 2 solved grids, I combine them into one and show you that one solved grid. So Sangria does that, but for Plonk circuits, and actually for Plonk-ish circuits. We'll see that some of the extensions of Plonk are supported as well. The costs of doing that are similar to the costs you'd have in Nova. The verifiers work. You'll see that there's 2 parties. There's a verifier. The verifier is constant with however many rows you have in your circuit. However, the constants are slightly worse than Nova. And we'll see why in a second. And you can think of this as a price that you have to pay for the added flexibility of Plonk circuits. Quick overview of what we're going to talk about. I'll give you some motivation, like why do we care about recursion? What can we do with these things? What are the best known results? A bit of background to get everyone to the same level. What are Plonk circuits? What is a folding scheme? And then we'll jump into Sangria. How do we actually fold these circuits? And I'll describe sort of the trade-offs, like what are the costs? How do they scale? And kind of what is the design space that we have to play with? So going right into it, what's our goal? We want to do what we call incrementally verifiable computation. It's kind of like the formal way of saying we want to do recursion. We have this one function f that we apply many, many times. So we have a state S0 that goes into f. We have some like private inputs, omega 0, and that outputs a new state S1. That state S1 is then fed again into f with a new private input, and we keep going up until we've reached like n iterations. What we want to do is to have a succinct proof that some prover knows all the private values, W0 up to omega n minus 1, such that the final state is correct. So the verifier should only have to see the first state, the final state, doesn't really care what happens in between. What can we build with this? Why is this useful? So it turns out if f is one cycle of a microprocessor, say, RISC-V, ARM, whatever you want, this iterated approach to f is actually like running the processor. We could also do roll-ups with this. If S is the state of a blockchain, and the omegas are incoming transactions, and your function f is the transition function from one state to the next, we now have a roll-up. We have a succinct proof of many, many blocks. So hopefully you're convinced that IBC is useful. Let's see how we do this. This is very similar to the diagram we just saw, but we have now this new row of proofs being carried along. And the question is, what happens inside this black box prover? So we're going to have to do the function f, because obviously our state is coming in, coming out. To update it, we need f. And we're going to have to do some extra work on the proof, because we have a proof coming in, a proof coming out. That extra work we're going to call the overhead. And as you can see, this overhead, we pay for it at every step in our computation. So the question is, how small can we get this? And that will be kind of the defining feature in our system, like how performant this is. So let's take a look at what's been out there already. Top right, there's a little reminder of what we're doing. So we have these nice things called snarks, which you probably know about if you're sat here. Succinct, non-interactive argument of knowledge. So we have tiny proofs, very short verifiers. That sounds like a good candidate, right? So we plug those in. At every step, we take in a proof, verify the proof, and output a new proof that we did all that correctly. And this is sort of the approach followed in Plonky 2. It's how Starkware do their recursion. It's what Fractal does. It's quite nice, but it's very expensive. I think Fractal has about 1 million R1CS constraints. Can we do better? The answer is yes. The people working on Halo came up with this idea of accumulation. So they realized that a verifier could be split into like an easy part and a hard part. And what we do at each step now is we read the whole proof, but we only run the easy part of the verifier. The hard part gets accumulated and deferred till the very end of all our steps, and we only do it once. So yeah, that's what you see in Halo and Halo 2, and in this paper called, I think, Proof Carrying Data. I forgot the rest of the name. This is quite good. This is substantially better than what we had before, and I think Halo, the original version, works with Sonic, so not exactly R1CS constraints, but it's about like 100,000 constraints, so a lot better. Can we do any better? Yes. This is what was then called split accumulation. So rather than reading the whole proof as we did before, we're just going to read part of it. So we read just part of the proof, we do just part of the verifier, and we defer reading the whole proof and doing the whole verifier until the very end. And that's a paper called Proof Carrying Data without succinct arguments. So you give up on this succinctness requirement. Can we do better? Yeah. This is what Nova does. They actually defer the proving until the very end. So at each step, you're going to take an unproven instance. You will create a new instance from actually running F, fold that, so compress it with a running one, and you're going to have a new running instance, which you can keep moving forward. This is a lot cheaper, and it comes down to, I think, in Nova, about 20,000 constraints. Can we do better than deferring the proving? It's going to sound very hard. Personal opinion, I don't think so, but maybe we can get some efficiency from using a different constraint system. Maybe you can express our circuit in a more efficient way. And this is sort of what we're trying to do here with Sangria. Instead of using R1CS, can we use Plonk? Cool. So a bit of recap. I'm sorry for the Plonk connoisseurs. You're going to have to sit through this slide. You've probably seen this so many times. There's many ways of describing this. I'm sorry if this is not the way you usually think about it. So what you can do is see a Plonk trace like a Sudoku. It's a grid, fixed size. You will fill the cells with numbers, and I have numbers in quotation marks because finite fields. And there's a set of rules you have to follow. Some of these numbers are pre-filled, because that's kind of like the problem you're trying to solve, right? So the ones on the left that I've grayed out, we call selectors, and those are fixed. The ones on the right, they're controlled by the verifier. Whoever wants you to execute a circuit is going to say, all right, I want you to start with 5 and 10 and run everything. Now the rules. The first rule you have to follow is copy constraints. And I've signaled this with colors. So 2 squares that have the same color have to have the same values. The second rule is a gate equation. So at each row, this equation has to be satisfied. And you see that our columns have little labels there. Finally, just a tiny bit more definitions. The stuff on the left, we call selectors. The copy constraints and the gate equation, those are our rules. The selectors and the rules define a circuit. Once you fix those, you have fixed your circuit. All the stuff on the right is what the prover and verifier get to play with. The verifier plays with the top part, the instance, the witness, the prover works with the witness part. Cool. Now folding schemes. Like, let's have a proper definition. And here I'm stealing a slide from Dan Bonnet. You have the link down there for his lecture, which I highly recommend, the whole course actually. So what is a folding scheme? As we said earlier, it compresses 2 instances into one. So you fix a circuit, important, we fix a circuit, and then we have 2 parties, a prover and a verifier. The prover works with 2 instance witness pairs. So it has 2 assignments to that grid we saw earlier. The verifier only has the top parts, 2 of them. Prover sends a message, verifier sends some randomness, and now the prover is going to output a new assignment to this grid. and the verifier outputs a new top part. Great. Two very important properties of this scheme. Firstly, we need completeness. So if the first two assignments were valid, the resulting assignment has to be valid as well. Super important, the second property, knowledge soundness. If you present to me, I'm the verifier, you present to me a valid assignment for my instance X, I know with high probability that you knew valid assignments for the two incoming instances, X1 and X2. I'll say that again. If you present me with a witness for the resulting, the folded instance, I know that you know witnesses for the incoming ones. Great. Another fun thing to notice is that this is not an argument. We're not proving anything. Prover says, hey, verifier says, hey, and they move on. This is kind of why it's cheaper, conceptually. So how do we do this for Plonk? So we have on the left our two traces incoming. Everything that has one dash is from the first trace. Everything with two dashes is from the second trace. And we use what I call the cryptographer's best friend, a random linear combination. So I have this random value r, multiply one of our traces by r, add them together, and bam, we have a new trace. Importantly, this thing is of the same size as the first two. So hopefully you can have some intuition from this picture that copy constraints are preserved. If my blue squares on the left are equal, and my blue squares in the middle are also equal, then the ones on the right will be equal. Unfortunately, we can't say the same of the gate equation, because our gate equation was not linear. We had this QM times AB. And that's going to put us into some trouble. Luckily enough, Nova sort of solved this for us already. So these are like the insights from the Nova paper. You are allowed to relax your gate equation. We'll change it ever so slightly so that we can still express anything we wanted to express, but that thing will be more folding friendly. The other thing is, for the verifier to hold the prover accountable, it can work with commitments. Commitments are also very short, so it means the verifier will do very little work. On the other hand, the prover will still work with the full trace. All right, how do we do this for Plonk? So, relaxed Plonk, and this is where the name Sangria comes from. Thank you. So the witness is still our Plonk witness, as we know it, these three columns. But we now have a new column, which we call the error vector. We'll see in a second how we use it. The instance is still our Plonk instance, but we also have some scalar u. We'll see in a second how we use it. And we have some commitments. And here, this notation of like having WA in the box means I have a commitment to WA. So I have commitments to all of the columns in my witness, and a commitment to the error. And this is our relaxed gate equation. So you can see in blue sort of the new stuff. Everything in black is sort of our old gate. We have these U that pop up once in a while and this E that we've added. Why do we do this? If you count sort of the number of variables in each of these terms, you'll see that we're now degree 2 everywhere. So QM A1B1, AIBI, sorry, is of degree 2. QC had no degree, so we gave it U squared, bam, degree 2. All this stuff here that was first degree 1, give it U, it's now degree 2 as well. So we now have a homogeneous function. We've also added this error term, kind of a trash can. We'll throw stuff in there that we don't like. So folding. We are still going to do our random linear combination, close to our hearts. The scalars we also take random linear combinations of. And then the error we can be smart about. So we'll keep this flexible for now, and let's see how we can be smart with it. Now you're going to have to trust me on this next sort of little equation. If we apply the relaxed gate equation to our final trace, and we distribute it out, we'll find that we have gate of our first trace, plus r times something big and ugly, plus r squared times the gates of our other incoming trace. Remember completeness, if our traces were correct, gate goes to 0. So gate of trace prime will go to 0. R squared gate of trace second goes to 0 as well. We still have this ugly thing. How do we get rid of it? Trash can. We bring in E. we say, all right, E is actually the two incoming E's multiplied by the right powers of R so that it can fit into gate on the left and gate on the right. And we just take out R times the ugly thing. That's it. So how do we keep everyone, honest, essentially? We'll get the prover to first compute T and commit to it. So T, what does it look like? It depends on our gate equation, but it's always the same thing. So that's defined in the protocol. You commit to T, send it over to the verifier. Verifier does what a verifier does, send some randomness. Sorry. And then both the prover and the verifier will do linear combinations. Prover does it with the actual trace, and we have our error term that we're adding very smartly. Verifier works only with commitments. And the nice thing about this is because the prover had to commit to T before seeing the randomness, it can't try to be smart about how it forms T. The other nice thing is the verifier has everything it needs to compute commitments to the folded witness. Right? So the verifier never sees the new witnesses, but it can still compute commitments to them. This is because the commitment scheme we're using is additively homomorphic, and this is sort of a very strong requirement of these folding schemes. I'm ignoring a lot of details. Our commitments right now are not hiding. The verifier does some work on the public inputs as well, but that's quite cheap, so it's abstracted away from this slide. This is actually what it looks like on paper. It's pretty ugly. You can see T. That's T. That's why I've not been showing it. We don't like it. You can see also that our prover will be working with random values because we are using hiding commitments. Ignore this. Go check out our little PDF if you're interested in the whole thing. The important question now, because we sort of lost track of where we were, performance. The verifier's work, which is the part we're doing in our overhead, is just adding these commitments. In real terms, we'll be using elliptic curves, and we'll be adding elliptic curve points. We can count these out. We have 5 additions. Another nice thing, when we're actually doing IVC, the incoming instance is not yet relaxed, so it won't have an error term. So in practice, we only need 4-point additions. And that's it. Your overhead is 4-point additions. I'll point out, though, that Nova has just 2-point additions, a lot cleaner, because they don't need to work with 3 commitments for the witness. They just have 1. But now we've gained flexibility, right? We're working in Planck land. We can add more columns. We can change our gate equation. How does that affect our folding? So we can deal with wider circuits. So these are circuits where you can think of each gate as having more than 2 wires coming in and more than 1 wire coming out. And the way to do this is just having the prover commit to an extra column of witness, which means if you remember here, we'll now have like WD, let's say. So our verifier is going to have to do 1 extra point addition for every extra column that we have. Can we deal with custom gates, higher degree gates? Yes, but it's going to change how we deal with our error term. So when you distribute it out, you know how we had like the very nice gates plus r times something ugly plus r squared times gate? This actually gets moved away. We're going to have gate plus a lot of ugly stuff with different powers of r plus a big power of r times our gate. The nice thing is we can apply the same trick as we did before and just keep track of these ugly terms, multiply them by the right power of our random challenge, and take them out. Again, this means that the prover will need to send commitments to each of these t values that are multiplied by different powers of r. We have 1 more commitment. We're going to have to do 1 more addition. So that's the cost of custom gates. 1 extra point addition per degree. That sounds pretty good. If we come back here, our overhead is just adding a bunch of points. The question is it worth it? Right? Like we're paying extra point additions for every column. We're paying extra point additions for every degree. What can we do with those things? The answer is I don't know. And there's a nice design space here to explore where, let's say, if I add one column, but somehow my point additions become each 50% cheaper, maybe I've won something. If I add one column and my point additions stay just as expensive, go back to Nova. Nova circuits, let's say that's our target, has 20,000 constraints. The most expensive thing in there is point addition, sadly. So we're going to have to be very smart with how we design our circuits. Hopefully, there are people in here who will be interested in designing these kind of circuits. I'll finish by just mentioning some upcoming work and giving you a few comments. So Sangria, as we saw, is a folding scheme for Planck-ish circuits. And because we now have a folding scheme, we can piggyback off of all of Nova's results, which say we can do IVC from folding schemes. We can also piggyback off Supernova, if any of you are familiar with that paper, which is sort of saying, hey, we can actually do IVC with different functions every time. We're currently working on an implementation of this for standard Planck specifically, just to show that it works, and have a running example. We're working on folding lookup-enabled traces. So we haven't spoken of lookup arguments. Hopefully, if you signed up and you did the application, you did a bit of searching, what is a lookup argument? So yeah, we're looking to fold ultra-Planck. We have something that pretty much works. I don't want to make too many promises. The ZK Summit 10? I don't know. And yeah, hopefully, some circuit wizardry to come soon to have cheaper overhead and super cheap IVC. Thank you very much.
Cool. Does anybody have any questions? Okay. Wait. We need a mic. Here, I can get you. Let's try that.
Sorry, I have 3 questions. I will ask all of them. Why is it not hiding, and why T? I didn't see the T computation. How is it not depending on the witness? And then when you go to the higher degree, you have to go more back to the folding, or just depend on the last folding? Thank you.
So it is actually hiding. Just for the purpose of this slide, I was simplifying things away and not talking about hiding commitments. In the actual protocol, it is hiding, and the prover has to keep track of the values that it used to hide the commitments. The second part of your question was about higher degrees.
The second, like, why T is not depending on the witness?
Yeah. Let me see. Why is it not?
Yeah, where is T?
Yeah. Because we've made our equation to be homogeneous, and each of our variables is going to contribute 1 power of r, we are going to be able to have something multiplied by r. Does that answer your question? Or?
Yeah, and just the slide on the higher degree, if you, the last one, when you use the higher degree gates.
Yeah, when we use the higher degree gates.
So what is T d minus 1? Oh, okay, each degree has a specific
Exactly.
T.
We have now, for each power of r, we'll have a new sort of ugly T value. It is fully defined, but it really depends on what you have in your gate. So every time you define a new gate, you're going to have to compute this out and hard-code it into your protocol.
I saw one more hand somewhere around here. Oh, 2 more hands. I think it was you first, but all right.
I know Nova only through Lurklang. Have you thought of making this a backend to Lurk?
Yeah, so the implementation, I'm actually working with Francois, who's here, and working at Lurk Labs. Yeah.
And
if we use Supernova, what's your opinion?
What's my opinion? This is on record. No. There's still a lot to be seen. I think it's a great idea. And I would want to see benchmarks, essentially. The good thing is, whatever I think about it, you can just use this, plug it into Supernova, and you have, I guess, Super Sangria, I don't know, naming. Yeah.
Cool. I think that is it. Thank you so much.
Thank
for
you
the
very much.
presentation. right, and last but not least, Daniel. Let's see, wait for slides. Okay. Aha, yeah, that's clear. Daniel will tell us about scaling trustless deep neural network inference with ZK snarks to GPT, ResNet, and beyond. Well, thank you, Daniel, and let's hear it.
Great, thanks for the introduction. So thanks everyone for coming to the final talk of the session. I know that this has been a long day, and hopefully this talk will leave some time at the end to allow people to get a bit refreshed before the end, and also to answer some questions. So today I'll be talking about scaling trustless DNN inference to these larger models, including GPT, ResNets, and others as well. So if you've been following the news over the past few months, you'll probably know that ML is eating the world and we'll all be unemployed soon. So things like ChatGPT, Bing Search, and Google Bard are becoming increasingly prevalent. And also things I'm not mentioning here, for example, Midjourney and Stable Diffusion have shown amazing results. And so one question I want to focus on today is, can we execute machine learning models trustlessly? I'll motivate this with a few applications, but before that, I want to talk about some stuff which I realized after I made the slides this audience probably knows a lot about, so I don't really need to cover it. But there's a variety of ways to do trustless execution, including multi-party computation, homomorphic encryption, and zero-knowledge proofs. And obviously, we'll focus on the zero-knowledge proofs today. And so some of the features that are obviously really great is that they can give privacy, validity, and no interaction. But unfortunately, they have high compute overheads. So I'll describe some techniques on how to reduce this, specifically for ML models and also for image edits, which is important for certain kinds of applications I'll talk about today. Also, very boring for this particular audience, but I just want to be a little bit concrete about what's going on here, since I'll use this notation later. The prover takes in some private inputs W and some public inputs X and produces a proof. This proof can then be validated by any verifier after the fact. And what's also really useful is that these proofs can be computed after the computation is done, which again is very important for certain kinds of applications I'll describe later. So I promise that I'll motivate the need for executing ML models trustlessly with several applications. And I'll first start with trustless audits. So why do we care about this? Well, as ML increases in the different uses and scenarios, we want to be sure that the models that we're running satisfy some properties. For example, for medical ML, you might want to ensure that the training data set conforms to some regulations, for example, by the FDA or some other regulators. And also recently, Twitter open sourced their algorithm, and you might want to ensure things like my timeline isn't biased. But of course, Twitter has a bunch of private user information that they are not allowed to release due to regulatory reasons. But they still might want to show that certain properties like this. So how can we accomplish this with ZK snarks? Well, we'll use two steps. The first step here is the proof of training, which unfortunately also has two steps. The first thing to do is to commit to the training data. And so, for example, you might want to commit to the images that you're using for training a medical ML model. And then you can, in fact, unroll the entire training process. One common method of training ML models is using what's called stochastic gradient descent. And you can produce ZK snarks of the training process to ensure that the model that can be committed to at the end in a hiding manner was actually trained on the data that you committed to originally. Then you can compute these audits trustlessly. And in general, these audits take the form of a function of the data and the weights. And in particular, all of these can be hidden using the process I described in the previous slide. And as I mentioned, there's many different kinds of audits that you might want to run. For example, that your data isn't biased for medical ML, that your model performs well, also, for example, for medical models, and say that your timeline isn't biased, and a whole host of other things that consumers might want to know about the models that they're consuming. Another important type of audit might be that your training data doesn't contain any copyright copyrighted images. I also want to talk about two other applications before I go into our open source framework. And I'll first start with decentralized prompt marketplaces. Just to get everyone on the same page, there's been a huge boom in generative AI in which you take in some inputs. In this particular example, it's an astronaut riding a horse. You pass it through some complex model, and then out comes an image or a piece of text or audio or some other thing generated by an ML model. Now, this particular prompt is very simple, but there's a whole host of other kinds of prompts that you might want to use. So let me try to read this. Cinematic, off-center, two-shot, 35mm film, still of a 30-year-old French man, curly brown hair, and a stained beige photo. Anyway, you get the point. These prompts are complicated and, in fact, require a lot of effort from individuals to create. And they're also very valuable. Now, if you try to reverse engineer, for example, this one, this is my best attempt at this. Clearly, I'm not very creative. But the point I'm trying to make is that these viral images that are generated from these amazing generative AI methods require a lot of effort to create. And I want to put a number on this, actually. Prompt engineers can pay up to $335,000 US per year just to generate these prompts. Now, I'm not going to make any commentary on this, but you might want to imagine that there are very valuable things you can do, but you might not want to pay for an entire engineer to do this. So instead, what you can do is produce these, what I'll call proof of prompts. So to do this, you can take in the inputs, which can be hidden, as I described earlier in this talk, and produce a ZK snark, which generates the output. Now, one thing that I might want to do is that, let's say I want to do some marketing based off of that looks something like this. I can then purchase this prompt, which the user can then reveal to me, and then I can modify it to set for my own particular use cases. For example, I might want to have a diverse set of prompts for different kinds of backgrounds to target to specific demographics. And ZK snarks will enable this in a decentralized manner. The last application I want to talk about is trustless biometric authentication and also fighting deepfakes. And this is the application I'm personally very excited about. So first, what are deepfakes? Well, deepfakes are images or video that modify what a person looks like, and specifically for a malicious or for a malicious purpose or to spread misinformation. I want to contrast this with the harmless forms of generative AI, like I showed in the previous slides. In the opening session of today, zkpod.ai was mentioned, and this is an example of a positive use, but you could also imagine taking Anna's voice and making her say terrible things. And you might want to be sure that she doesn't actually, Anna might want to prove that she didn't actually say these things. Now, unfortunately, with the rise of generative AI, deepfakes are also on the rise. The things I'm listing here are actual uses of deepfakes that have been already used today. They've been used by state actors to spread misinformation, to trick businesses into miswiring funds, and even fool unsuspecting consumers into being scammed. This is one example of ftxcompensation.com, which I do not recommend visiting. Okay, so to fight deepfakes, there's many parts of the technology stack that need to do to enable this. And one of the things I want to tell you about is these things called attested cameras. Now, attested cameras contain hardware devices in them that sign the pixels that come off the sensor immediately upon capture in a trusted way. And after you have the signature, it can attest that it took a specific photo, but say not a deepfake. Now, of course, attested sensors are great for this very particular operation, but there's unfortunately many things it doesn't help with. In many circumstances, the taker of the photo wants to edit the images privately. Now, one obvious example is that you might have this very valuable credit card that you want to crop out before releasing the photo. But also, even for biometric authentication, if you take a photo of yourself, say a selfie, it might contain extraneous information, and you might want to crop down to the specific part that contains your face. But also, if you want to do this in a privacy-preserving way, you can't reveal the original image. Now, to address this, I developed ZK Image, which can attest to image edits securely and privately. And the way this works is that given the signature or the commitment to the original image, ZK image can take this as a hidden witness and then output the image, an edited image that's done using ZK snarks, so that the consumer of the photo can verify that the edits were done honestly. For example, that I didn't run an AI method that swapped out the face. So I mentioned that attested cameras themselves don't solve the problem, and neither does just ZK image. ZK image needs to also be combined with other kinds of technologies, for example, decentralized ways of tracking these signatures. And so, for example, you might have a registry which contains the signatures of the original images and the proofs. And whenever someone wants to consume the image, they can then consult this registry. You also might want to attest to multiple edits, and in order to do this, you might have to use multiple proofs. I won't get into the technical details today. They're described in our preprint on arXiv, which you can find on my personal website. I also want to talk about how to do a trustless Face ID using these technologies. So the first thing you do is you can take a photo of your face using an attested camera, and you need this to validate that the photo actually came from the real world. And then you perform some image edits, for example, cropping the photo to only contain your face. You might also do other things like rotating the photo or sharing it to be better for the next step, which is to input it to a Face ID model. And then by combining these steps, you can then produce a proof that, say, your face embedding matches one that you uploaded previously. And this can all be done privately without revealing sensitive biometric information to service providers. Great. So now that I've talked about the various applications of ZKML, I want to talk about the open source framework that I just released yesterday and what it can enable. So if you look at the frameworks for zero-knowledge proofs on some of the prior work, all the prior work operates on these unrealistically small images. For example, on these data sets, which are very common in ML, like MNIST or CFAR10, which are these tiny images which are really used for just toy demonstrations of capabilities. And with our framework, we can scale this to ImageNet, which is a realistic sized data set that's actually used in, where models of this form are used in production, and also other models, which I'll briefly mention, like GPT and diffusion models like the generative AI things that I mentioned earlier as well. So in order to produce our framework and produce these ZK snarks in an efficient way, we need to make many design choices, and this ranges all the way from the ML side straight down to the proving stack. And this includes choosing the correct architecture, arithmetizing the DNN computation efficiently, and leveraging the proving system in such a way that you get high efficiency. From an architecture perspective, we use quantized models, and we do it in such a way that we can achieve high accuracy despite doing the quantization. I'll briefly talk about this later in the talk, but just to give you a sneak preview of results, using our quantization methods, you lose something like 0.02% accuracy compared to some other frameworks and other libraries that lose a lot of accuracy when doing quantization. We also have to optimize the arithmetization, which is basically how the circuit is laid out, and use the proving stack efficiently. I won't go into the technical details. I'm sure everyone here is tired after a long day of staring at math all day, so I'll just briefly talk about what we do. We do the linear layers efficiently using custom gates with these polynomial constraints. The non-linearities via lookups, and we do some tricks with the fixed point arithmetic to be a little bit more efficient compared to just doing the operations naively. So to use ZKML, all you need to do is install Rust, clone our GitHub repository, and run our example. And in this example, we have an MNIST model which achieves 99.5% accuracy, and this will actually run on your laptop, and it runs in about 4 seconds, which, as far as I'm aware, is the most efficient proving of an MNIST model that achieves over 99% accuracy. But in addition to that, I also want to talk about the evaluation of our framework, ZKML, on realistic models. And what we'll focus on in particular are these things called mobile nets, which are also used in production. In fact, many of them are running on your phones today. So in the paper that I published on this earlier last year, we can achieve around 79% accuracy on ImageNet with proving times of around 2,500 seconds and verification times of around 10 seconds. With our open source release, we can get, this is a bit outdated actually, we can get 13% higher accuracy, 6 times cheaper proving, and 500 times cheaper verification. And all the applications I described earlier really depend on the efficiency of being able to run these ZK, to compute these ZK snarks in a reasonable amount of time. And we're working really hard to ensure that this is accessible to everyone, not just the most powerful servers in the world. Now, just to give you an example of the improvements, let's say you want to use our framework to verify a private model's accuracy. These are the costs with our previous work, but with our new work, and this is the cost of proving, we can take down the cost of verifying a model's accuracy within 1% to from around $2,500 to about $400. And just to put this in context, for a medical data set, it might cost around $85,000 to produce the labels for this. So verifying the accuracy is becoming increasingly feasible, especially in comparison to how much the training data costs to obtain. So as I promised, I think we're ending a little bit early, so plenty of time for questions, but also to relax after the talk. But in conclusion, we're increasingly interacting with digital systems, and zero-knowledge proofs provide trust in the face of adversaries, and this includes for ML models and also against deepfakes. We just open sourced a framework yesterday. The link is available down here. My email is here, and my Twitter is here as well. I'm happy to be contacted offline if you have any questions, but I also think there's some time for questions now as well. Thank you for coming to my talk.
Thank you so much for that talk. Are there questions, thoughts, comments? And actually, if you have a question, just put your hand up so I spot you.
Hi, welcome. I read your previous printed version, and yeah, actually I asked a question on the Telegram. So I'm curious about the improvement, this huge improvement of the proving time and the verification time is given by, let's say, a Hello tool or given by anything else? You have some specific trick or improvement on that?
Yeah, so the question was about where these improvements come from. There's a number of things we did to improve the performance. So for the verification times, we allow both IPA and KZG has much more efficient verification. We also have many improvements in the actual arithmetization of the circuits, the way that we do the fixed point arithmetic to increase the accuracy, and also some algorithmic improvements on how to do, say, convolutions and matrix multiplies more efficiently. We'll have a blog post detailing all of our improvements in the upcoming weeks. So be on the lookout for that. I'll announce it on my Twitter, and also happy to, if you contact me offline, I can provide some more follow-ups as well.
All right, Guillermo, you go first.
So quick question. You mentioned that you could potentially do provable training, which seems particularly difficult, right? Because provable training requires that you try a bunch of seeds and do a bunch of like different stuff. Like it's a little bit more of a dark art than just inference. So does this framework currently support like provable training, or is this just like a thought exercise at the moment?
Yes, the question was, do we support provable training? The answer is yes, actually. We have results that unfortunately came in after the slide deadline. And so they're not here, but be on the lookout for the blog post. Roughly speaking, so training has many complexities beyond inference, as you mentioned. So it's a little bit more difficult. With our preliminary results, we can achieve nearly the same accuracy as full floating point 32 precision using our framework. and also at reasonable cost relative to the cost of the labels on this data set. And be on the lookout for that. There's actually, if you look hard enough, you'll be able to find it in our repository, but it's not ready for public consumption yet.
Thank you. Thank you so much for the talk. I was actually also going to ask about training, because I read a paper recently and it said that you can embed an adversary example in a network and it will be undetectable, but they will always be able to provide an output they would like to get from the network. That's why I think training would be very important to be verified if you want to actually use the ZK proof of inference. My other question is, you mentioned that the loss of precision is very little because of quantization. Do you have the numbers for GPT? Because I also know you did GPT-2 proving. Do you have numbers of how much of a loss was there?
Right, so there's two questions here. The first is about training and planting backdoors. I believe you're referring to the Shafi Goldwater paper. We can avoid this, we can literally provably avoid this through some mechanisms which, well, okay, basically, once you commit to the training, you can do this in a way that the commitment, and you can basically base the data traversal order based off of your commitments in such a way that the trainer cannot mess with it. So this prevents those kinds of backdoors that are specific to that paper. In terms of your other question, accuracy on GPT, that is a great question. Unfortunately, accuracy for generative models is much harder to measure for many reasons. But if you compare the outputs of our framework compared to the outputs of using floating point FP32, so full precision, we have like an error in the vector outputs of maybe like 1% or something. So we don't think that there's going to be a substantial loss in accuracy. And we're also actively working to bring this number down as we improve our framework. So happy to talk offline about that as well.
Thank you very much.
Great. There's a question back there and one over here.
Hello, thanks for the talk. I was just wondering, in the case of the generative models, where you've got some randomness that is used to generate the response, is there a way to prove that it's truly random value and that the model hasn't been run many times? Or is there a hope of a solution to that?
Yes, the question is for generative models, there's often some randomness that needs to be input to the model. And if there are ways to ensure that the randomness wasn't chosen in some adversarial manner. The answer is actually yes, although it's not necessarily within our framework. There are several things you can do. So one thing is that you can use the verified randomness, for example, from the Ethereum beacon chain as inputs to a pseudo-random number generator to generate the randomness. And you can prove the pseudo-random number, and you can do the snarking of the pseudo-random number generator to verify that you can't, that the producer of the generative output didn't cheat. And one way you can do this is you can say, okay, you can commit ahead of time that I'm going to use like the randomness from the block like 1,000 blocks from now, so it's hard to cheat. And there's other ways you can do this as well by using other forms of verified randomness. For example, you can hook up to random.org if you trust them, and other kinds of techniques as well.
Oh wait, there's one up here actually that was first here. Oh, you're going to go around.
In practice, how high an assumption is it to trust that the sensor produce authentic data, such as Face ID or a camera that signs the input?
Yes, the question is, in practice, how much can we trust the attested sensors? And this is always a work in progress, but I think that as this problem becomes more and more prevalent, the public desire for these kinds of things will increase, and so will the security. So, in some sense, there's no way to fully block against physical attacks. Like, if I'm willing to pay enough money and wait enough time, I can get plastic surgery to look like someone else. But we want to raise the cost of performing these kinds of attacks beyond being able to do this entirely in software. And that's the hope, especially as these technologies advance, as people realize that generative AI can be very dangerous in addition to being very useful.
I see a question over here. Yeah, if there are any last questions, just put your hands up now so we get you.
Thanks very much. Very impressive work. Do you have already plans on improving further? I mean, not to be demanding, but maybe recursing or aggregating or folding even? Is this things you're thinking about?
Yeah, so the question is, are there plans to improve? It's a hard audience over here. No, sorry. We have many plans to improve. There are things, there are optimizations ranging from the proving stack to like aggregation, for example, for training in particular, to optimizations on the deep neural network level, and also just on the basic computer systems level to improve the performance of our framework. And that's in the works. I'm happy to chat about the specifics offline if you want to get into nitty-gritty technical details.
Perfect. Seems like that might be our last question. Thank you so much, Daniel.
Thank you.
So, wow, I don't have any slides. This brings us to the end of ZK Summit 9 here in Lisbon. It's amazing. Thank you all so much for coming through. The talks today were so, I mean, I was mostly on this main stage. I can't wait to see the videos for the other stages. I know over here it was just phenomenal. Thank you to all the speakers for bringing, you know, this amazing information to everyone. I want to say a massive thank you to the team, who I hope is partly in here this time. Big thank you to, is Agnieszka over there? Is that you? Yes. For making this happen. And to Rachel, Henrik, Kobe, wherever you are. I don't know if there's anything else I'm supposed to say. I know that there was some misunderstanding about the timing on the party. So we're going to be wrapping up here. We're then, you know, feel free to go eat, go for a dinner. The party is, I think we're saying 9. And I don't think we have much food there, so you should probably, if you want to have dinner, you should probably do that before. You need a wristband to get in. It's at a place called Suspenso, which is near the Castello, near the castle on the hill. If you go to the center, sort of like downtown-ish, it's close to there. So I hope to see you there. And thank you so much again for coming. And stay kind of on the lookout for ZK Summit 10. I think maybe, I mean, a lot of you went through this application process this time, and some of you maybe also saw that like tickets went pretty quick. If you want to come to the next ZK Summit, like be early, get that application in. It definitely helps us also to just like get a better count early on. So yeah, I hope to see a lot of you there. Thanks so much.